Hi, my name's Mike Fitzpatrick.
And I am Ákos Lédeci.
We're coming to you from Vanderbilt University in Nashville, Tennessee.
We have put together a course whose purpose is to teach computer programming to people with little or no programming experience.
To program a computer, you have to use a programming language. There are a lot of them. You may have heard of some of them, C++ and Java, for example. But for this course, we've decided to use a programming language that you may not have heard of. It's called MATLAB.
The purpose of MATLAB's designers was to make programming easier, especially for solving numerical problems.
And they succeeded. MATLAB is very easy to use and to learn, and at the same time is very powerful. It's used worldwide by professionals from scientists to engineers to economists.
Many of the devices you use daily, your car, your smartphone, have features and components that were developed with the help of MATLAB.
And when you see the news about a NASA mission, you can be pretty sure that their programmers and computer experts used MATLAB to make it happen.
Our purpose with this course is to teach the basics of computer programming and MATLAB.
The level of the course is that of a college introductory first-year course. It's 9 weeks long, including 8 weeks of video lectures and 1 week for a final homework submission.
If you follow along with us, try all the examples as you'll see, do the quizzes and the homeworks, then by the end of the 9th week, you'll be able to program a computer.
In fact, you'll be good at it, and you should have fun doing it.
And as an added benefit, all registered students of this course will get a free MATLAB license.
So what are you waiting for? It's time to learn computer programming with MATLAB. Welcome to Computer Programming with MATLAB. This is Lesson 1, Introduction to MATLAB. My name is Mike Fitzpatrick, and I'm coming to you from Vanderbilt University in Nashville, Tennessee. I'll be your lead instructor, but this course is a team effort. There are many people involved, including the co-creator of this course, Ákos Lédeci, who both directs the course and handles student evaluations. Ákos and I are members of the faculty of Vanderbilt School of Engineering, and we designed this course to teach computer programming to students who have little or no experience with programming. In fact, we're aiming particularly at those of you who've never even been introduced to programming. And for that reason, Coursera's title for this course is Introduction to Programming with MATLAB. The level is targeted at first-year college students and high school seniors, but really this course is suitable for anybody who wants to learn programming from high school to grad school to retirement. The length of the course is 9 weeks, and that includes 8 weeks of video lectures plus an extra week for a final homework submission. Throughout that time, we teach one programming language called MATLAB. And because of that, this course has also turned out to be handy for people who already know how to program, but who want to learn MATLAB from the ground up. MATLAB makes it especially easy to learn programming. So if you follow along with us, repeat all the examples that you see me do on the screen, take the quizzes and do the homework, then at the end of these 9 weeks, you'll be able to program a computer. You'll be good at it, and you should have fun doing it. To program a computer, you have to use a programming language. The first languages were complicated affairs of strings of ones and zeros or cryptic code words and numbers, and then in 1954, all that changed. A language was invented that was much more like a human language. It was called Fortran. Its purpose was to make programming easier, especially for solving numerical problems. Since then, hundreds of such languages have been developed. And in the 1970s, a new wave of them began. The most successful of these were C, C++, Java, and C#. And they're still heavily used languages. They're used especially for writing very large programs, by which I mean programs with hundreds of thousands or millions of statements in them. These programs are the shrink-wrapped products used by non-programmers, things like word processors, spreadsheets, web browsers, games, operating systems, and the like. In the midst of this new wave, another language appeared called MATLAB, and that's the language we're going to use in this course. MATLAB's purpose was to make programming easier, especially for solving numerical problems. But you may have noticed that was exactly the purpose of Fortran. So have we come full circle? No, because MATLAB is far easier to program than Fortran. I know, I've used them both. So where did MATLAB come from? Well, it sprang from the mind of one person, an expert in Fortran, by the way, named Cleve Moeller. Professor Moeller was teaching students at the University of New Mexico to solve numerical problems with Fortran, and they were spending way too much trouble struggling with the language. So he invented MATLAB, and it soon became so popular that Moeller teamed up with an engineer outside academics named Jack Little to form a company to make it available to the world. They named the company the MathWorks. It was formed in California in 1984, and it had one product, MATLAB. Well, that company is alive and well today in Natick, Massachusetts, 3,000 miles from California. And today it has 100 products, all based on MATLAB, and over 1 million users worldwide. And it's taught in 5,000 universities, including Vanderbilt. MATLAB is clearly having a big impact on the world. And in 2012, the Institute of Electrical and Electronic Engineers recognized that impact by giving Dr. Moeller its Computer Pioneer Award. They give this award out once a year, and they named it for improving the quality of mathematical software, making it more accessible, and creating MATLAB. And that brings us to this course. Computer programming with MATLAB is our effort to add to the impact of Moeller's creation by using it to make computer programming more accessible to you. There's no required textbook for this course, but there is a recommended one. As you can see, the title is the same as that of the course, and Akos Leditsi and I are the authors, so it's no surprise that it's the one we're recommending. This is an ebook, no paper is involved. It's been used at Vanderbilt since 2013, and previous versions of it were used since 2000. The book is organized into 3 major parts, which in the iBook style are called chapters. This course covers Chapter 1 and 2. The remaining Chapter 3 covers subjects that are beyond the scope of this course, but you'll be able to continue through that chapter on your own after you've completed this course. The book is available online at cs103.net. You'll find 2 versions there, an iBook for Apple's iPads and Macs, and a PDF for any other device, and they cost $9.99 each. To make our textbook and our course more effective, we approach MATLAB programming as part of the discipline of computer science. Computer scientists have spent over 50 years developing a concise set of concepts and a consistent vocabulary to describe all aspects of computer programming. And in both this book and this course, we use those concepts and that vocabulary to introduce you to computer programming. This approach will give you an idea of how computer scientists think, and it'll make it a lot easier to learn MATLAB. Well, let's take a look at the iBook. I'm going to show it on this MacBook here, but the iPad has the same features. The only difference is that instead of clicking a mouse, you touch the screen on the iPad. So after you've purchased it and downloaded it, it should be in your iBooks collection. Let's find it here. There it is. I've got it under Computer Programming. And if we double click it, it opens up and then it takes you to this page. Now we see down at the bottom a scrollable list of pages. There's pages at the front. Here's the preface. Here's Getting Started, Procedural Programming, Advanced Concepts. But I'm not going to click on those. I'm going to go up here and click this table of contents here. Let's click this little arrow next to Getting Started. This is Chapter 1. And we see Section 1 of Chapter 1 and 2, Introduction to MATLAB, Matrices and Operators. We'll spend a lot of time near the beginning of this course right here in Matrices and Operators. So let's go there. At the bottom we see we're on page 33. Let's go to page 34. If you look around here, you'll notice some lowercase words in blue type. If we click one of these, let's click matrix, we see a definition. A two-dimensional rectangular arrangement of numbers, also known as a two-dimensional array. And there's two links. One says glossary, one says dictionary. Let's click the glossary. That's the glossary of this book. And these are the, you might say, official definitions that will help you the most as study aids when you're trying to understand programming. And here's a link that takes you to the first occurrence or the defining occurrence of the term in the text. Right back here where we were. There are other special study aids, including setting bookmarks. Just click at the top up here, right on that little bookmark icon. It turns red, indicating that this page is now bookmarked. Let's bookmark a few more pages. I'll go forward a bit and bookmark this one, and maybe we're done. Now, if you go up here and click on this little arrow just to the right of the bookmark, you see a list of your bookmarks. 41, 37. Let's go to 37. Okay. Let's go to 34. That's where we started. Highlighting and annotating are both easy too. Just click and hold the mouse while you slide over what you want. And maybe I wanted to put a note. I want to try this in MATLAB. And down here, I'm going to highlight that in pink. To see all your highlights and annotations collected together, click up here at the top of the window on this page icon here. This section called Notes shows up. They're exactly the two highlights we just did, and it shows what page they're on. If you want to delete one of these, you just go to the one you want to delete, click on it. You can remove the whole thing or remove part of it. One last standard iBook study feature is found by clicking the Study button up here on the left corner. It'll give you the annotations like that. You can click here. Then we get to glossary terms. Flip the card, and it tells you the definition. And you can go to one after the other and try them. Clicking Done will get us back to the book. And if you want to close the Notes section, just click this little page icon again, and it's gone. Okay, that's a look at generic iBook study features, but there's one essential study technique that we've left out. Practicing what you're learning by working problems. Let's go to the table of contents again. And loops. Let's click Practice Problems down here. There. And you see these little question marks here. Well, those are where the answers are. So, for example, problem 21 over here, if I click this little question mark, I find the answer. So I'll close that. There's one last thing I want to show you about the iBook. It includes animation. Somewhere in this book is an example called Surface Plot Animation. Well, up here in the right corner, we see a little search icon. Let's click that. I'm going to search for that surface plot animation. Hey, it showed up right there. Let's go there. There's a play button here. Let's click that. No, that's kind of cool. Okay, enough with the preliminaries. It's time to get down to business here. After you've picked a textbook and downloaded and installed MATLAB, or got your license to MATLAB online, you're ready to go. So what's next? Let's run MATLAB. Well, I'd like to welcome you to the future. In 2016, 2 years after we recorded the original videos for this course, the MathWorks brought out an entirely new way to get MATLAB. In this video, we're going to run MATLAB, but you got to get it to run it. And to get it, you now got two options. One, you can use an installed version like one of these, over here on my computer desktop. Or 2, you can use an online version. Option 1 up here requires that you download an installation package and use it to install MATLAB on your computer. If you are lucky enough to have MATLAB installed on your computer already, as I do, you're in great shape because you don't have to download or install anything. You can get started immediately. If, on the other hand, you do not have an installed version of MATLAB on your computer and you do not have a license to allow you to get one, you are still lucky and you are still in great shape because with option 2, the online version, you never have to download or install anything. And the very nice people at MathWorks have decided that just for enrolling in this course, they're going to give you a free 12-week license to use their online version and 250 megabytes of space to store programs. You can find out how to get that online version in the resource section of this course. MathWorks has put in a huge amount of work to make this option available to you, but it should take you only about 5 minutes of work to get it. So there are 2 groups of you taking this course. Some of you will be using an installed version of MATLAB like, these up here, and some of you will be using the online version. So which version are we going to be using in this course? Well, it depends on where we are. I'm not talking about where we are in the world, which for me is the Vanderbilt School of Engineering in Nashville, Tennessee. No, I'm talking about where we are in time. Right now, as I'm recording this video, it's March 2018. And in this video, I'm going to introduce you to the latest installed and online versions of MATLAB, both of which are called R2018A. In fact, you can see the icon for the very latest installed version right up here at the top, R2018A. I'll open that up in a minute, and I'll also open up MATLAB Online and compare the two and give you an introduction to them. Then we're going to get in my time machine, which I've got warmed up and hovering right behind me in the studio. Let me see. Yeah, it's back there. And it's going to take us back to 2014 when we began recording these lectures. And while we're there, you'll see me using the latest version available back then, which has been sitting right here on my computer for 4 years, waiting for me to use it again, my good old trusty MATLAB R2014B. And look at that. That is exactly how I left it back there in early 2015 when I recorded the last segment of Lesson 8, which you will be watching in Week 9. Thanks, old friend, but right now we're going to let you rest just a little while longer. I don't have the heart to tell it, but except for this little cameo, we're not going to use it at all for any of the new videos. Hey, we're 7 releases past it now. Its days are way over. But I do take it out for a spin every once in a while. It still runs great. And this brings me to a very important point about MATLAB. That 4-year-old version of MATLAB is almost identical to the model you'll see in the showrooms today. In fact, as you follow along with me and do the exercises that we recorded with it almost 4 years ago, you might not notice any difference at all, even if you're using the latest version. Sure, each new version is an improvement, but the MATLAB language stabilized many years ago, so the changes are incremental, and that's a very good thing for 3 reasons. First, you don't want to write programs in a language that is rapidly changing because the programs you write today might not work tomorrow. Second, if MATLAB were to change significantly, I'd have to record 12 hours of videos all over again. That would make me cranky and crabby. And you wouldn't like me when I'm cranky or crabby. Third, you wonderful people out there who are writing Chinese, Dutch, Korean, Romanian, and Spanish subtitles for us would have to do that all over again. You know what? That's a lot of work, and Akos and I are very grateful to you for doing that. Hey, wait. No français, mes amis? Quelle horreur! Of course, even stable languages can get new features, and when features are added to MATLAB that we think you should know about, we'll add them to the course. In fact, we're adding a few good ones to the videos toward the end of this course this very year. So I've got 3 versions on my desktop, and you can have as many versions of MATLAB as you want or can afford installed at the same time. And if you want to hear your computer's fan run, you can fire them all up at the same time. But they're all backward compatible, meaning that the old code will run in the newer versions, and really there's no reason to have more than one. Unless you are a total MATLAB nerd, or a totally cool MATLAB instructor, and of course we know which one I am. Oh, is that so? Okay, fine. That's fine. And I assume you know what nerd means, right? Yeah. Naturally endowed for research and development, N-E-R-D. And of course you know that nerds are the people that make our world such a nice place to live in. You know, that find cures for diseases, that launch rockets, provide the internet, invent GPS, a cell phone, and that computer you're looking at right now. I just thought of something. Since you're on that computer taking this course, learning MATLAB, you might be a nerd yourself. Well, if you are, then you're a member of a very exclusive society, and you might even be a genius enhanced with engineering know-how. There's an acronym for that, too. But I digress. Let's just double-click this MATLAB 2018A icon and fire this baby up. And we'll have a look at it. That launches MATLAB, and a window opens up to show the MATLAB integrated environment, which is usually referred to simply as the MATLAB environment or as the MATLAB desktop. This desktop is perched on top of your computer's desktop, and that's where you'll type all your MATLAB commands and where MATLAB will show you all your results. When you first open it up after its installation, this Getting Started link shows up here. You can check this out, but we don't need it for this course, and we need all the space we can get in the desktop, so I'm going to click this little X and dismiss it. You can move the window around and reshape it. And I'm going to do that to make room for MATLAB Online above it. That's right. The name of the online version is appropriate enough, MATLAB Online. And it's really pretty slick. To run it, all you need is a MathWorks account and a web browser, and then you can use it on any computer, anywhere, anytime, as often as you want. To run MATLAB Online, I'll just launch a browser. I like Chrome, but since I'm on a Mac, maybe I should use Safari. Well, just to show I'm not playing favorites, let's flip a coin. Heads, it's Chrome. Tail, it's Safari. All right. Chrome it is. I'll type in this address, https://matlab.mathworks.com. Hit return. And here we are at the login prompt. It's a good idea to bookmark this site. I'll do that, because you'll be coming back to it a lot. I type my login. Well, it's actually already there. I guess Google has remembered it. And it's remembered my password too. Use password for that. Then I come down here. I can just hit return or I can hit login. I think I'll just hit return. And after a few seconds, there it is, MATLAB Online. This is its default layout, but I prefer a different layout, which I can get by going up here and clicking on Layout, and then clicking 3 column. And I want to adjust the window. So we can see MATLAB Online and MATLAB install at the same time. Let's get them just so. There. I want to give them the same amount of space each because I don't want to play favorites here. I don't know which one you got. There we go. But wait, before we do another thing, you need to get your version of MATLAB going too. You got to do that right now because you need it so you can do everything I do right along with me at the same time. You can't learn by just watching me. You have to do everything I do, pausing me whenever you need to so I don't get ahead of you. It's like your yoga class. You won't get any benefit from just watching me do exercises. If you have either MATLAB online or an installed version of MATLAB already, great. If you don't, then you need to stop right now and follow the written instructions that we posted in the resource section of the course website to start your free 12-week license of MATLAB online. And so you won't miss anything, I'll end this video right now and wait until you get set up. When you have your MATLAB desktop open and ready, you can start me back up in the next video and we'll put it to work. Welcome back. I hope you didn't have any trouble getting MATLAB and that you're ready to start using it. So I've got two MATLAB desktops open here, as you can see. MATLAB Online on top and my installed version at the bottom. And you should have one desktop open, either MATLAB Online or your installed version. This is a good time for me to point out one big advantage of MATLAB Online over any installed version. Any computer tool that you access with your web browser, like MATLAB Online, will periodically improve without you having to do anything. One day it looks and behaves like, well, this. And the next day or the next month, you may open it up and find that it looks a little different and it's got some new features. And that's a very good thing. With this auto-updating of online tools, you don't have to install anything, and yet you always have the latest and greatest version. The side effect is that the MATLAB Online that you see in this video might look slightly different from the MATLAB Online that you are running because you are out there in the future and I'm stuck back here in March of 2018 using R 2018A. But the difference won't be big unless you're so far in the future that you're wearing a silver jumpsuit and people are taking vacations on the moon. The generic name for tools like these, whether they're MATLAB Online or Install MATLAB or Excel or Chrome or Call of Duty World War II, is Graphical User Interface. Or using the initials, as most programmers do, we call it a GUI, spelled G-U-I. And like any decent GUI, as we've seen, we can resize it and move it around on our computer screens, and we can use the mouse and the keyboard to interact with it. Inside each of these two MATLAB GUIs, we see three sub-windows. The current folder over here on the left in each of them, the workspace over on the right, and the command window in the middle, which is labeled down here in the installed version, but is not labeled up here in MATLAB Online for some reason. You can see that the three-column layout is the default for the installed version, and I like that arrangement. But you can move things around a bit. To do that, just left-click the window label, and while holding that left button down, drag it somewhere else. Say, let's drag this current folder window over here under the workspace. And it'll pop into place, and you release the mouse. Well, I hate this setup, so I'm going to put it right back where I had it. There. That's a little too wide. Let's move that back over there. And this is a little too wide. There. Just right. Now I'm happy as Larry with my setup. By the way, if you quit MATLAB and restart it, it'll remember your last layout, so you don't have to keep moving things around every time. Okay, we've got command windows. Let's start commanding. We can look at the other windows later. If we left-click anywhere in a command window, say up here in MATLAB Online like this, we'll see a little vertical bar start blinking on and off just to the right of this pair of greater than signs. That blinking bar tells us that MATLAB is ready to receive a command, and that pair of greater than signs is MATLAB's prompt. And what's a prompt? Well, let's look it up in the textbook. We click on glossary, and we see the first definition. Abstract class. Well, you can learn about abstract class toward the end of this book, where we introduce the object-oriented programming constructs in MATLAB. Object-oriented programming is one of the advanced concepts that we mentioned that are beyond the scope of the course. But let's type prompt into the search bar. There it is. And there's our definition. A prompt is a symbol or symbols printed by a program, MATLAB is an example, to indicate that it is ready for input from the user of the program. MATLAB uses the prompt greater than greater than. To input a command, you type it on the keyboard, and that blinking bar shows you where it will appear, which is just to the right of the prompt. So, are you ready, Commander? It's time to issue your first command. I don't know about you, but I'm pretty excited. And here's the command that we're going to give. Type X space equals space 1 space plus space 2 and hit return, or it might be enter on your computer. All right, here we go. Okay, maybe I built that up a little too much. Here, let me do the same thing in the installed version. And let's think what just happened. In each desktop, MATLAB created a variable named X, calculated 1 plus 2, stored the result, which was 3, in X, and then printed the value of X. I should say lowercase x, because if I'd used an uppercase X, that would be a different variable. Oh, and all those spaces around the equal sign and the plus sign, not necessary. I just included them to make it look prettier. Here, let's leave all of them out. Works the same. Spaces are used in MATLAB, but they're often not needed. Usually you'll find that if you can make sense of what you typed with or without spaces, then MATLAB can too. Speaking of space, I don't like all those vertical spaces between the lines that MATLAB keeps putting there. It does that by default, but we can stop that by giving this command. Format compact. Now let's type x equals 1 plus 2 again. And no, wait, that's way too much work. Man, I can't be dealing with typing all kinds of characters over and over just to get the same command twice. No, that's not for me. I'm a man of efficiency. Instead, I'll just hit the up arrow on my keyboard 2 times. That pops up the last command I typed and then the one before that. And now all I have to do is hit enter. Bam. And there it is. And this time all those useless, screen-hogging, annoying, terrible, horrible, no good, very bad vertical spaces are gone. When I used that up arrow to see previous commands, MATLAB showed us its so-called command history window. The command history is an extremely handy feature of the desktop, and you'll find yourself using it a lot, and we'll use it in this course. Let's hit the up arrow again. And this time, we'll click this tiny down arrow here and select Dock. When we do that, the command history window is no longer a pop-up window, but is right there all the time for you to look at it. It ended up right over here under the workspace. You can scroll around, double-click a command to put it in the command window where you can hit return to execute it. Or you can just drag one over here to execute it. Hit return and there it goes. Of course, MATLAB Online has a command history too, but while we've been neglecting it up here, it is timed out. No problem. We just log back in again, and it'll come right back. And you can use the up arrow to run previous commands. And as you can see, it remembers the previous commands from one login to another. There is a difference, though. When you hit the up arrow in MATLAB Online, only one command appears at a time, not the entire history. Okay, I'll hit return to execute it. Ugh, it's still double spacing. Let's fix that. There. When you want to see the entire history in MATLAB Online, you can click up here on Show History, and it appears in a pop-up window. You can move it around and change its size. You can't drag and drop commands, but you can double-click them to run them. So there, I ran that one. There's another one. Doesn't change the spacing because we've already used it, but I just ran the format compact again. Okay, that's it for the command history. Put that away. But before we move on, let's tidy up the command window. It's gotten very cluttered. There are buttons for that in both versions, but I like to type more than click, so I'll use a command to do it. CLC, clear command window. There. I'll do it in the installed version too. That's much better. And I'll undock the command history. Undock. So both desktops have the same layout. Okay, it's important to get the layout you want for efficient programming, and now you know how to arrange things and how to see the command history, and you know how to use the format command to change to single spacing. There are many other formats that you can change also, such as the number of digits that are printed to the right of the decimal point. If you want to see all the formats that you can request with the command format, or if you want information about any command whose name you know, you can look it up via the search documentation field right up here to right on the top of the MATLAB desktop. You just type in format or whatever you're looking for and hit return. And up pops a window with information wherever the word format shows up. We'll look at this more closely later on. Before we go further, it's important for you to know how to regain control of MATLAB if it's taking too long to process a command. The method is different in the online and installed versions. We'll start with the online version. First, I'm going to give a command that will take way too long to complete. RAND. That's 7 zeros, my friend, and this command tells MATLAB to cough up 10 million random numbers. Okay, I'm going to hit return and step back. Whoa. And here they come, by the hundreds, and the thousands, and eventually the millions. Well, this is getting boring. But right down here, look at this little button. It says stop. Let's try clicking that. I gave it a double click. Try it again. Sometimes I've noticed it takes a couple of clicks if you've let a lot of stuff pour out onto your window. But that'll stop it. And that's how you rope, throw, and tie this little doggy. That's my rodeo talk. Shows how cool I am. Means that's how you stop MATLAB Online. Now let's give the same command to the installed version. 1, 2, 3, 4, 5, 6, 7. Return. And here they come. Where's the stop button? Well, you can look till the cows come home. Still on my cowboy theme. But you won't find one, partner. To stop this version, or any installed version of MATLAB, you need to use a special combination of keys called Control-C, which is done by holding down the Control key, or it may just say CTRL on your computer. And while you're holding it down, hit the C key. There. That's a little more responsive. Looks like this little filly knows who's boss. What, you didn't know MATLAB was a female? I would have thought the bigger surprise would be that it's a horse. And if you want to get off this horse, you can quit MATLAB by typing, guess what? Quit. Q-U-I-T. And when you hit return, MATLAB will go away. You can also left-click this red dot here up at the top left, which an X shows up when you get close to it. Or, if you're on Windows, you can click the X at the top right, which turns red when you get to it. Hey, Apple and Microsoft, isn't this feud a little silly? Anyway, another method is to click this tiny down arrow up here at the top right and log out of the online version. MATLAB will ask you if you really want to leave, and you can affirm your choice, and you'll be right back at the login screen. But this is no time to quit. We need to get back to our variable x. First, I'm going to clear the screen by typing CLC and hitting return. There. I'll do that down here too. Okay, back to the variable x. We call x a variable because its value can vary, but that value always stays the same until we assign it a new value, like this. When we do that, the old value, in this case 3, is gone. That's not special with MATLAB. Every programming language provides variables like this and manages locations in the computer's memory to hold their value. In fact, the definition of a variable in computer science is simply a location in memory that has a name and a value. The form of an assignment statement in MATLAB, and in almost all computer languages for that matter, is the same as it's been since 1957 when Fortran appeared. You type the variable's name, then the equal sign, and then an expression like 1 plus 2 or just 4.7. It bears repeating that when we told MATLAB to assign 3 in the first place to x, it did not yet exist. But that was not a problem because MATLAB created it right on the spot. All you have to do to get a variable with the name you wish it to have is to assign a value to it, and the magic genie, MATLAB, will grant your wish. This is not true for Fortran, it's not true for C, C++, or Java. They require a lot of setup work to create a variable. That's one of the things that makes MATLAB simple to use and one of the reasons that Moeller's students preferred it to Fortran after he'd invented MATLAB for them 40 years ago. For the sort of programs that are typically written in C, C++, and Java, there are good reasons for requiring all that setup work. But it's a lot easier to get a program written if you can get along without it, and with MATLAB we can. Okay, now let's just type our variable's name without assigning it anything. This time I'm going to do it in MATLAB Online, only because the installed version does exactly the same thing. Let's set x equal to 4.7 up here too, and then just hit plain old x. This time MATLAB tells us the value of x. It's not so helpful now, but very helpful if you've given 50 commands since you assigned a value to x and you can't remember what the value is. Again, there may be a bit more going on that might be obvious. MATLAB has just searched its memory for the variable named x, found it, checked its value, discovered that it's 4.7, and then printed 4.7 in the command window. Now let's ask it to look for another variable. How about, say, y? Oops. Red type is never a good thing in MATLAB. I've been programming MATLAB for 20 years, and I still get a little sting when I see one of these red error messages. MATLAB is telling us that y doesn't exist. It says undefined function or variable y because functions can have names like y or x too. And MATLAB thought maybe we were trying to run a function. A function is simply an operation that happens when you give its name. If you don't believe me, check the book. An operation that is invoked by giving its name. The computer science definition is in contrast to the mathematical definition, which is any operation that produces a result that depends only on its input. A MATLAB keyword that introduces the function declaration in MATLAB's M file. So it's a keyword in MATLAB. Well, invoked. Ooh, fancy. And I guess I left out the stuff about the difference between the computer science definition and the mathematical definition. But why do we even need to know about the mathematical definition in a book about programming? If you ask me, whoever wrote this book is just showing off. Now, we'll admit to the last thing here about the MATLAB keywords, good to know. We'll get to that a little later. Anyway, we've already invoked a function by giving its name. Remember when I typed this? The function rand. And all those numbers came flooding out? Well, I didn't press return this time. Well, rand is a function, and we invoked it by typing its name. The name stands for random, and the operation it performs is to calculate random numbers. These two numbers in parentheses, 10 million and 1, are inputs that the function used to calculate its output. Let's erase this thing before it gives us any more trouble. I'm going to click left and hold the button down and sweep over it and hit the delete key. There. However, if you just want one random number instead of 10 million of them, you can type this. Rand without any inputs gives you one random number between 0 and 1. There are lots of handy functions in MATLAB. In fact, that's one of its strong points. But there's no function named y. Since there's no function and no variable named y, MATLAB complained. Not sure why MATLAB mentions function before variable. Maybe it's alphabetical. And by the way, let's clear up any confusion between the word command and the word function. They mean exactly the same thing in MATLAB. Its documentation doesn't distinguish between these two synonyms, but it uses the word function more often than it uses the word command, at least in my experience. You may have noticed that things have been popping up over here in the workspace. In MATLAB, the workspace is the set of variables that we have available to us. You can find the fancy schmancy definition in the textbook, but you don't need that yet. The workspaces in the online and installed versions look a little different. The online version gives some extra information about each variable. We'll learn what all that means later, but right now all you need to know is the name of the variable and its value. And that's there in both versions. So what is this variable ands? Well, this is a special MATLAB variable whose name suggests that it holds the answer. And it does. It's created automatically to hold the result of any calculation that's not assigned to a variable by the user. And except for the fact that MATLAB assigns it values automatically, it's a normal variable. It's very handy because if you calculate something, don't assign it to a variable, and then you wish you'd assigned it to a variable, say zebra, then all you have to do is this. And zebra has the value 0.8147. So we know how to create variables, but how do you delete them? There's usually no reason to delete them, but if you want to reduce the workspace clutter, you can do one of two things. You can use the clear command like this. Zebra's gone. Or you can right-click the variable in the workspace, choose delete, and it's gone. Note that zebra is pink in this clear command. Or is that purple? Anyway, MATLAB uses purplish pink to mean that the name zebra is being given to the command clear instead of the value of zebra. Clear is not removing the 5 from the variable zebra. It's removing the variable zebra from the workspace. If that's confusing, forget it. The reason for the color is not that important. I brought it up because you might want to know your eyes aren't playing tricks on you. Oh, a couple of other things about the command clear. First, you can tell it to clear 2 or more variables. And second, if you give the clear command without telling it which variables to clear, it clears every variable in the workspace. Let's create 4 variables. Lions, tigers, and bears. And one more, I. And I'll give it the value of the sum of those 3 variables. Yes, you can use underscore as part of a variable name. And you can use stupid names. There are a few limitations, but almost any name you'll want to use is okay. We'll give you the rules for names later. They're simple. If you're wondering about the order of the variables in a workspace, it's alphabetical. And you can reverse the order by clicking this little arrow here, well, upward triangle. There. So now let's get rid of 2 of them with clear. Lions and I. Now we got 3 to go. Let's clear them this way. Clear with nothing after it gets rid of everything, and they're all gone. I'm sure you've been noticing things popping up while I'm typing, such as this is a list of functions that start with the letters CL. If you see one you want to invoke, you can select it and hit the tab key and it'll be typed for you like this one. And I can hit return and it'll do nothing because it's already clear. This is called tab completion. It works a bit differently in the installed version. There you hit the tab key once to pop up the list and then it's the same. Here's another example. This time, I typed the name of the function and a left parenthesis, like I'm getting ready to put an input in there, and what pops up is called a function hint. It reminds me what inputs I can give this function. Okay. Let's clean up by clearing the command window. This time I'll do it with the Clear Commands button up here. And let's do it down here too. But first I'll clear the workspace over here. But instead of using the Clear command, I'll use Clear Workspace. And they're gone. And now I'll clear this window and I'll use Clear Commands down here. Good. All tidied up, neat and nice. Okay, we've looked at the command window and the workspace window, but we haven't looked at the current folder window over here. For both versions of MATLAB, the current folder is the place where MATLAB saves the files that contain the programs that you write. And it's the first place it'll look to find files that hold programs that it needs to run. To learn about the current folder window, let's start up here with MATLAB Online. The first question is, where is this folder? Well, for starters, it's not on your computer. The current folder is inside a computer that's maintained by the MathWorks with space set aside for your use and only your use. When you got your account, login, and password, you are instantly allocated space and given access to it through this folder. The name of the folder is MATLAB Drive, and you can see the name right here in this white area, which is called the address field. We'll show you in a little bit how you can copy stuff between your MATLAB Drive and your computer, but for now we'll just focus on the MATLAB Drive itself. This bar above these three windows is called the Current Folder Toolbar, and we're going to be looking at everything in it. We've already looked at one thing, the address field, and that's this part right here. The name of the current folder is always shown in the address field. The stuff inside the current folder is always shown in the current folder window. There's not a lot to begin with there, just two folders, one named Published and one named Shared. We're not going to use these folders, but someday you may find them handy after you've completed this course as a full-fledged MATLAB programmer and you start working on shared projects with other people anywhere in the world that have access to the internet. If you want to learn about these folders and other things that we don't have time to cover in this introduction, you can find some documents on MATLAB online in the course resource links. Well, let's put some things in the current folder. The current folder, which is MATLAB Drive. Suppose I want to have a folder in there named First Lesson. Well, I come up here and click this big yellow plus sign and select Folder. This little window pops up and I type the name and either left click OK or hit the return key. And there it is. Now I want you to watch carefully. I'm going to double click my new folder, and that will make it my new current folder. I'll double click on the count of 3 while you watch the address field. 1, 2, 3, click. And as promised, its name is there in the address field. But why is the previous current folder, MATLAB Drive, still there too? Well, if you can wait a minute, I'll explain it. First, let's put something in First Lesson. I want 2 folders, Studying the Textbook and Using MATLAB, the 2 things you need to do to succeed in this course. I'll do it quickly. There. Now the current folder window shows that there are 2 folders in the current folder, which is First Lesson. Now let's change our current directory to Studying the Textbook. Remember how you do that? Just double click it. Okay, now you can see why MATLAB Drive was there. The address field shows you the path you would have to go from the MATLAB Drive, which holds everything, to Studying the Textbook. You have to first go into First Lesson and then into Studying the Textbook. In computer science terms, the folder named Studying the Textbook is the so-called child of First Lesson, which is its parent. And First Lesson is a child of MATLAB Drive. You might be tempted to call Studying the Textbook the grandchild of MATLAB Drive. Don't. Nobody says that. People will make fun of you. Yeah, and I'm still scarred by it. And no grandparents either. Oh, and a folder has just one parent, not like you and me. We have 2. The parent is considered to be at a higher level in the folder hierarchy than its children. Siblings are at the same level, and the folder at the highest level, in this case MATLAB Drive, is called the root folder. If it's hard to picture the root being at the top instead of at the bottom, just picture an upside down tree. That's what I do. One last thing about folders. Another name for a folder is a directory. and some MATLAB commands use that terminology. In fact, you may hear me occasionally slip up and call a folder a directory. That's what I was taught to call them when I first learned about all this stuff using Unix in 1980. What's Unix? Well, just Google it. Now let's do some stuff with the current folder in the installed version. When MATLAB started the first time, right after its installation, it did a couple of things for me regarding folders. The first thing it did was create this folder named MATLAB as a child of Documents, which is a child of FitzPodJM, which is a child of Users, which is the root folder. You probably figured out from this that my username is FitzPodJM. Now let's keep this on the down low, because if it gets out, it might be a security risk. It stands for John Michael Fitzpatrick, and I just celebrated St. Patrick's Day, which is, well, just Google it. You'll have your own username there, of course. The other thing that happened when MATLAB started is that it made MATLAB the current directory. Oops, sorry. It made MATLAB the current folder. You can think of this MATLAB folder as similar to the MATLAB drive folder up here, except that this folder, and all these folders, are sitting down here inside my computer, not up in the cloud. Okay, so let's put a folder in here. I'm going to name it Lesson 1 instead of First Lesson, so we won't get it confused with the folder up here in the cloud. There are a couple of ways to add a folder with the installed version. First, you can left-click the tiny down triangle up here at the top right of the current folder window and select New Folder. Second, you can right-click inside the window itself and select New Folder, which is the way I like to do it because it's easier to hit this big window with a click than that teeny-weeny triangle. Now I have a folder named New Folder. I'll change its name by right-clicking it, selecting Rename, and typing the name I want, Lesson 1. There. And as before, I'll quickly add Studying the Textbook and using MATLAB in there. This address field is not just a pretty place to see the path from the root folder to the current folder. You can use it to navigate too, and it works exactly the same in each version. So I'll demonstrate it in MATLAB Online. If you left-click one of these little triangular separators, like this one, you see a list of the children of the folder to the left. And if you select one of them with a left click, like this, it becomes the current folder. And like this. And like this. And you can left click any of the names in the path to go there. Back to First Lesson and back to MATLAB Drive. And over here on the right, you can see a list of recent current folders by clicking this little down arrow. And all this. And if there are too many, a scroll bar will appear over here on the right so you can see more. You can go to any one of them by clicking on it. I'll go to Publish just for fun. This is fun, right? We're having fun, aren't we, a little bit? Well, get ready for even more fun, folks, because in case you haven't seen enough ways to navigate through your folders, we've got 4 more. Over here at the far left end of the current folder toolbar is a so-called back arrow, which takes you to the last current directory before now, which in this case was MATLAB Drive. And when you go back, this forward arrow lights up. This one undoes the back arrow's work. Frankly, I find the forward arrow to be more confusing than useful, but if I click it now, we go back to Published. Wait, clicking forward took us back to where we were before we clicked back. Whoa, see, is that confusing or what? I just don't use it. Just to the right of these two arrows is a little icon showing a folder with a microscopic black up arrow on it. If I hover the mouse over it, you'll see its name, up one level. So which way is up? Well, up is toward the parent to the current folder, which, as we mentioned, is considered to be higher than its children. As we can see from the address field, the parent of the current folder is MATLAB Drive. So another way to explain this button is to say that it moves you to the left one step in the address field. So let's click it. And our current folder becomes MATLAB Drive. Both these arrows and the up one level icon work in exactly the same way in the installed version. All this work and we're right back where we started. Man, let's get out of here. I happen to know about a hidden door right here. It's this little icon of an open folder with a tiny green arrow curving down. We hover over it, we see its name, Browse for Folder. We click that, and what? This pop-up is only partially displayed because my browser window is too small. Let's make it bigger. There, oddly the name of the window is different from the name of the button that opened it. Select a new folder instead of browse for folder, but the idea is the same and it works like the browser on your computer, but a little slower in MATLAB Online. It shows the available file system. This folder up here, named MATLAB Add-ons, comes with the installation all set up to allow you to add things that you purchase from the MATLAB store. Don't worry, you don't have to purchase anything for this course. You and I are going to build all the things we need in our own little workshop with a mouse and a keyboard. But if you do want to buy something, you can shop at the add-on store by clicking up here on this little stack of red, green, and blue blocks. And you're at the store. The Browse button for the installed version works the same way. First I'm going to adjust things a little bit. There. The difference with the installed version's browser button is that it opens the Finder on Mac or File Explorer on Windows or whatever browser your operating system happens to provide, and you can navigate to any folder on your computer and make it the current folder when you go to MATLAB. There, like that. Okay, one last thing on the current folder toolbar here, if you can stand it. Hey, look, if I can stand it, you can stand it. Okay, way over here on the right is this little magnifying glass, which is the universal symbol for search. If you click it, then you can type the name of a file you want to find over here, hit return, and it'll look for it in the current folder and in the children of the current folder and all their descendants. But we don't have any files to search for. We got folders. We got children of folders, but we got no files. Let's create one. I'll click this X to end my file search. And then to create a file, I'll use the tool in this gray area up here. We've already sneaked up here and clicked a thing or two, but we haven't really talked about it. The area above the current folder toolbar is called the tool strip, and it contains so-called global tabs. They're global because they're always there no matter what you're doing with MATLAB. The Home tab is on top of the Plots tab and Apps tab. If I click the Plots tab, it comes to the top where we can see it, and the same for the Apps tab. But we'll spend most of our time with Home on top. Let's click the New Script button over here on the left. It's asking for a new script name, and it's already put an extension for the file name, the dot and the M. I'm going to type pretty picture in front of the dot and click OK. A couple of things have happened. First, 3 new global tabs appeared: Editor, Publish, and File versions. Second, a new window appeared here. This is the Editor window. It's where we'll type our MATLAB programs. Actually, instead of programs, I should say more precisely functions. We're going to create functions and then run them by typing their names in the command window. MATLAB will then run them. In this scenario, MATLAB is the program, and the function is part of the program. While you've got its desktop open, MATLAB is running. If you want that program to do your bidding, you write a function and invoke it, giving its name in the command window. You write functions by typing MATLAB commands into the editor window, and for most of this course, that's all you're going to do. We'll teach you all about it, but right now, all I want to do is paste a function in there that I've copied from the MathWorks website. It was written by Cleve Moeller and Jack Little back in the 1980s. I've copied it, and now I'll put my mouse into the editor window and hit Command V, which is done by holding down the Command button while hitting the V key. If you're running MATLAB on a Windows system, instead of the Command key, you use the Control key. Now I'll go over here in the editor window and click this Save button. It just turned blue. There. We have stored the MATLAB code that you see in the editor window into the file named prettypicture.m. Let's stretch the desktop down a little bit so we can see the whole function. There. It's too early in the course for me to explain how this function works, but I will mention one thing about it. All those lines that start with a % sign, the ones that are green, are referred to as comments, which means comments to the user of the function. They're not MATLAB commands, but they are important. They help people understand how the function works, where it came from, and how to use it. For example, this comment tells us that we should give the command an input, and that a good input to use is the number 500. Now we're ready to run it. We run functions that we've written in exactly the same way as we run built-in functions, like rand, and clear, and format. We type its name, and if it required inputs, we add them in parentheses. Well, that is a pretty picture. And notice that a new global tab showed up here in the tool strip named Figure. It lets you change the way the picture is presented, but we'll leave it like it is. I wonder what would happen if I changed 500 to 1,000. I'm going to hit up arrow, click the left arrow on my keyboard, come over here, hit delete, and hit 10, and return. What about 100? It's interesting how much complexity you can get out of 5 lines of MATLAB. 1, 2, 3, 4, 5. Well, 6 counting this one up here. The comments don't count because MATLAB doesn't even use them. The COS here, by the way, means cosine, and SIN means sine. These are built-in MATLAB functions that are being invoked by our function. Let's change cosine to sine and see what happens. Hit up arrow and run it again. What? Oh, my fault. I forgot to save it. See this blue? This means we're supposed to save it first. Forgetting to save, here I'll save it. Forgetting to save changes before running is a very common human error. At least that's what I keep telling myself. MATLAB Online will save automatically for you about once a minute. But you'll find that when you're correcting errors in a function, you'll need to save more often than that. The installed version saves as soon as you click anywhere outside the editor window, so you don't need to remember to save. But with the online version, you need to remember to do it yourself. So I've saved this time, but if you would, please remind me to save next time. My memory is not the best. So I'm going to run it again. Up arrow. Well, that's disappointing. I'll try changing the second one to TAN for tangent. Well, it's not bad. It's not as boring as a straight line, at least. Maybe I'll change this sign to tangent too. See what happens. And here we go. Oops. Thanks for reminding me. I would definitely have forgotten this time. I'll save it. Up arrow again. And here we go with another straight line. Okay, I've saved several versions of this file. Now suppose I want to go back to a previous version. Well, I can click this tab labeled File Versions. Click this down arrow. And it shows me how many versions I've made. These are versions I made while you were watching me. These are ones I've made before as I was working on this video for you. I can pick any version I want. Let's pick this one. That's the one we had. Or I can click this button named Older and go back one step. I can go Newer and go forward one step. And I can click Restore as Latest and give whatever version that's in the editor window at the timestamp right now as the latest version. Okay, I've fiddled with changes to this file just so I could tell you about file versions. But now I am so done with this function. Let's close its editor by clicking this little X right here. And let's go over here in the current folder window, click right on this thing, and let's delete it. Yes, I am sure I want to delete this file because for this... Oh, nuts, I should have kept this thing in case I have to reshoot this video. Well, guess what? MATLAB is going to come to my rescue. You can get deleted files back. No, there's no tab for it. There is a website. I'm going to use the URL https://drive.matlab, and you can see I've been there before, .com. You usually have to log into this just like you logged into your regular account, but I logged in a few minutes ago so to save us some time here. Well, look here. There's my MATLAB drive. There's first lesson. There's published. It's all here. There's no shared because, as I mentioned, shared is not really a proper folder. And if I click this little arrow, I get to see what's inside here. But it's all here. And down here at the bottom left, we see how much space we've used, 254 kilobytes. I have 5 gigabytes. You'll have only 250. I've got the 5 gigabytes because of a license Vanderbilt has. But you won't need, look, this is 1,000th of 254 megabytes, so you're in good shape. But there's something more important here in this page than that. Look over here at this one. Deleted files. It'll show us the files that we've deleted since we started using MATLAB Online. Let's click that. Wow, I didn't realize I deleted that much stuff. I do remember this file, ADSF. I made it by accident. I think I'll permanently delete it because I know I'll never need that. To do that, I click right on it and pick Permanently Delete. And of course it says, do you really want to permanently delete? Folks, there's no coming back from this, so yep, gone. Doing that doesn't affect the space you've used because deleted files don't count against your total allotment. And speaking of permanently deleting things, any file that stays in the deleted folder for 30 days will automatically be deleted. So let's scroll down and look for the file we want. Oh, there it is. Pretty picture. To restore it, a couple ways. You can click Restore up here, or you can click right and choose Restore. And isn't that reassuring? Pretty picture restored to MATLAB drive. Go to location. I'm just going to click here, and there it is. Okay, let's move this up a little bit. I'd like to have the same function in my installed version for MATLAB. Pretty picture. I could click New Script in the Home tab, which will open up the editor window and do all the things we did before in MATLAB Online, but that would be repetitious. And more importantly, there's a much easier way. Now that we've got the pretty picture file ready to go, I'm going to download the file from the cloud onto my computer. First, I highlight the file by left-clicking it. Then I click this Download button in the Home tab. What happens then depends on the way you've set up your browser. I have mine set up to download things to my download folder. So I'm going to look there by opening up Finder, go into Downloads, and folks, there it is, pretty picture. And that's down here on my computer. It showed up here at the top because I keep my Downloads folder organized so that the latest things are at the top. Now I'm going to copy it, go to my MATLAB folder, which I also have in Favorites, navigate to Using MATLAB, and move it there. There we go. Now let's come down here. Let's look in there. Using MATLAB. There it is. And we're ready to run it. Let's do that. And there it is. But in the installed version, it appears in a floating window instead of being docked inside the desktop. Ooh, it looks even better when it's bigger. Reverting to an earlier version of a file and restoring a deleted file is not a built-in part of installed MATLAB. There are lots of third-party options for that, though. I use Dropbox Professional, which provides it. And believe me, it has saved me more than once. Okay, I'm going to clear things up. Let's make this a little bit smaller. And let's get rid of this bar showing downloaded files by clicking this X over here on the right. There. Now I can pull this down a little bit. Okay. So that's how you get earlier versions and undelete files in MATLAB Online. Okay, we just downloaded a file from the MATLAB Online cloud to my computer. Now let's upload one from my computer to the cloud. Nothing could be easier. First, I find the file I want in my Finder. Let's see here. Here's what I want, this JPEG file. I could use the Upload button up here, but I prefer to left-click the file, hold down the left button, and drag it over here to the current folder. And there it is. And maybe you'd like to see the picture in this file. Well, that's also easy with MATLAB. You can type the built-in function mshow and give it an input of the name of the file. Notice that I put the file name inside single quotes. Is it me, or is that a little small? Let's make it bigger. That's a little bit better. You can read all about making and displaying images with MATLAB in the textbook. Just look up image processing in the glossary and click the blue link at the bottom of the page. All this uploading and downloading can be automated. MathWorks provides a tool called the MATLAB Drive Connector that will continually synchronize the files in your MATLAB Drive with a folder on your computer. When you change something in one place, it's changed in the other. When you add a folder or a file or delete something, it happens in both places. You can find out how to get it done in the resource section of this course. Well, what have we learned in this video? Well, lots of stuff. We've learned how to use the folder and file system. We've learned how to write and run a function. And we learned how to use the command window, the workspace, and the command history. And these things are going to come in very handy in the next video. Well, as we gaze at this beautiful aqueduct in the south of France, and as we perhaps wish that we were there, or in my case, wish that I was back there again, we'll end this video, get in our time machine, and return to those early days in the fall of 2014 when I explained how you could use MATLAB as a calculator, a very powerful calculator. I'll see you 4 years ago. Okay, we know how to use the command window and the workspace and the command history. Now let's do a more interesting calculation. Let's calculate the number of kilometers in a light year, which is the distance that a light beam will travel in a year. The speed of light is equal to 300,000 kilometers per second, which we can put into a variable like this. A few notes about this variable. First, the KPS is there in the name to remind me that the units are kilometers per second. You can't include units when you assign a value to a variable. The value is just a number. Second, note that it's okay to use the underscore as part of a name in MATLAB. And third, if you look at the workspace up here, you'll see that speed KPS is listed above X and Y. That's because variables are listed in alphabetical order, not in the order that they're created. Okay, back to the calculation. To compute a light year in kilometers, we multiply the speed by the number of seconds in a year. First, let's put the number of seconds in a year into a variable. I'm going to call it year sec. And that's equal to the number of days in a year, which is 365. We'll forget about leap year. Times, and we use the asterisk for times, the number of hours in a day, which is 24, times the number of minutes in an hour, which is 60, times the number of seconds in a minute, which is also 60, and there's the number of seconds in a year. So, to calculate the light year, let's do this. Light year km, to remind me that this is kilometers, is equal to year sec times speed kps. And there you are. The answer, 9.4608e plus 12, might be a little mysterious. MATLAB has written the answer using scientific notation. The number after the letter E is the power of 10 that you multiply the part before the E by. So 9.4608e plus 12 is the same as 9.4608 times 1 trillion. Let's prove that by entering it the long way. So let's see here. 9.4608 times, see, a trillion is a 1 with 12 zeros. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There, sure enough, 9.4608e plus 12. Oh, and by the way, ands means answer. It's the variable that MATLAB creates to hold values that are typed in or calculated without being assigned to any other variable. And we can see it over here in the workspace. It's first because it starts with an A. Let's do one more calculation involving the speed of light. The distance from the Earth to the Sun is 149.6 times 10 to the 6 kilometers. Let's use our skill with scientific notation to assign that value to a variable. So Earth to Sun in kilometers is 150 times 10 to the 6th power. So how many minutes does it take light to get here from the Sun? That's what we want to calculate. First, let's calculate the number of seconds by dividing the distance in kilometers by the speed in kilometers per second, like this. There, it looks like it takes 500 seconds. And then we convert that to minutes by dividing by 60. .33333 minutes. Okay, we've got a lot of variables in our workspace. If we need to stop working and close MATLAB, it'd be a shame to lose them. You know, like if it's time to break for lunch or for dinner or for breakfast or whenever you do MATLAB. No problem. We can save them for when we come back later. We save them in a file simply by giving the command save, like this. There, it's all saved. And there's a message telling us where it was saved. What happened was MATLAB has copied everything in the workspace into a file called matlab.mat, and you can see it over here on the left. It just showed up. This file is called, imaginatively enough, a mat file. When we restart MATLAB, we can get all our variables back by copying them from that mat file into the workspace with a command called load. Let's prove it. First, let's clear out the workspace with the clear command. It's all gone. And just to make sure that we're not pulling some kind of trick because the assignment statements are in the command window, I'm going to clear that with the CLC command. I've used that once before. There, it's all clear. And if we try to check the value of the last variable we created, we'll get a red reprimand. Let's do that. Let's make a new variable called mini by assigning a value to it. Now we have just mini in the workspace. But we can get our other variables back with the load command. And there they all are. And note that mini is still there. Okay, let's take a minute or two to talk about MATLAB's rules for variable names. First of all, you've noticed that we can use underscore. We talked about that, in fact. And you can use uppercase. Mini is a great example. And speaking of uppercase, the uppercase can go anywhere. Let's make Mickey equal 9. And now I'm going to make a Mickey with a capital C in the middle. And I'll make him equal to 5. If you look over here in the workspace, you'll see these are two separate variables. The fact that this is a capital C makes this variable different from the one with the name that has only a lowercase c there. You can also have digits in the name. Let's try x45 equals 66, 7. And, well, but you can't have them just anywhere. There. You see red, so there's something wrong with that. And you can't have other characters. I mean, you can't have any characters other than letters. So if we did this, notice that's already red. Red's never good. So we'll try pound X. That's no good. $X equals 7. That doesn't work. And you can't start with an underscore. Well, already, there you go. You have to stick to the rules that the characters in a variable name can only be letters, underscores, or digits, and you have to start with a letter. And one last rule, the length is controlled. You can't have more than 63 characters. So if you're planning on having a variable that had 64 or more characters, I got bad news for you. You can't do it. But I have never come close to that. Maybe I've used 25 characters, but I doubt it. Okay, this desktop has gotten very cluttered. Let's clear the screen with CLC. We've used that before. By the way, CLC stands for Clear Command Window. The workspace is cluttered too. Let's get rid of that. Now, much better. And you can clear the history too. You just come down here and hit Clear Command History. It says, "Are you sure?" There. Now everything's nice and clear. And while we're on the subject of clutter, let's give a command. There. I'm imagining that I'm supposed to set the absolute value of 0 in centigrade, which I've done. And the value shows up here in the workspace. It also shows up here on the screen. MATLAB echoes the value that was assigned to the variable. Well, a lot of time we don't want to see that. We just want to assign it and have nothing happen. Let's do another assignment. What I'm doing is setting absolute 0 in Fahrenheit by using the formula. But this time I put a semicolon on the end. When I hit return, nothing's echoed back, but over here in the workspace, something actually happened. Just to emphasize that, let's do one more. Sticking with the temperature theme, I'm using paper ignition Fahrenheit equals 451. There. Again, the assignment took place, but there was not this echo over here cluttering up the screen. There's also another use for the semicolon. It'll allow you to put multiple commands on one line. Let me show you that. So I write x equals 42, then a semicolon, and then I just keep on typing and note enter. Now I'm going to hit the enter. Look over at the right. The command x equals 42 is executed. So is the command y equals 87. There's no echo. We had these semicolons, but also we separated the first command from the second command with the semicolon on the same line. You can put as many statements as you want on a line as long as you separate them with semicolons. Or you can substitute a comma for that purpose. Let's watch this. I'm going to put a comma here instead of a semicolon. Leave this part the same. We were able to do two different commands again, the same two commands. The only difference is this time we got the echo. So the semicolon is doing two things here. One, it's ending this command and allowing us to begin another one on the same line. And secondly, it's silencing MATLAB's echo. Here the comma ends one command and allows us to begin a second command on the same line, but it allows the echo. And not only can you have multiple commands on one line, you can have one command on multiple lines. Let me show you what I'm talking about. Let's use a really long variable name here. For some reason I just have these long variable names in my mind. So we've gotten to this point. And I want to multiply that times the other variable called another long one, but there just doesn't seem to be room here. So what I'm going to do is hit 3 dots. I don't know if you can see this. Let me magnify this a little bit. The dots turn blue. They're special. Those 3 dots, 3 periods, 3 full stops, whatever you like to call them, allows me to continue this one statement on the next line. So I'm going to hit enter. I'm down here. The blinker is still blinking. Nothing has happened. No error. No echo. And I'm going to type the rest of my command. There. It's as if we typed this whole thing from here, not counting these 3 dots, all the way to here on one line. And you can continue as many lines as you want if you keep using those 3 dots on each line, except, of course, the last one.
We've seen that MATLAB's pretty picky about its rules. Every programming language is. The reason is that strict rules make it easier to write accurate, unambiguous programs. We've violated MATLAB's rules several times, and we've seen those red error messages that they cause. There's a computer science term for this type of rule. The type of rule we've tripped over, it's called syntax. Syntax is a language's set of rules for the form of the statements, including, for example, the rule that says you can't use a hash symbol in a variable name. Here's another example.
1 equals x. Of course, MATLAB doesn't like that. As you can see, it says the expression to the left of the equal sign is not a valid target for an assignment. The simple form of this syntax rule, or syntactic rule, that we're violating is this. In an assignment statement, there must be a variable name on the left of the equal sign. We knew that, and we know that 1 is not a variable name.
We'll run into lots more syntax errors as we learn more rules, but there's another type of error that is much worse, the semantics error. As we said, the syntax of a command is its form. The semantics of a command is its meaning. An example of semantics is this.
Suppose we want to swap the values that are in x and y. First, note that the current value of x is 42 and the current value of y is 87. I've seen many new programmers try to do it like this. And by the way, I'm certain I did it too when I was starting out. So I type x equals y and y equals x. You see what went wrong here? Let's look up here and see that something did go wrong. They're both equal 87. Instead of having their values swapped, they both now have the value that y had before. So what happened? Well, the first statement, this one here, copied the 87 that was in y into x. And at this point, they both have the value 87. So x's value has just been lost. 42 is gone. Then this next statement just copies whatever's in x, which happens to be 87 now, back into y. So y is 87, it was 87, that really didn't do anything. Well, let's do it right. First, let's set things up the way they were to begin with. X was equal to 42, and y was equal to 87. And we can see that we've done that over here in the workspace. Now here's how you swap them. Temp equals x. We've copied x into temp. Temp stands for temporary variable. We've actually saved it there so that when we copy y into x, we haven't lost x's value. And now we simply copy temp into y. And there we go. So when we made the error, MATLAB didn't catch it, and it didn't print an error message, and there wasn't any red color. That's because our syntax was perfect. The problem is that our code didn't mean what we thought it did. This is a semantic error, also known as an error of semantics.
The semantics of our first try was that y's value was simply copied into x, that's all. It was a semantic error because we thought that x's value would also be copied into y. A semantic error is an error in which the meaning of our code is not what we intended. And the reason that it's worse than a syntactic error is that MATLAB has no way of knowing that it's an error. Neither would the other languages we've talked about. We could have made this particular error in any one of thousands of applications because swapping variables is a generic problem that occurs a lot. But an even more common type of semantic error is one that is application specific. Look, for example, at the formula we use for calculating absolute zero in degrees Fahrenheit. Right up here. It's correct, but suppose we typed this. Everything's the same, except that we used a minus instead of a plus. We would have gotten the wrong answer, but MATLAB wouldn't have known it, and it wouldn't have told us anything. Errors of semantics are the biggest problem in computer science by far, because the rules that they violate are unknown to the language we're using, so we get no help. Makes you kind of like those red error messages. Well, almost. MATLAB's trying to help us with these error messages, of course, but there's a lot more help easily available in MATLAB. It provides lots of commands like the who and whose commands that we use to look at the variables in a workspace, and the clear command that we used earlier to remove all the variables from the workspace. All these commands are executed by giving their names, and every one of them has something called a help page, which is roughly a page, more or less, of explanations of the syntax and the semantics of the command. We've seen that we can get information about MATLAB's built-in functions by typing their names into the search bar up here at the top. But there's a command that we can enter that will print what we need to know right here in the command window. The name of the command is help. You just type help followed by the name of the command you want to know about. Let's do that to find out about a command called format. Here we see the so-called help page for the command format, or I should say we see the bottom of the help page because this is a pretty long one. We can scroll to the top by using the scroll bar over at the right, or the mouse wheel, or your fingers on the touchpad, or however you like to do it. Every help page starts out by giving the command name, in this case format, and telling you in just a few words what the command does. So here we see set output format. This is followed by more detailed ways that you can use the command, and tells you what it does. You can read all about format later, but right now let's scroll down until we find format compact and format loose. Right here they are. You'll notice that compact and loose and these other options here are in uppercase, just to make them easier to spot when you sweep over this help page with your eyes. But you can use lower or uppercase with a command. Most people use lowercase. Let's see what these two options do. First, I'm going to set x equal to 5. Now let's use format loose. And I'll repeat the command. You see the difference? By loose, MATLAB means that spaces are inserted between the lines. I like a more compact output myself, so I always change the setting to compact, like this. Now we're back to normal, or what I call normal. If your particular MATLAB installation is set to loose, you may have been wondering why you're getting these spaces and I'm not. Now you know. And you might want to go with compact. Another thing that the format command can change for you is the number of decimal places that it shows when it prints a response to an assignment statement. We can scroll up and see these options. see here if I can find them. There they are. I've got MATLAB set to short, which says scaled fixed point format with 5 digits. Let's do another assignment statement. I'm going to do boy equals 117 divided by 19. There are an infinite number of digits in the exact answer. MATLAB shows 5 of them, 6.1579. Now let's try format long. And I'll repeat that command. Let's use the up arrow key to do that. Whoa, this time we've got lots of decimals. MATLAB is showing you all the accuracy it's got. It's important to know, though, that it works behind the scenes with all the accuracy it's got, whether you have the format set to long or short or anything else. All the command format affects is the printed output. You don't lose any accuracy during the calculations when the format is set to short. You just don't see all the accuracy in the output. I usually don't need to see all the accuracy, so I tend to stick with short. And that's what I'm going to do. And there we're back to 5 digits again. Let's see, before I went off on this format tangent, I was talking about the help command. And I wanted to tell you some other things about it. For example, if you want to see the fancy documentation with the fancy fonts that you get when you use the search bar up here, you can also get that with the command called doc. So let's try that with format. There, all this nice stuff shows up. It is pretty handy. We won't go into it, but we've seen it before and you can check it out. And there's another thing that we need to talk about. Suppose you don't know, the name of the command that you're looking for. You want to do plotting, for example. So you could come up here and type plotting and hit return, and well, you see this window and see, oh, this looks good. You see plotting basics. Click that. How to create 2D graph, add title, change limits. 2D graph, that might be good. Create a line graph, 2D. Oh, and here's some examples. It gives you a function. This is a workhorse function right here called plot xy. We're going to look at that in a minute. Shows you examples and so on. Now that you know plot is what you want, you can type help plot. And I'll scroll up here, and you'll see all kind of information about the plot command. It does a linear plot and so on. There's one other thing you can do. Let's go down here and look at this little thing. You probably not noticed this before. This FX with this tiny down arrow here. This is called Browse for Functions. Let's click on that. You see a little window show up here with some stuff. It says MATLAB, Language Fundamentals, Mathematics, Graphics. I'm looking for plotting. It looks promising. Whoa, there you go. 2D and 3D plots. I click there. Line plots. And there's this plot function that I mentioned, and here's some information about it right here. So this is another way for you to find information about a function when you don't even know its name. You just browse for it. Let me just bring up Chrome and type how do I plot in MATLAB. Well, 2D line plot, that looks promising. Let's see what we get there. And there we are. That's exactly what we wanted. You'll usually get not only the name of the appropriate function like this, but you'll be taken right to the help page that you need. MathWorks keeps all their documentation online, so it's available to everyone. And Google's search engine is so magical that, well, I usually wonder why I didn't just ask Google in the first place. Okay, let's Chrome here. And there we see, still waiting for us in the command window version of the help page for plot. No matter how you get the help page, if you scroll down here at the bottom, you usually find See Also list. Here's plot 3. I wonder what that is. Let's click that link. Plot lines and points in 3D space. That seems pretty cool. Let's suppose that that's sort of what I was looking for. The other thing I might do is look at an example. I find it's easier to be introduced to a subject by an example than theory anyway. That's really why this course is like that. Let's show you how easy it is to try an example. I'm going to copy this thing. Here's copy. Then I'm going to paste it into the command window. And it runs. That's the way all plots work. They pop up in a separate window called a figure. See here, figure 1. This plot does look three-dimensional. It's supposed to be a helix. But is it really 3D? Well, you can't use, the 3D glasses with it, but you can do something just as good. I'm going to click this little circle thing here and look at this. You can look at it from any angle. And that makes it pop out. Makes it look very 3D, to me anyway. By the way, if I click somewhere in this command window, this thing disappears. And if that happens to you, don't worry. It's back here. It just went to the back. You can always get it back that way. Okay, that was fun, but I'm going to close this. We're going to be a little less ambitious and go to 2D, because that's what you'll want 99% of the time. And let's plot just 3 points on an XY graph to get the idea. Okay, let's clear everything using clear and CLC. There. Now, the first thing we need to do to plot something is to specify the X and Y coordinates for the points we want to plot. And here's how we can do that. And the next thing we do is run the plot function, like this. And there's our plot. Before we go further, let me show you how you can keep this nice figure from disappearing back there behind the MATLAB desktop when you click in the command window. You just click this tiny arrow right here, and the figure suddenly shows up in its own little window right here in the MATLAB desktop. It's called docking the figure. Okay, let's see what we did to get this plot. Command window is just this little thing down here now. And we can see the first command, set the variable x coordinates equal to a list of 3 values, 1, 3, and 10. Well, let's stop right there. A variable has 3 values at the same time? Well, actually, x coordinates has just 1 value. It's this whole thing here. Its 1 value is a vector. And we get a vector by typing these left brackets and right brackets. We'll go into detail on that later. But a vector is just an ordered list of numbers, 1, 3, 10 in this case. Those numbers are called the elements of the vector. We did the same thing for the y coordinates. And here's the first point. X equals 1. X is plotted along the horizontal axis. And y equals 2. There's the 2. Then there's a line drawn to the second point. You can see that x is equal to 3. And y looks like it's probably equal to about 4.2. And here's the last point. X equals 10, y equals 12.3. When we typed x coordinates and y coordinates in parentheses after the function name plot, it meant that the values in those variables were inputs to the function. Inputs to a function are called input arguments in programming, or just arguments. Plot expects to get 2 vectors as input, and they have to have the same number of elements, 3 in this case. In MATLAB terminology, the number of elements of a vector is called its length. For you physicists out there, the length of a vector is the square root of the sum of the squares of the elements. And there's a MATLAB function called norm that will give that to you. But to get the number of elements in the vector, you use a MATLAB function named length, like this. So the value of the variable x-coordinates is a vector of length 3 whose elements are 1, 3, and 10. When we entered those elements, you may have noticed all those commas. Before now, the comma had been used only to separate two commands on the same line. Now we see a second use, separating elements in a vector here and here, and a third use, separating the arguments to a function here in our call the plot function. The plot function gave us a nice plot, but to tell the truth, it's not quite what I wanted. Instead of this jagged blue line going from point to point, I wanted to plot each point separately. Well, the plot function will do that for us if we know how to tell it to. We do that by giving it a third argument. Let's call it again, but slow down a bit as we type. P-L-O-T, left paren. After that first parenthesis, this thing pops up. It's called a hint, and it reminds you of the various arguments that you can feed it. I say reminds you because you really need to know how it works for the hint to be much help. I happen to know that the third argument here, this second option, called line spec, is the so-called line specification argument, and you use it to tell plot how to plot your points. Let's do it this way. This quote asterisk quote tells plot to put an asterisk at each one of the points instead of a line connecting them. So now I'm going to hit enter. And there we go. Here's a point here, here's a point here, and there's one there. An asterisk usually means multiply, but this asterisk has single quotes around it, as you can see, and that changes its meaning. A single set of quotes around characters tells MATLAB not to treat those characters as the name of an operation or a variable or a function. Instead, it treats the characters between the quotes as just a string of, well, characters. And it's in fact called a string. To remind you that it's a string, MATLAB highlights it in that purplish pink color that we saw before. Or would you call that lavender? And speaking of color, let's alter our plot by changing the color and, while we're at it, the shape of the points that we're plotting. Let's go back to the help page to see how to do that. I'm going to use the doc command because I have so little space in my tiny command window with this figure taking all this space. Doc plot. Here we go. Two-line plot. What I'm looking for is something about line spec. Oh, here we go. Line spec. Let's see. I can specify a solid line by using a minus. These are the things that go in those little quotes instead of the asterisk. Here's a dashed line and so on. The marker I'm looking for is a square. There we go, square. So I use an S for that. And what about the color? Oh, here's the colors. Yellow, magenta, well, red is an R. Okay, so now I know what to do. What I'm going to do, hit the up arrow key to repeat this command. I'm going to go up to there. And I'm going to alter this by putting in, what did we decide? Red square. You can put an RS or an SR, it doesn't make any difference. Now watch these little asterisks, these blue asterisks, change into red squares when I hit return. 4, 3, 2, 1, there. And there you have it. There's those little red squares. There's other ways to enhance these plots too. For example, we can add a grid with the grid on command. There we have a nice grid. And you can probably guess that you can turn it off with the grid off command, but we're going to leave it on. And we can add labels to the axes like this. Let's add one to the x-axis. X label. Let's just make up something. Say selection. See, that shows up right away when we hit selection. And Y label. That's going to be change. There's our Y label. And what about a nice title for this thing? Title is the name of that command. Changes in selections during the past year. And there it is. Here we've got three more functions that use strings as arguments. We've seen plot puts a string here, and there's a string, there's a string, there's a string, just a string of characters. And they're all colored this color, whatever it is. And it's the same color that's used here and used here when you give arguments to the doc, the grid, and other commands. MATLAB automatically chose the ranges in this plot. It chose 1 to 10 for x, the horizontal axis, and -6 to 14 for the vertical axis. But you can change these ranges with the axis command. Let's do that. Before I hit enter, I'm going to talk about what we've done here. Axis takes a 4-element vector, 1, 2, 3, 4 elements. The first element is the left end of the horizontal axis. That's going to become 0. The right end is going to be 12. The bottom end of the vertical axis is next. That's going to be -10. And then the upper axis limit is going to be 20. So watch this. I'll hit return. You'll see these change. So now we go from 0 to 12 and -10 to 20. Just what we asked for. Well, that's about it for plot. There are other plotting functions too. There's one called bar, which produces bar graphs. Let's try that next. Note that the bar graph replaced the previous plot. And we see here at the positions of x, 1, 3, and 10, the heights of the bar match the y values, 2, -4.2, and 12.3. If you don't want the second plot, the bar, for example, to replace the first plot that you were looking at in the figure, you can ask for a second figure. You type figure, like this, and it gives you a new figure. Let's put something in that figure. I'm going to dock it. And what I'm going to do is put a pie chart in there using the function called pi. Pi takes one vector as an argument. I'm just going to make one up. Note that we separated the elements of this vector with spaces instead of commas. Yep, you can use spaces or commas or both. Each element in the input vector, the 4, the 2, the 7, the 4, and the 7, determine the size of one slice of pie. So now I'm going to hit enter and see what we get. I'm going to pick some colors for each slice, and it calculates the percentages of the sizes of each slice relative to the whole and shows them for each slice. And there you go. To close a figure window, you can use the close command. To close figure 2, you use close 2. And that leaves us with figure 1. We could close figure 1 with close 1, but you can always close all the open figures with close all. So I want to show you that one. And there, we're back to no figures. Before we finish looking at figures, let's put up one last one. This time we're going to display a photo. Over in the current folder window here, we see that there's a file named palace.jpg. You're probably familiar with this. JPG means that this file contains a photograph stored in a very common format. It's called the JPEG format. So the first thing we need to do is load this photo that's in this file into MATLAB, and we can do that with a command called mread. So I'm going to type that in. And the argument I give it is the name of the file in quotes, like this. You have to use uppercase where there's uppercase in the file name. And so now I'm going to hit return. And okay, not good. We need to stop this. It doesn't hurt anything, but it won't stop for a couple of minutes. And we don't have time for that. Do you remember how to stop MATLAB? Control-C. We press the Control key. While we're holding that down, press the C key. There. That's over. What happened is that the mread command found the file, read the numbers inside it just like we wanted it to, but then it poured those numbers out into the command window, and there are a lot of numbers in there, over 47 million of them. What we should have done is tell MATLAB to assign the output of mread into a variable instead of pouring it onto the screen. We should have used an assignment statement like this. I'm going to assign it to a variable called pretty picture. Sheesh, are we ever going to get this right? Control-C again. This time we forgot to put a semicolon at the end of the line. So after it stored the data in the variable pretty picture, and we can see up here that it did that, there's a lot of data there. 3,456 by 4,000 times 3, that's a lot of numbers up there. We'll learn what all this means in the next lesson. But what we should have done was put that semicolon in. Let's do that and repeat the command. Okay, 3's the charm. The picture is captured in the variable pretty picture, but we haven't seen it yet. So how do we look at it? Well, we can do that with a function named image, like this. It is a pretty picture, but we don't need those numbers on the edges cluttering it up. Let me dock this thing, and I'm going to give a command called axis off. There. Much better. MATLAB can display images in lots of formats in addition to JPEG, and it allows us to do image processing on all of them too. We'll look at that in a later lesson, but now let's end lesson 1 and let's quit MATLAB while we admire this photograph. It is beautiful, isn't it? I'd tell you who shot it, but modesty forbids me. Okay, to quit, we give the quit command. Here we go. Q-U-I-T, return. MATLAB is gone, and we're back to our computer desktop where we started from.
We could also have quit by just closing the MATLAB desktop by clicking the little X in the upper corner, but in either case, the desktop closes and all the figures close as well. When MATLAB leaves, it puts everything away. And it's time for us to leave too. That's the end of lesson 1. Hi, welcome to Lesson 2, Matrices and Operators. As we pointed out in Lesson 1, MATLAB is designed not only to make it easy to program a computer, but also to make it easy to solve numerical problems. Numerical problems often involve operating on matrices, and MATLAB makes that easy. We're going to start this lesson by finding out what matrices are. Matrices, which is the plural of the word matrix, are special kinds of arrays. So what are they? Well, both concepts are pretty simple, really. First of all, an array is just a set of numbers arranged in a rectangular pattern. So imagine a piece of paper with rows of numbers written on it, like this one. This is a two-dimensional array. Numbers are called elements of the array, and each row must have the same number of elements as each of the other rows.
In this case, we have 6 rows of 4 elements. We call this a 6 by 4 array. As you can see, it has 6 rows and 4 columns. And we always say the number of rows before we say the number of columns. Now imagine having a stack of 2 such pages, each with the same dimensions, but not necessarily the same numbers. We'll use the same 2-dimensional array that we started with for one page, and we add a second page with the same layout as the first one, that is 6 rows and 4 columns. Now we have a 3-dimensional array. Its dimensions are 6 by 4 by 2, which means 6 rows, 4 columns, and 2 pages. We always say the number of pages after the number of columns, just as we always say the number of columns after the number of rows. Now let's add a third page with the same layout as each of the other 2 pages. This is still a 3-dimensional array. We've just changed the dimensions. This one is 6 by 4 by 3, which means 6 rows, 4 columns, and 3 pages. Arrays of 4 dimensions and higher are rare. We won't use them in this course. And the most common are the 2-dimensional arrays. In fact, they're so common they have a special name. A 2-dimensional array is also called a matrix, and that's what we call it. And if there's only one row in the matrix or only one column, in other words, it's only one-dimensional, the matrix is also called a vector. The most ingenious part of MATLAB is the way Moeller set it up to deal with matrices, and because of the special role that matrices play in MATLAB, he gave his language a name that stands for Matrix Laboratory. Okay, let's look at some matrices in MATLAB. Before we look at a matrix, let's remember what we did in Lesson 1 when we were doing plotting. We actually made a vector called x values, and we did it this way. We used a left and right bracket to mean that we wanted a vector, in this case of 3 values. We're going to use those same brackets to make a 2-dimensional array, and here's how we'll do it. I'm going to use capital X this time. Here's my left bracket, 0, 1, minus 1. This time I'm going to put a semicolon. That means end of a row. I want to put another row. It has to have the same number of elements. Pi 100. Right bracket means the end of the matrix. And what we see here is we have a 2 by 3 matrix. First row is 0, 1, minus 1. Second row is 2.5, 3.1416, and 100. Let me say a word about the 3.1416. We actually typed pi here, and as you probably guessed, pi means the ratio of the circumference of a circle to its diameter. You might think that pi is some kind of built-in variable. It's not. It's a built-in function. As you'll remember from Lesson 1, a function is just an operation that's invoked by giving its name. And we had examples there of clear, plot, title, axis. These were functions that did things to the screen. Pi is a little different. What it does is return a value, the ratio of the circumference to the diameter of a circle. It actually returns a lot more decimals than we're seeing here. The format we have set up only shows 1, 2, 3, 4, 5 digits, as you can see. So pi returns a value. And when we say it returns a value, we simply mean that the program inserts the value where the function name appears. As you can see, function name appeared in the middle of the second row, and so the value appears in the middle of the second row. MATLAB provides hundreds of built-in functions. Here's one called squirt. Actually means square root. MATLAB loves short names. And you can see when we hit return that we get the value 1.4142, which is the square root of 2. Of course, both of these numbers, pi and square root, are irrational numbers, so these digits would go on forever. MATLAB stores about 15 of them, and it's showing you just a few. Here's another function, sine of 30. Sine, like square root, takes an input value. Pi takes no input value. Some functions do, some don't. You might think this is sine of 30 degrees. It's actually the sine of 30 radians. If you want the sine of 30 degrees, you can do it this way. sine D looks like send, and that's the sine of 30 degrees. Here's another function, size. I'm going to give it an argument, x. It says 2, 3. What this means is x is a 2 by 3 matrix. The job of size in life is simply to give the dimensions of the matrix that you give it in parentheses. Let's try this with another value. Let's make x equal 5. And let's do the size of x. Now, x is just a simple number, and since size is supposed to give you the dimensions of a matrix, and x clearly is not a matrix, it's probably going to give an error, one of those red messages. Well, no, it doesn't. In fact, it gives us that x has the dimensions 1 by 1. And here we see that MATLAB looks at everything as a matrix. This is one of the ingenious ideas that Cleve Moeller had to begin with MATLAB. A scalar is simply a 1 by 1 matrix in the eyes of MATLAB. You notice that we used a lowercase x for this 1 by 1 matrix. It's commonly called in mathematics a scalar, and it's common to use lowercase as the initial value or initial letter in the name of a vector, as we can see from x values up here at the top of the screen, and x, as we did here for the scalar. And we used a capital X for a two-dimensional array. MATLAB knows nothing about that. It's just a custom. You might say, and maybe we want an array of voltages. Let's give it 1, 2, 3, 4, 5, 6. I'm in a hurry. I don't want to come up with any fancy values. So there's a 3 by 3 array of voltages. If we wanted to say what the first row was, we might say row 1, and I'll use an underscore to make this clear, of voltages equals, well, 1, 2, 3. And I used a lowercase r because this is, after all, a vector. Well, let's look at a vector a little bit more closely. Let's set x equal to 1, 4, 7. This is a row vector. Let's look at a column vector. I'm going to set y equal to 1 semicolon 4 semicolon 7. Since semicolon means the end of a row, we've got a row of only one element, another row of only one element, and a third row of only one element. And as you can see, row 1 is one element, 4 on the second row, 7. So this is a column vector, and MATLAB lays it out as a column vector when it echoes back the value of y. So let's look at the size of x and the size of y. For x, we have a 1 by 3. That means one row, 3 columns. For y, we have a size of 3 by 1. 3 rows, 1 column. X is a row vector, y is a column vector. MATLAB doesn't use these names. We use the names, but MATLAB shows you that it's a vector by showing you that the size has the number 1 in it somewhere. A vector is simply a matrix, one of whose dimensions is 1. And a scalar is a vector. It's a matrix, both of whose dimensions are equal to 1.
Let's look at a picture from the book that shows the relationships among all these types of arrays. Here we see all 4 types, the arrays, the matrices, the vectors, and the scalars. First, we highlight the set of all arrays. This is the biggest set, and it includes all numbers of dimensions, 1, 2, 3, 4, and on and on. In particular, it includes as subsets the special types of arrays, the ones with other names. Here are the matrices. You can call these matrices or arrays, and inside the matrices are the vectors. This set includes all row vectors and all column vectors, and you can call them vectors or matrices or arrays, but we usually call them vectors. And finally, inside the set of vectors are the scalars. These are the 1 by 1 matrices, and you can call them scalars or vectors or matrices or arrays, but we usually just call them numbers.
Everything that MATLAB works with, from the largest to the smallest, is found in this diagram. And on the subject of size, now we're going to see how you can create a very long vector without a lot of typing by using the colon operator. To see how the colon operator works, let's start with a simple example. X equals 1 colon 3 colon 7. I hit return and I get 147. X is a vector. Here's what the meaning of this colon operator is. And notice we've got 2 colons in the so-called colon operator. It means start at 1, increase by steps of 3, and stop before you go over 7. Go no higher than 7. So we add 3 plus 1, we get 4. We add 3 to that, we get 7. If we added 3 to that, well, it would be over 7. This concept of incrementing and going no higher than a limit sometimes is confusing. Let's look at 1, 3, 8. We start with 1, we add 3, and we continue, but we go no higher than 8. Well, we got the same result here. Because if we added 3 to 7, we would be higher than 8. So it stops at 7. Let's try this one. Still no joy. Let's try this one. We want to get another number. Nothing's happening because if we added 3 to 7, we'd be higher than 9.9. So finally, let's do this. 1, 3, 10. This starts at 1. We add 3 and get 4. We add 3 and get 7. We add 3 and get 10. MATLAB checks. If you add 3 to 10, would you be higher than 10? Well, of course, so it stops. There's a special shorthand if you want to go up by 1 instead of, say, 3. Let's call this variable ints. We'll set it 1 to 100. This is the same as going up by 1. Just 1 colon is needed. And, well, we get 100 numbers here. Let's look at the size of this variable. It's a 1 by 100 vector, as you can probably see. So we call this the colon operator. Well, what's the definition of an operator? Pretty simple. You've seen a function. An operator is a function that's invoked by a symbol. A function is an operation that's invoked by the name. So the name of this special kind of function is a single symbol, or 2 symbols, as in the case of 2 colons here. Plus and minus are probably the most familiar examples. Let's look at 1 plus 2. Of course, we get 3. There's another function that does the same thing in MATLAB, plus 1, 2. The first one is an operator. The second one is a function. They're both called plus. One's a word, one's a symbol. There's a colon function that does the same thing. As this. So the first one is the name colon. The second one is the colon symbol. As you learned in lesson 1, we call the inputs to a function call arguments. For an operator, we call them operands. For a function, the arguments are surrounded by parentheses and separated by commas. For operators, the inputs are separated by the operators themselves. For example, 1 plus 2. The plus separates the 2 operands, 1 and 2. If you had multiplication, 10 times 20, the operands are 10 and 20. They're separated by the operator asterisk. And of course, here we have 1 and 7 separated by the colon. And you can even have 2 symbols in the colon operator, so we can separate 3 operands with the 2 colons. The colon operator is very useful for generating huge vectors of equally spaced numbers. Suppose we wanted all the odd numbers smaller than 1,000, starting with 1. We might set z equal to 1, colon 2, colon 1,000. Before I hit return, fill the screen, notice that we're going to start at 1, then we're going to add 2, that'll give us 3. Then we add 2 to that, that'll give us 5, 1, 3, 5, 7, and so on, all the way up to, but as you know, since 1,000 is not reachable as an odd number, it doesn't quite include 1,000. So we go to 999. If we added 2 to 999, we get 1,001, which would be greater than 1,000, and MATLAB won't do that. Let's look at the size of Z. It's 1 by 500. There are 500 odd numbers from 1 to 999. Suppose we wanted the even numbers that are smaller than or equal to 500. Let's call those evens, and we'll set them to 2, 500. We start with 2. We keep adding 2 till we get to 500. 2, 4, 6, 8. And there are those numbers. What's the size of that vector? Well, it's 1 by 250. You can have decreasing sequences too. Let's start with 7, go down by 3, and end up at 1. 7, 4, 1. So we start with 7. We subtract 3, that gives us 4. We subtract 3 again, that gives us 1. If we subtracted 3 again, we would be less than 1. So the rule now is, instead of go no higher, it's go no lower. So we go no lower than 1. Let's look at one we'll call down by 10. It's equal to 100 colon minus 10 colon minus 100. So here we start at 100. We decrease by 10. We add minus 10, in other words, until we get to, and don't go below, minus 100. And there's the numbers. Size of this is 1 by 21. Again, it's a vector. You always get row vectors with the colon operator. You never get a column vector. If you want a column vector, you have to change it into a column vector, and we'll show you how to do that later. I want to show you a strange thing. X equals 7 colon 3 colon 1. So innocently, I type 7 colon 3 colon 1, meaning I want to start with 7. I want to change by 3 until I get down to 1. I hit return, and I get this strange thing. X is the empty matrix, 1 by 0. Well, what's the difference? Last time I typed 7. Well, here I had a minus 3. Here I have a plus 3. And there's the problem. I want all the numbers that start at 7, get bigger by 3, and end up at 1. Well, there is no such number or numbers. So it gives us the empty matrix. Let's see what the size of X is. 1 by 0, just as it said. There are other sizes of empty matrices in MATLAB. And by empty matrix, we don't mean a matrix with zeros in it. We mean a matrix with nothing in it. Here's how to get that other kind. You just type nothing. So we typed X, a left bracket, type nothing, and then type the right bracket. And it shows that it's an empty matrix. It shows it a little differently here. Let's look at the size of X. This time X is 0 by 0. Before it had one row with nothing on it. You always get a row matrix, as I mentioned, with the colon operator. And sure enough, we got a row matrix here with nothing in it. One row, no elements. Here, we didn't indicate whether we wanted one row of nothing or one column of nothing, so it gives us no rows, no elements.
Now that we know how to make a matrix, we need to know how to access parts of it. So for example, if we want to see just the one element on the second row and the third column, we'll know how to do it. And it's all based on rows and columns. To see how it's done, we need a sample matrix. This command will make us one. And here it is. As you can see, its dimensions are 3 by 4, meaning that it has 3 rows and 4 columns. And they're numbered from top to bottom, 1, 2, 3. And the columns are numbered too, 1, 2, 3, 4,
from left to right. So how do you look at just the element on the second row in the third column? You give the command x, left parenthesis, 2, comma, 3, right parenthesis. The 2 is the row index, and the 3 is the column index. As always, the row comes before the column. Together, the two indices, 2 and 3, in parentheses and separated by commas, tell MATLAB which element you want to see. And it shows it to you. Okay, let's do this same example again, but this time let's do it in MATLAB. Okay, well, let's look at this same example in MATLAB. We said x equal to left bracket 1 colon 4 semicolon 5 colon 8 semicolon 9 colon 12 right bracket. Note how we've used the colon operator to save typing. We could have done it the hard way, which would have been x equals 1, 2, 3, 4, 5, 6, etc. I'm not even going to do that. It's just too much work, but the colon operator works perfectly. Each row of a matrix is simply a vector of numbers, and the colon operator produces a row vector of evenly spaced numbers. So if we want the numbers on a row to be evenly spaced, we can use the colon operator instead of typing them out, and that's what we wanted this time. So we use the colon operator. Okay, to continue with our example, let's specify the third element on the second row as we did before. So we say x, parenthesis now, 2, 3, right parenthesis, and we see the answer is 7. We always, as here we did, give the row index first and the column index second. We can also use this notation in an assignment operator. So let's say we want to call the variable center, and we set it equal to x 2, 3 as we did before. Center now has the value 7. Or Bob, I don't know, x 3, 3. There we go. Bob is 11. And as you can see up here where x was displayed, this 3 by 4 matrix, on the third row, and here's the 3 down here, in the third column, and here's the second 3, we find the 11. And we can assign a new value to a specified element, x 2, 3, instead of being 7, I'd like it to be 97. So we set it to 97. You'll notice that while we only mentioned to MATLAB one element, it shows us the whole matrix. Well, we will notice, however, that it did make the change we requested. So element 2, 3, that is second row, third column, is now 97. And if we wanted the second row, second column to be, 123. If we look at it now, it's 123. So what happens if we assign a value to an element of a matrix, but the matrix doesn't exist? Let's say, for example, a matrix XYZ. If we look over here in the workspace, we'll see there's no XYZ matrix, so it doesn't exist yet. Another way to check to see if it exists is to try to look at it. We get one of those awful red messages saying we made some kind of error. Okay, MATLAB, I did this on purpose. It's not really an error this time. But anyway, let's set a value to it. X, Y, Z, element 2, 2 is equal to 123. So we're doing the same thing we did with X, but now we're doing it with a non-existent matrix. So you expect some more red to come back, I'm sure. Well, surprise. What is this? XYZ equals 0, 0, 0, 1, 2, 3. Well, here's what MATLAB did. It said you want to have a matrix XYZ and you want to have 123 on row 2, column 2. I'll give that to you. You didn't tell me what goes on the rest of the rows and columns, so I'll put zeros there. And that's what MATLAB does. It makes the smallest matrix it can and still accommodate your request. In other words, the smallest matrix it can that has an element 2, 2, and that's a 2 by 2 matrix. And what happens if the matrix exists, but the element we specify doesn't exist? Let's try to peek at a non-existent element. Let's look at the element of the 3 by 4 matrix that's on the 4th row and the 5th column. That doesn't exist. Well, we get our hands slapped and we deserve it. But an assignment to a non-existing position like this is another thing entirely. Let's assign a value to element 4, 5, say 456. So what's this? Well, MATLAB has had to extend the size of the matrix from 3 by 4 to 4 by 5 to accommodate our request to put something at element 4, 5, the 456. There it is. It's right there. We didn't tell it what else to put on the 4th row, and we didn't tell it what else to put on the 5th column, so it puts zeros there. There's one pitfall we need to point out concerning the first element on the first row. Let's set that first element on the first row to the value 99. It's 1 right now. We'll change it to 99 there. So we see our matrix with the 99 replacing the 1. That works fine. You might be tempted to do this because we've talked about how x as a scalar is the same as a 1 by 1 matrix, and it kind of looks like the same meaning here, but it's not. It's entirely different. What we have just done is obliterated our entire matrix and replaced it with just the 1 by 1 scalar matrix, 99. Well, we know how to access or change individual matrix elements, but you know we can change multiple elements at a time using the so-called subarray operations. Let's see how that works. Let's come up with a little simpler matrix this time. Just 2 rows. One of my favorite matrices because it's so easy to type. 1, 2, 3, 4, 5, 6. Let's look at a subarray. I'm going to type x, 2, comma, then 1, 3. What I've done here is said that I'm interested in just the second row, and I'm interested in the first and the third columns. I want to see that. So MATLAB slices off that second row, and it gives me the first and the third element on the row, and there they are, 4, 6. This is a subarray. This is the whole array, and this 4 and this 6 taken together is the subarray that we've specified. The comma is required, by the way, this one I'm talking about. Let's try doing without it. We get an error. And it's just as easy to specify multiple rows as multiple columns. So here we go. I'm going to say I want row 2 first and then row 1. And I just want to look at column 2. Now let's go back and look at what x is. It's still visible up here. We've asked for row 2 first, and there's the 5, and then row 1, and there's the 2. We asked for the second column each case. So it puts the 5 first and then the 2. And here's a combination of multiple rows and multiple columns. For my rows, I'm going to say I want row 2 first, and then row 1, and then row 2. And then for the columns, I want to start with 3, and then go to 1, and then 1 again, and then 2. You can do anything you want to, as long as you're picking elements that are actually inside the array. So let's just look briefly here. We took row 2 first, and row 2 had a 4, a 5, and a 6 on it. And we asked for columns 3, and then 1 twice, and then 2. So here, the 6, the 4 is repeated because we asked for it twice, and then the 5, and then you can see what happened with the other rows. You can do any combination you want as long as the elements you request exist in X. Let me give an up arrow to repeat the previous command, and I'm going to change that 2 to an 8 and hit enter. Well, MATLAB didn't like that because we asked for elements that didn't exist inside X. And you can use the colon operator to form a subarray. As an illustration, let's do this without the colon operator. Spacing this out so you can see a little better. But we can do the same result with the colon operator. Let's do it that way. Instead of this 1, 2, 3 vector, which I wrote out explicitly, this time I'm going to get the same thing with the colon operator. This is not really a new concept. It's just a combination of two concepts that you've already learned. First, you learned that a vector like 1, 2, 3 can be used in a subarray operation. And second, you learned that the colon operator can produce a vector of evenly spaced numbers. In this case, 1, 2, 3. And you can get as fancy as you want with this. For example, let's do this. We'll put 2 colon minus 1 colon 1 for the rows we want, and for the columns, 3 colon minus 1 colon 1. We're going backwards on both of them. And there you have it. MATLAB provides a very helpful way for specifying the last index of a row or a column. Here's an example. As you might guess, the word end here means the last row index in the matrix X. And here's how you ask for the last column index. I'm sure you can guess. You just put end in the column position. End is an example of a keyword in MATLAB. The term keyword is a computer science term, and it's used for all programming languages. Its definition is simply a word that has a special meaning in the language. And every programming language has keywords. Here, the special meaning of this keyword is last index. A keyword is also typically reserved, meaning that you can't use it as the name of a variable or a function. Let's try to do that. We'll set end equal to 5. Oops. As you can see, MATLAB says it's a reserved word. The keyword end may not seem all that helpful to you right now, but we'll see later that it's very helpful when we write a program in which we can't know what the last index is. That actually happens a lot. And when it does, end will always give it to us. Here's some more examples of end. You can even do it in both positions. And here's 2 and 1 and 3. So we pick the second, last, the first, and then the last element again on the third column. And you might be surprised to find that end can be used in arithmetic expressions. Subtraction's the most common. Let's do one of those. Let's remind ourselves what x is now. It's 1, 2, 3, 4, 5, 6. So here we go. 1 and minus 1. So this means we want to be on the first row. And instead of the last element, we want 1 before the last element. N minus 1 means end, which is the index 3, minus 1, which gives us the one before that, 2. And here's another one. And finally, if you want the last 2 elements of the first row, in reverse order, you get them. Addition is a little bit less common with end, and it'll cause an error if you're using it to look beyond the end of a matrix, or trying to, like say this. But it's perfectly legal in an assignment operation, like say this. Notice that X has gotten bigger. Up here we see it was 1, 2, 3, 4, 5, 6, 2 rows, 3 columns. Now it's 1, 2, 3, 4, 5, 6, 17, 0, 0. When we put end plus 1, we said we wanted to put 17 on the third row. Well, there wasn't a third row, so MATLAB added one. We told it what to put in the first column. We didn't tell it what to put in the other 2 columns. So as usual, it guesses that we want zeros there. And can also be used with the colon operator. Here's some examples of that. Let's see what we've done here. We want row 1 here, and we want to start column 1, jump by 2 until we get to the end. Well, row 1 has a 1, 2, and a 3. We jump over that 2 and we get a 3. 1, 3. Here we want the third row, and here's the third row, and we want to start at the end and go backwards to 2. 0, 0, and there's the 0, 0. And in this last one, we want row 1. Here's row 1. We want to start not at the end, but at one short of the end. That's here. And go to the end. 2, 3. And so you see that we have a 2, 3 here. Well, MATLAB also provides a shorthand for one particular phrase. 1 colon end. Let's start first of all by putting 1 colon end. 2. 2, 5, 0. We want to go from the first row to the last row, and we want to stick on column 2, and here it is. Let's look at this. Instead of 1 colon end, I just put colon and then the 2. And it's the same thing. The colon stands for 1 colon end. It's a shorthand. And of course, it's the same with the column indices. So we could do this. And that means we want row 1 and then all the elements on that row. 1, 2, 3. And of course, you can use it in both positions. We want all the rows and all the columns. But that's just the same as X. So this isn't a shorthand. It's more like a longhand. And of course, this is even longer. But all 3 of these things give us the same thing. But the point here is that MATLAB opts for consistency, which means it always lets you use these expressions for any index with no exceptions. This emphasis on consistency is a hallmark of a good programming language, and all the programming languages that are in heavy use today, including C, C++, and Java, and even good old Fortran, all emphasize it too. Well, so far we've used the array operations just to look at elements inside a matrix, but you can also use them to change the values of elements inside a matrix. Let's look at an example of that. I'm going to give the subarray 1 to end and 1. And if we look at that, we see that's elements 1, 4, and 17 there on the first column. If I give this operation, which is an assignment operation, we see that we have assigned minus 44 to every one of the elements in that subarray. In other words, the whole first column. And you'll notice that, as usual, we get to see the whole array when we do a subarray operation. Here's another one. Now what we've done is told MATLAB that we're interested in all the rows and we're interested in columns 2 and 3. And we want to set all those elements each to the value of 9. Arrays can be on the right side too. Let me show you what I'm talking about with an example. I'm going to type the same left side that I just typed. On the right side, I'm going to specify an array. There, you can see what's happened. The array that I specified on the right side just fits exactly into the subarray that I specified on the left side, and so MATLAB has dutifully put it there. And the size on the right side has to match that on the left side. It's a rule. Let's try to violate that rule and see what happens. Here on the left side, I'm putting exactly the same thing that I did before. But on the right side, I'm giving just a row vector, and that's not the same shape. And MATLAB complains.
Well, we've learned how to change a matrix. Now we're going to learn how to combine matrices to make a new matrix. First of all, we're going to explain what the combination of matrices means. We've got an example here of two matrices, A and B. You can see them there. And here is a matrix C, which is the combination of A and B. C has A in its upper left corner, B in its upper right corner, another copy of B in its lower left corner, and another copy of A in its lower right corner. And here's what it looks like. To make this a little easier to understand, let's highlight 1, 2, 3, 4, 5, 6 in C in red, and that's A. A shows up in the left-hand corner. And in the right-hand corner, outlined in green, we see B. And then there's another copy of B at the bottom left and another copy of A at the bottom right. So now let's see how to do this in MATLAB. We need to ask MATLAB to make the matrices that we're going to combine. But first, let's start with a clean slate by clearing our workspace. There, as you can see, variables are gone, and clearing our screen. There, nice, clean, tidy screen. Now we'll get those matrices. We're going to call them A1, A2, and A3. We've made these matrices have the same number of rows and the same number of columns. And because of that, we can put them side by side or we can stack them. Let's put them side by side. There. And let's stack them. And there we have that. Easy. But the only requirement for side-by-sideness is that they have the same number of rows. Let's prove that by making three matrices that each have 2 rows but different numbers of columns. We'll call these B's. B1 equals 1 colon 1. B2 equals 2, 2, 2, 2. And B3, 3, 3, 3, 3, 3, 3. Let's look at these. We'll notice that B1 has 2 rows. B2 has 2 rows, but it has 2 columns. And B3 has 2 rows, but it has 3 columns. Now let's see if we can put these things on the same row. Yep. And let's do a little more complicated. Put them all there. And we can repeat them if we want to. And there you have it. But we can't stack them. Let's try to do that.
MATLAB gets mad about that. It won't let you do that because the result wouldn't be rectangular. And arrays, as you know, matrices, have to be rectangular. You might be wondering about the strange word vertcat that popped out of nowhere. That's the name of a built-in function. And as we've learned before, with the plus operation and the colon operation, MATLAB uses functions to carry out operations behind the scene. Vertcat, which means vertical catenation, just happens to be the function that it uses to stack matrices. Okay, the rule for stacking matrices is that the matrices all have to have the same number of columns. You might expect us to show you an example of that, but we're going to invite you to come up with your own examples to demonstrate the stacking rule.
Okay, we've seen how to combine matrices. Now we're going to change a matrix that we already have. We're going to transform it using the transposition operator. Here's an example of a matrix H. It's a 2 by 3 matrix, as you can see over there on the right. And what we're going to do is assign H prime to G. That little character, let me make it even bigger. Right there, that little thing there. Looks like a single quote. In mathematics, it's usually called the prime symbol. That is the transposition operator in MATLAB. And so what does it do? Well, look at G. First thing you notice, instead of being 2 by 3, G is 3 by 2. Then you may notice that the first row of H is now the first column of G. Second row of H is now the second column of G. It changes rows into columns. And when it does that, of course, the columns become rows. So the first column of H is the first row of G. The second column of H is the second row of G. And the same thing happens with the third column. Furthermore, the indices are swapped for each element in the matrix. By that, what I mean is, you look at that 2 in the top. That's element H12. It becomes element 21 of G. So the 1, 2 becomes 2, 1. 1 and 2 are swapped to become 2, 1. Said formally, H prime, or H transpose Mn, is equal to H Nm for all M and N in H. So now let's see how to do that in MATLAB. And let's use the same matrix. H equals 1, 2, 3, 4, 5, 6. We want to set G equal to the transpose of H. And here's how we do it. Simple. And we can see what we've done here. We have a row that changes to a column, and the second row that changes to the second column. Note that H itself is not changed by this operation since it's not on the left side of an equal sign. Let's prove that. So here's H. Still has 2 rows, 3 columns. You can use transposition to change a column vector into a row vector and vice versa. Let's do that. Let's set X equal to, say, 1, 3, 5, 7. And now let's let X equal X prime. This time we have changed X. On the right side, we've said we want the transpose of X, and then we've assigned it on the left side to X. So what was a column vector is now a row vector. Now look at this. As you know, the colon operator gives you a row vector. Let's suppose we want a column vector with the same numbers. So we naively put the prime symbol there for transpose. And we get the same thing. So what happened? Well, what we wanted to do was first make a row vector using the colon operator and then transpose it. But what in fact happened is that we transposed the 5 first and then used the colon operator. Transposing the 5 does nothing because 5 is just a 1 by 1 matrix. We can transpose it, but since it's just got 1 row and 1 column, the result is the same. To get the colon operator to go first, we have to use parentheses, like this. Now we get what we wanted.
MATLAB will always carry out the operations inside the parentheses first. And parentheses are important because in MATLAB, the transposition operator is ranked above the colon operator, which means that without the parentheses, it goes first. And that definitely wasn't what we wanted to happen. So how can you find out the relative rankings of the operators? In computer science, the rank of an operator is called its precedence. And after we've had a chance to show you a few more operators, we'll give you a precedence table with all the rankings.
We're going to look at array addition. There are special rules for arithmetic on arrays. Let's look at an example to illustrate it. X and Y are two arrays that we want to add together. X is a 3 by 2 matrix, 1, 4, 7, 0, 5, 5, and Y is also a 3 by 2 matrix, 2 minus 4, 6, 2, 0, and 3. In order to add two matrices together, we have to make sure that they have the same dimensions. So suppose we give MATLAB the command z equals x plus y. What's z look like? Well, here's what x plus y equals to z means. On the right side, we see the two matrices, x and y, added together. And on the left side, we see what happens. Let's look at the first element on the first row. The first element on the first row of x and y is 1 and 2. We add those together, 1 plus 2. That's what we put at the first element on the first row of z. Let's look at the next element on that row. X and y are 4 and minus 4. If we add those together, we get 4 plus minus 4, which will be 0. And we do this for every position in the matrices. If we carry out these individual additions, we get 3, 0, 13, 2, 5, and 8 on the left side. And so z is equal to 3, 0, 13, 2, 5, and 8. Let's take a look at this in MATLAB.
Well, we'll give MATLAB something to work with. Let's let x equal 1, 5, minus 2 on the first row, and then 3, 0, 7 on the second row. And we'll be lazy with y. We'll use the colon operator. So x is 2 by 3, that's 6 elements. Y is 1 by 6, also 6 elements. So let's add them and assign them to z. MATLAB doesn't like this. It says matrix dimensions must agree. Well, we've tried to add a 2 by 3 matrix and a 1 by 6 matrix. And as we pointed out, that doesn't work. So what I meant to do was make y a 2 by 3 matrix by putting a semicolon here instead of a comma. And now I'm going to use the up arrow to repeat that command, z equals x plus y, and things work just fine now. Subtraction works great too. Let's try that. Let's let z equal x minus y. And there's no problem there either. Let's look at some of these numbers and see if they came out right. With addition, well, let's look at this second element on the first row. We ended up with a 7. Where'd that come from? Well, there was a 5 at that position in x and a 2 in y. 5 plus 2 is 7. And what about this minus 5 on the second row of z here? When we did subtraction, well, we had a 0 there for x, and we had a 5 for y. 0 minus 5 gives us minus 5. And we can do a similar thing with array multiplication.
Array multiplication is very similar to array addition. We'll use the same example, x and y, that we used to illustrate addition for multiplication. If we want to do array multiplication, we use the dot asterisk operator. So we say z equals x dot asterisk y.
You may wonder why we don't just use the regular asterisk, which is the traditional symbol for times. That's because the asterisk alone is reserved for matrix multiplication, which is different from array multiplication. So what does Z look like? Well, on the right side, you see the same numbers you saw for array addition, but this time the operator is the dot star operator. And on the left, the only difference is instead of plus everywhere, you see the asterisk, the times symbol. So we have 1 times 2, 4 times minus 4, and so on. So you carry out all these multiplications, and you can see the result for Z right here. Well, array multiplication has the same rule that addition and subtraction has, that is that the matrices that are operands have to have the same dimensions. So we'll use the same examples, x and y, that we used for addition and subtraction. And here we go. Z is equal to x dot star y. That's array multiplications. Really simple. And we can check an example. Here's a 5 and a 2 on the first row's second element, and 5 times 2 is 10. And if we look at the last element on the second row, we see a 7 and a 6, and a 7 times 6 is 42. So when might you use array multiplication? Well, let's clear the screen and do an example. Let's suppose you had an array of temperature sensors outdoors somewhere laid out in a rectangular grid covering a few square miles and reporting back to a central facility. And today, let's suppose they measured these high temperatures, which I've already put into an array called highs measured. Let's take a look at these. There. So it's a 2x3 array. You'd probably have a larger array in a real application, but this is just an example. And furthermore, suppose that each sensor's measured temperature must be corrected by multiplying it by the sensor's calibration factor. And that would be kept in a permanent array of the same shape. I've set up that array too and called it calibration factors. Let's look at that one. There. And you can see both of these over in the workspace over here on the right. They were sitting there. I don't know if you'd noticed them. Well, to get the true temperatures, we now need to multiply each element in highs measured by the corresponding element in calibration factors. And that's exactly what array multiplication does for us. So let's do that. Let's call the result highs true. And we'll set that to highs measured dot star. There's that array multiplication operator. Calibration factors. And there's a result. If you look back at the original temperatures up here, 71, 52, 78, and 83, and so on, these are more reasonable down here, 78, 78, 77. They're just varying by a smaller amount. They're more reasonable because you wouldn't expect a wide variation over just a few square miles. The need for calibration like this is fairly common, and array multiplication makes it easy to do.
So now we know how array multiplication works, and we know that matrix multiplication is very different from array multiplication. In fact, it differs in 3 ways. First, there's obviously no dot. Second, the shapes of x and y must be compatible, which is different from having the same shape. And third, the calculation of each element of z uses both multiplication and addition. Well, first let's look at the compatibility requirement. Here we show z, x, and y schematically. And we've been careful to give them all different shapes. So x is clearly not the same shape as y, but it is, as we'll see, compatible with y. X and y are compatible because the width of x is the same as the height of y. We've highlighted that with the blue arrows. To be specific, the width of the left operand of the matrix multiplication operator must be equal to the height of the right operand. Put another way, the number of columns of the left operand x must equal the number of rows of the right operand y.
Let's move our schematic up a little bit to make room to write out their dimensions. And there are X's dimensions. And we've color-coded them to make it easy to see that the number of rows, L, is the height of X, and the number of columns, M, is its width. Similarly, we show the dimensions of Y and color-code them so it's obvious that the number of rows, M, of Y, is its height, and the number of columns, N, is its width. If we drop the schematics and put the dimensions under X and Y in the matrix multiplication operation, we notice that there are two dimensions next to each other that are equal, the two blue M's. Because of the way that these M's are situated between the L and the N, they are called the inner dimensions of X and Y. And that provides a simple way to state the compatibility rule for matrix multiplication. We simply say that the inner dimensions of X and Y must be equal. So what about the L and the N? Well, they're called the outer dimensions, and there's no restriction on them whatever. But they do have an effect on the calculation. They determine the shape of the result. Z will be an L by N matrix. So to review, the width of X, blue, must equal the height of Y. The height of Z, red, equals the height of X. And the width of Z, green, equals the width of Y. So we know the shape of Z, but we still don't know how its elements are calculated. Let's use MATLAB to see how that's done. I've already prepared a couple of matrices that we can multiply, A and B. The dimensions are 4 by 3 for A and 3 by 2 for B. Since the width of A is equal to the height of B, we can do matrix multiplication of A times B. But before we do, let's put the sizes into a row vector, like this. Arranging their dimensions like this shows that the inner dimensions are equal. Here are the inner dimensions right here, 3, 3, which is another way to say that the dimensions satisfy the rule for matrix multiplication. So let's multiply them and assign the result to C. So C is 4 by 2, and those are the outer dimensions, 4 and 2, of the matrices A and B, as expected. Okay, so let's see how matrix multiplication produced an element of C, say the 0 on the third row. That element is C32, this one. There, 0. Since C32 is on row 3 and column 2, its calculation involves only the elements on row 3 of A and column 2 of B. It's calculated like this. Now I'm going to write it out in detail. There it is, and indeed it equals 0. Now let's look at that expression. Note that the row index stays the same for A, so 3, 3, 3. And the column index stays the same for B, so it's 2, 2, and 2. But the inner index, this one here, this 1 and this 1, the inner index means it's the inner index of these 4. And it's the same for the A and the B. It ranges from 1 to 2 to 3. It ranges across the entire width of A and height of B. The products of these pairs of elements are then summed to get element 3, 2 of C. This same sort of calculation is performed for every row of A with every column of B. And since there are 4 rows of A and 2 columns of B, we get a 4 by 2 matrix. And what happens if the inner dimensions do not match? Well, we can get an example of that by just multiplying B and A in the other order. MATLAB complains. It says inner matrix dimensions must agree. And to show that it's right to complain, let's put the dimensions for b times a into a row vector just as we did for a times b. So size b this time, size a. Sure enough, the inner dimensions, 2 and 4, are not equal. So MATLAB's right. But then MATLAB's always right. So that's how matrix multiplication is carried out. But when might you want to use matrix multiplication? Well, let's clear the screen. There, nice and tidy. And look at an application. We'll use the same two matrices, A and B. And here they are again, A, B. Suppose a given row of A represents numbers of shares of each of 3 stocks. And each row gives the shares owned by one of 4 persons. So person number 1 owns 1 share of the first stock, 2 shares of the second stock, and 3 shares of the third stock. Person 2 owns 4, 5, and 6 shares, respectively, and so on. Suppose also that each column of B represents the gain in dollars of 3 stocks. Column 1 gives the gains for the stocks on one day, and column 2 gives the gains on a second day. So looking at column 1, we see that on the first day, the first stock gained $2, the second stock gained $3, and the third one gained $7. Looking at column 2, we see that on the second day, the first stock lost $2, and the other 2 gained $8 and $4, respectively. Well, to calculate the profit that one person would have made on a given day, we need to multiply the number of shares times the gain for each stock on that day, and then add the 3 products together. So, for example, to calculate the profit for the first person on the first day, we would multiply 1 share times $2 to get $2, and 2 shares times $3 to get $6, and 3 shares times $7 to get $21, and then add these 3 products together to get $29. Then we'd repeat that process for each person, that's each row of A, and each day, that's each column of B. Well, that's exactly what matrix multiplication does for us. So let's do it. There are 4 people in 2 days, so there are 8 distinct profits to calculate, and the results are all laid out neatly in matrix C. Let's see. The first person profited about the same on each day, $29 and $26. The third person did much better on the first day, didn't make anything on the second day. And by comparing the columns, we can see that everybody did better on the first day than they did on the second day. Matrix multiplication made this calculation easy. But this operator has applications far beyond the stock market and far beyond finance. The applications fall under the heading of linear algebra, and you can find many examples in books on this subject. Types of division, the so-called matrix division and array division. We're going to take up array division first, and there are 2 types of array division. Here's how you divide x and y. First of all, there's x dot slash y, and then there's x dot backslash y. In the first case, it kind of looks like x is over y, so that's x over y, and the other one sort of looks like x is under y, so we'll call that x under y. And we'll explain what both of those mean. Here's an example. You see an x and a y. They're both the same shape and size. That's required for array division. And now let's suppose we use that first example, x dot slash y, x over y. and put that in Z. So what does Z look like? Well, over on the right side, we see X written out and Y written out, separated by the dot/slash operation. And over on the left, we see the result. Let's look at the first element on the top row. We see 1/2. Over on the right, we see a 1 and a 2 in those positions. So 1 divided by 2 equals 1 over 2, and that's what we get for Z. Of course, MATLAB will carry that out and give you 0.5. Every single one of the elements in Z is equal to the corresponding element in X divided by the corresponding element in Y. And that's what dot/Y means. Here's what it looks like, the results in MATLAB when all these divisions are carried out. And when they're assigned to Z, this is what Z looks like. No surprise there. And what about the backslash case? Well, everything's the same except that 1, instead of being divided by 2, is divided into 2. This is the 1 under the 2 case. So 1 under 2, what do you think that's going to be? Well, it's 2 instead of 1/2. 1 goes into 2 2 times. Same thing happens for every element at every position. Here's 1 under 2, and we're showing you that it's the same as 2 over 1. And here are the numbers carried out to 4 decimal places, and here's what you see when it's assigned to Z. You should try some examples of your own to get used to this array division. But don't forget the dot. If you leave the dot out, then you're in a strange new territory called matrix division. Matrix division has different rules completely. In fact, it's quite a complicated concept in linear algebra, and we're not covering it here. But if you want to check it out, you can try the advanced concepts of the textbook and get a detailed explanation.
Now let's look at exponentiation. 2 caret 3. The caret is the exponentiation operator, and 2 to the third power is what that means. 2 to the third power is 8. Not surprising. But what might be surprising is that you can do exponentiation operation with arrays. Array exponentiation works sort of like array multiplication. At least the rules are the same. Let's look at x, 1, 2, 3, 4. And let's let n equal 6, 0.5 minus 1, 2. X dot caret n is the array exponentiation operation. The dot means array exponentiation, just like the dot means array multiplication when we have dot star. And let's look at the result. What this means is the first element of x on the first row, 1, is raised to the first element on the first row of n. So 1 to the 6th power, of course, is 1. The second element on the first row of x is raised to the power of the second element on the first row of n. So we have 2 raised to the 1/2 power. Well, that's the square root of 2. And down here we have 3 raised to the minus 1 power. Well, that's 1/3, and 4 raised to the 2 power, which is 16. So that's array exponentiation. There's no real surprises there. As you may have guessed, if we go to matrix exponentiation, things are going to be more complicated, just like they were more complicated when we went from array multiplication to matrix multiplication. We'll only cover one case, and that's the case in which the second operand is actually a scalar. Let's do that. X matrix exponentiation 3. What this means is x is multiplied by itself
using matrix multiplication 3 times. So it's the same as this. X times X times X, and you can see you get the same result. It's not possible to raise X to a power like this unless X is a square matrix. That's true because, as you may remember, for matrix multiplication, the width of the first matrix has to be equal to the height of the second matrix. Since both these matrices are X, that means the width of X has to be equal to the height of X, and that's the definition of a square matrix. We've seen that there are strict rules on the sizes and shapes of the operands for both array and matrix operations. For array operations, the matrices must have the same size and shape, while for matrix operations, the width of the first matrix must equal the height of the second one. Now we're going to see that MATLAB waives these rules when one operand is a scalar. We'll show how it works with some examples. I'm going to gin up a couple of matrices first. Here's my favorite. It's so easy to type. And another one. Just picking some random digits here. And we'll start with addition. You'll remember that the addition of two matrices requires that they have the same size and shape. A and B here are both 2 by 3, so we can add them. And let's do it. There, no problem. But we can violate the same size and shape rule if one operand is a scalar. So let's do that one. There, I've got the matrix A, which is 2 by 3, and I've added a scalar, which, by the way, is a matrix that's 1 by 1. And 2 by 3 doesn't match 1 by 1, but no error message. And what happened? Well, you can see here, if we look at A, the first element is a 1. We've added a 3 to that 1 to get a 4. The second element on the first row is a 2. We've added a 3 to that. We've added a 3 to every one of them. And that's the general idea for any arithmetic operation that mixes a scalar and a matrix. The operation is repeated for each element using the scalar as one of the operands. And the scalar can come first or second, as for example, there, which, as you would expect, does the same thing as A plus 3. Let's do some more examples. A minus 1 subtracts 1 from each element. 2 dot star A multiplies each element by 2. 2 star A, the matrix multiplication version, does the same thing. And we can divide 2, let's see, A dot slash 2, array division of A by 2, divides each element by 2. And you can go the other way, 2 dot slash A, divides each element of A into 2. The matrix versions of division with a scalar and a matrix don't work, though. So 2, say, divided by A. MATLAB doesn't like that. And A under 2 also gives an error. Finally, the array version of exponentiation works as you might expect it to. A dot caret 2 applies that exponent 2 to each element of A, so it squares each element. And it works the other direction too. Let's look at A again so we can remember what's in there. Here we have 2 because we've raised 2 to the 1 power here. Here we have 4 because we've raised 2 to the 2 power. Here you have an 8 because we've raised 2 to the 3 power, and so on, until we get all the way down here to 64, which is 2 raised to the 6 power. So array exponentiation works fine with a scalar. But as we've just seen, the matrix version of exponentiation is kind of picky. A caret 2 is no good unless a is square. And of course, a is 2 by 3, so it's not square. All these special cases with scalars may require a little memorization. It's just like idioms in a spoken language. But very little memorization for two reasons. First, the cases of addition, subtraction, and multiplication work exactly the same as they do in ordinary mathematical calculations, so you may be familiar with them already. And second, you can always try out unfamiliar cases on small examples to see whether they work and what they do. That's what I do. Welcome to Lesson 3, Functions. So far what we've learned is how to perform individual operations with MATLAB, and we've used MATLAB as a glorified calculator. But now it's time to start programming. You'll remember that we've called a few of MATLAB's built-in functions. For example, to plot lines in a figure, to calculate the square root, to calculate the sine, and to do other things. And there's hundreds more functions that we could call. But what if we need a function that's not provided by MATLAB? Guess what? We can write our own functions, and we can use them just as if they were built into MATLAB. Let's see how. The built-in function named rand creates random numbers between 0 and 1. The numbers are uniformly distributed, and that means that any number in that range is equally likely to be chosen. Here's an example of how we might call it. Creates a 3 by 4 matrix of random numbers between 0 and 1. You can see the first argument gave us the 3, and the second one the 4, the height and the width of the matrix that's returned. And you can see these numbers are all between 0 and 1. Well, what if we needed random numbers between 1 and 10 instead? It's easy enough. And here's some numbers between 1 and 10. Multiplying by 9 stretch the range to go from 0 to 9, and adding 1 shifts the range to go from 1 to 10. Let's say we need this functionality repeatedly. We could type in this expression every time we need it, but that would be annoying. And more importantly, it would be error-prone. We might mistype something one or more of these times, and the result would be wrong, and potentially we might not even notice it. So let's create our own function that does what we want it to do. Then we can just call that function repeatedly. And let's call it myRand. We create a function by using the editor. Let's see what that is. We can get it with the command edit. E-D-I-T, turn. And there's the editor window right there. The editor is the place that you type in code that you can save in a file. And the code we're going to type into the editor will be a function. We type this, function myRand return a equals 1 plus rand 3, 4 times 9, return, and I'm going to put an optional end in here. You'll notice that function and end both turned blue. These are keywords. We'll say something about that a little bit later. The word myRand is, of course, the name of our function. So now what do? Well, we want to be able to run this function. And in order to run the function, we have to save it into a file. MATLAB reminds us that we haven't yet saved it in the file with this little word untitled and this little asterisk right here. Okay, to save our function into its file, we click this little diskette right over here. Up pops our operating system's file save window. And it's suggesting that we name this myran.m. That's a good idea. This is no time to be imaginative. We're going to name it just that. We could pick another name, but it's very bad practice to do that because it can be very confusing. First off, we should always use the same name for the file, not counting the .m here, that we used for the function name, which is myran in this case. And second, the .m is required. All MATLAB functions must be stored in files with the extension .m, and as a result, they're all called .m files. Okay, let's save this file. We hit save. And notice that the file is saved right here in the current folder. That's exactly where we want it to be because that's where MATLAB will look for it when we tell it to run it. Okay, we've opened the editor, we've typed in a function, we've saved it into a file. We can now run it by typing its name in the command window, just like we would for a built-in function. Let's do it. Voila! There's our 3x4 array of random numbers selected from the range 1 to 10. Let's review what happened when the function ran. There was only one statement, so it's pretty simple. The expression over here on the right was evaluated. It was assigned to the variable a, and since we didn't put a semicolon at the end of the statement, by the way, that's why this little orange highlight shows up. And there's a little hint there that says terminate statement with semicolon to suppress output in functions. That only happens, that little yellow thing, only happens in a function. But anyway, we didn't put a semicolon there, so MATLAB printed the value of a in the command window. No surprise there. Let's print that value again. It's undefined. If you check the workspace, it's not there. Why? We didn't clear it, so where did it go? Has this workspace quit working? Something strange is happening here. Let's investigate. Let's assign a simple scalar value to a, say 3. There it is in the workspace, as it ought to be. A equals 3. Okay, let's run myran again. We got a new set of random numbers as expected. But look over here at a. Can its value still be 3? Wait a minute. Yep, a's value is still 3. It's not a random matrix. What's going on? Well, mon ami, allow me to elucidate. There's a saying in Nevada, what happens in Vegas stays in Vegas. And that saying fits what's happened here. A function has its own private workspace, and what happens in that workspace stays in that workspace. During that little fraction of a second that myran was running, I should say fraction of a microsecond, the variable a was created, right here, stored in myran's workspace, and then when myran was done, its workspace was deleted. It doesn't show up in the command window's workspace. The a that we see there is a completely different variable from the variable that was created over here. The one that was assigned this array of random numbers is gone forever, along with these values down here. All we're left with is the printout of those values. We can look at them, admire them, but we can't assign them to a variable in the command window or use them in any other way. The variables in the disappearing workspace are called local variables in computer science terminology. These are variables that are defined by assignment statements inside the function, and they can be used only inside the function. Here's the textbook definition. Local variable, A variable that is accessible only by statements inside one function. A local variable exists only during the function call. Well, this is not good. A function typically calculates a result, and if we can't use the result of the calculation after the function closes, what good is it? We need to be able to propagate that result from the inside the function out into the outside world. We do that with an output argument. Let's see how that works. Let's change myRand just a little bit here to make A an output argument. We do that by typing A equals right here between the function keyword and the name of the function. Now let's save our function. We come up here and you'll notice that this little diskette is bluish, and I'm going to click on it and watch it change to gray. There. That means what's in the file here is the same as what's on the screen. And that's important because when we call the function, the code that will run is the code that's inside the file. Now let's run myRand. Now we get the result twice, here and here. So why is that? Well, first, while the function's running, MATLAB prints the result of this assignment statement right up here because we don't have a semicolon here at the end of it. So this is the first printout, and you can see it says A equals because we have A equals up here. And then after the function is done, down here in the command window, MATLAB echoes the result of the value that's returned from this call of myRand right here. And here it is, because we don't have a semicolon after that. These two values are the same, so we see the same numbers twice, here and here. Oh, and in case you've forgotten, this variable ands that appeared out of nowhere is that variable that's automatically created by MATLAB whenever it calculates a value that's not explicitly signed to a variable. This wasn't explicitly signed to a variable, and so it made this variable ands to accept the value. And what about A? It looks like it's finally gotten the values we wanted it to have, so let's double check that. No. It's still equal to 3 because this A here, the one we see in this workspace, is the one that we set in the command window, not the one that we set up here in the function. It makes no difference that we declared A here to be an output argument. An output argument is still a local variable, and it lives only as long as the function is running. It just happens to be the local variable that holds the value that we wanted the function to output. It still disappears as soon as the function's done, just a split second after its value is sent to the command window. No matter how many times we run myRand, the A in the command window will be unaffected. It's not the A in the function, so it just stays equal to 3. Okay, let's tell MATLAB not to print from inside the function. We don't need that. A semicolon right here should take care of that. Now, when we run myRand, this statement inside the function right here won't cause any printout, and we'll see only one copy of the random numbers. But before I run it, I want you to note that the diskette icon is blue over here, indicating that we've changed the contents of the editor, but we've not yet saved those contents into the M file named myRand. And there are two other indications that we've not saved yet. The file name here in the current window and the file name here on this little tab in the editor both have an asterisk after the name. That also means that we haven't saved. Now I'm going to click in the command window and watch what happens. There. This disk icon is gray. This file name doesn't have an asterisk after it, and this file name doesn't have an asterisk after it. This is a new feature of the latest version of MATLAB. When you click anywhere outside the editor window in version 2014b, MATLAB automatically saves the function into the file. If you have an earlier version, you'll need to remember to click the diskette icon or use the appropriate keyboard shortcut, such as Control-S or Command-S or whatever your operating system might provide. to save the file before you run it in the command window. Okay, let's run it again. Now only one copy of the output appears. That's good, but we should still capture the output into a variable of our choosing instead of ands, which is the variable that MATLAB chooses. So how about, B? There, we look over here, we see that there's a B, and it says it's a 3x4 array. Double will explain what that means later. You can look at these variables, so let's click that, double click it, and you see the array laid out here that's inside B. And I'm going to close that. Of course, we don't usually need to see this output, so one last thing, we could put a semicolon. This time I'm going to use a C, semicolon. So now nothing happens here, but the C gets the value, as you can see. Here it is. There, C has the value. There's the C. C got a different value than B because every time we run myrand, we get a different set of random numbers. Okay, we have our function working perfectly. What if we also wanted a 3x4 random matrix with values between 2 and 5 as opposed to 1 and 10? What would the formula look like for that? Let's see. Right now we got the numbers ranging between 1 and 10. And we did that by adding 1 here and multiplying by 9. The 9 was the range between the values from 1 to 10, which is 10 minus 1. So we could get the numbers that range from 2 to 5 this way. And those numbers look like they range from 2 to 5. The reason I wrote 5 minus 2 instead of 3 will be apparent in a minute. Okay, so to use this formula, should we write another function? No. What we should do is modify myrand to be more general. It should be able to provide a 3x4 matrix of random numbers between any two limits we want. We can do this by providing two input arguments to the function that specify the limits we want, then using those two arguments in the formula. Let's do that. The input arguments come after the function name here and go in parentheses, and if there are two or more of them, they must be separated by commas. Let's name them low and high. Before we go further, I want to take a minute to explain this yellow pop-up. This thing right here. It's a tip to help us with programming. It says that the input argument low, right here, might be unused, and it suggests what we might want to do if this is okay. Well, it's not okay. We are going to use it. We just haven't used it yet. This tip is MATLAB's way of helping us while we write our code. It's gently suggesting that we might be forgetting to do something. Because after all, why would we require an input to myrand if we aren't going to use it? If we hover the mouse over high, we get the same sort of warning about that argument. And also both high and low are highlighted, as you can see here, to alert us that something might be wrong. These highlights will disappear, and you'll notice that, when we use low and high in the calculation of A. And we're going to put both low and high in that calculation right now. So here's low. And this, remember, is the difference, high minus low. By the way, input arguments, just like all the other variables, the output arguments in a function are local variables. So you can't read them outside. Now you can see why I used 5 minus 2 instead of 3 down here when I was doing this calculation of the random numbers from 2 to 5. It was to emphasize that when you give MATLAB the range 2 to 5 or low to high in general, the only way to know what the range is that you're going to multiply by here, that is the difference between high and low, is to subtract them. Well, okay, let's try out this more versatile version of our new function. I'm going to put the value in a variable called test and give it two arguments, 2 and 5. I'm going to put a semicolon there so we won't have anything printing out in the command window. Before I hit return, let's think what happens. First, the input argument low, right up here, will get the value 2 because it's the first argument. And the input argument high will get the second value 5 because it's second. Then this function will use low and high in this expression to calculate the random numbers. Third, since A is declared right here to be an output argument, its value will be returned when the function closes. It'll show up right down here. The way a value is returned is no different from the way a value is returned from any function, like the built-in functions. When we say return, we simply mean that the value, this value, whatever it is inside A, is inserted right here at the point where the function was called, which in this case is in the command window on the right side of this equal sign. Okay, let's execute. There. Let's look at test. Well, it looks right. I mean, the numbers seem to be between 2 and 5. Now let's try to take a look at low, which was one of our input arguments. Well, we get a message here that says undefined function or variable low. Did you mean flow? Well, that's something else that we might have meant, but no. What we wanted to do was just establish again, and it shouldn't be a surprise, that you get no low in the command window. This low is in here in MyRand, and it's just a local variable, just like high is. Neither one of them are available outside the function. Now let's tell MyRand to use the range we started with. Remember that 1 to 10? Let's put that in test 2. I don't think I'll put a semicolon this time, so we can just take a look right at it. Yeah, it looks like that goes from 1 to 10. These numbers are between 1 and 10. Works like a charm. Wonder if it works with negative numbers. Let's go from -2, say, to 6. Did you notice that little hint we got there? It's giving us a hint with our own function. It'll do this with a built-in function. It'll do this with any function that you create. It shows you that if there's a couple of arguments, low and high, and there they are up there, just to remind you. So where was I? I was going to do -2 to 6. -2 to 6. Yeah, it looks like these numbers range from -2 to 6. We've got a really versatile function here. Okay, let's clear the screen and clear the workspace. Our function has 2 scalars as input and 1 matrix as output. But what if you want your function to return 2 outputs? No worries. There's an easy way to do that. Let's say we want MyRand to compute the sum of all the elements of the generated random matrix and return both the matrix and the sum. Well, let's add a couple of statements to calculate the sum of the elements in A. Put my cursor there, hit return. These 2 statements will do it. You might be surprised by the first one of these statements. Since A is a matrix, when we put parentheses after it, you'd probably expect to see us put 2 indices inside them. Separated by a comma to specify an element on a given row and column. Instead, we've given just 1 colon here. This is a special way of indexing in MATLAB. When you give just 1 index for an array, MATLAB treats it as if all its columns were stacked up into one long column vector. And that index picks out one element in that vector. And when that index is a colon, it means you want all the elements in that vector. And in this statement, when you give the built-in function sum an argument that's a vector, it returns the sum of all the elements in that vector. And since V has all the elements of A, we're going to get the sum of all the elements of A, and that's what we want here. By the way, if we were to give sum the matrix A directly instead of a vector, it would calculate a set of sums, one for each column of A, and it would return them in a row vector. But that's not what we want here. Okay, so we've got the sum, we've got the matrix in A. Let's see how to return both A and the sum that's in S now that we've calculated them. We make a very small change in the header of MyRand. That is, in this first line, like this. There. We now have two output arguments, A and S. We can have as many output arguments as we want as long as we put them in square brackets like this, and it's recommended that they be separated by commas. Okay, let's run it. First, we have to save it. I can save it automatically simply by clicking in the command window, since this is version R2014B of MATLAB. But I'll remind those of you who are using earlier versions that you'll need to save your functions manually every time you change them. And you can do that by clicking on this little blue diskette icon over here. Okay, here goes. I'm going to give it 2, 3 as arguments. And there's our matrix. Wait, who stole the sum? Where did it go? Well, we didn't save it in a variable, so MATLAB threw it out. It catches only the first result of a function. And the first result in this case was the matrix, which was stored in A. If we want to catch two results, then we need to provide two variables to catch them. Like this. I'm going to give variables x and ss. We'll do 2, 3 again. There. Looks like x got the matrix and ss got the sum. You see the syntax for catching more than one output returned by a function? We need the square brackets again, just as we did up here in the function arguments, output arguments. And this time the comma is totally optional. Well, we've seen what happens when we call the function without enough output arguments. We just lose some of them. What happens if we call it with too many output arguments? Say 3 in this case. Let's go, I don't know, minus 10 to 10. We found out that negatives work. Well, MATLAB complains. Error using MyRand. Too many output arguments. Well, sorry, MATLAB. We'll try not to do that in the future.
Now we know enough to study the formal definition of MATLAB functions. A function's interface with the world is defined in a header at the beginning, and that header is called the function declaration. The declaration starts with the function keyword, and to remind you that it's a keyword, MATLAB highlights it for you in blue. Then come the output arguments, if you have any. If you have more than one, the square brackets are required, otherwise they can be omitted. And if you have output arguments, even one of them, then you have to have an equal sign. Otherwise, it can be omitted. Next comes the function name. And the same rules apply for function names as for variable names. Then come the input arguments, if any. If you don't have any input arguments, then parentheses are optional.
Otherwise, a comma-separated list of input argument names goes between parentheses. Okay, that's the formal description of the function declaration. But let's see some examples. You can have 0, 1, or multiple output arguments, and 0, 1, or multiple input arguments. And you can have them in any combination. In fact, here are all 9 possibilities, starting with a case in which there are no output and no input arguments, in example 1, and ending with a case in which there are multiple output arguments and multiple input arguments, in example 9. And what about function names? First off, the name of the function should be descriptive. For example, if you write a function that computes the Fibonacci series, don't call it f or x. Instead, call it Fibonacci or Fibo or something that suggests its purpose. And stay away from the names of built-in functions because that can get very confusing very fast. If you see a function called sqrt, for example, you're going to expect it to return the square root of its argument. And furthermore, if you name your function sqrt, you won't be able to call the built-in sqrt. You'll be running yours instead. How do you know whether or not there's a built-in function with a name that you'd like to use? Use the built-in function named exist. The command help exist will help you learn how to use it. As we've seen, one function can call another function. For example, myRand called the built-in functions rand and sum. But built-in functions don't have to be involved at all. Our own functions can call each other as well. We could, for example, define a function called Bob, which we saved into bob.m, and a function Mary, which we saved into mary.m. Then Bob could call Mary, or Mary could call Bob. Furthermore, we can define multiple functions in the same M file and have them call each other. Why, you may ask, would we put 2 functions in the same file? Well, if the problem we're trying to solve is complicated, we'll want to break it up into several functions. But if those functions are not likely to be useful for solving other problems, then it makes sense to keep them all in the same M file. Let's see an example. Let's rewrite the last version of myRand. Let's see, we'll leave all this the same, but we're going to get rid of this. Instead of calling sum here, we're going to call sum all elements of A. Now that's not a built-in function, so where is it going to come from? Well, we're going to put it right here. Let me get rid of this end statement. We're going to put it right here in the same file. I got rid of the end statement because if you have more than one function in a file, either they all have to have end statements or none of them can have end statements, and it's extra typing, so I just got rid of it. We've created a separate function for summing up the elements. This is, of course, a very simple example, and there's not much of an advantage to doing this here, but later we'll see examples when it matters. In any case, you can see how simple the syntax is. The second function keyword, right here, indicates that the first function is ended and the second one is begun. Functions that are defined in the same file like this behave in most respects just like other functions. The only difference is that only the first function up here, which is called the main function, can be called by other functions outside the file. The other functions, in this case we only have one, are called subfunctions or local functions, and they can only be called by functions inside the file. Like other functions, all their variables are local, and this means that the variables in a function are unavailable to the command window and unavailable to all other functions, whether or not they're in the same file. So V is not available inside myrand, A is not available inside sum all elements, and none of these variables are available down here inside the command window. Well, let's see if this thing works. Let's see, we'll do the same exact command that we did before we made the change. There. Works. The only way to exchange information between these functions is with input and output arguments. In this case, when we call sum elements from inside myrand, we use A as an input argument to pass its value into sum all elements. That value, which happens to be a 3x4 array, is copied from A into the input argument M inside sum all elements. Note that we calculated the sum of the elements of the 3x4 array, which is in M, the same way as we did it before, but this time the calculation is done inside sum all elements, and the array that we're working on is inside the variable M. Note that we can't use the variable A here inside sum all elements. We can't because it's a local variable of myrand. And the local variables of myrand are unavailable inside other functions. Okay, so we pass the array into sum all elements via an input argument. And after we calculate the sum, we need to send that sum back to myrand. Well, inside sum all elements, this local variable summa is declared right here to be an output argument. So that means when sum all elements is done and closes, the contents of that summa, which is the sum we want, will appear right here in myrand where sum all elements was invoked. And then it'll be copied into S, and when myrand ends, and that'll go back to the command window, or whoever called this function myrand. The passing of information via input and output arguments when one function calls another is the same for any function, whether it be a subfunction or not, and whether it's a built-in function or not. Okay, so that's how this thing works. You can put as many subfunctions in an M file as you want, but the first function, you should remember, is always the only one that can be called from outside. Okay, we've pointed out that local variables are visible only within the function in which they're defined. So even though the variable v was just given a value by sum all elements when we called it, and of course it was called from myrand, we called myrand and it called sum all elements, and then v was given a value. Even though all that happened, we can't access v from inside the command window. Let's try it. V. Told you. In computer science terminology, we express this local variable restriction by saying that a function's variables have local scope. Scope is defined as the set of statements that can access a variable. And this limitation, that the set of statements that can access a variable are just inside the function in which the variable is defined, it's actually a good thing. It keeps things simple, and local variables are all we need in the vast majority of cases. And this limitation of scope to just the set of statements inside a function has a computer science term too. It's called local scope. Let's look at that. Local scope is accessibility by statements in only one function or only in the command window. But in some very, very rare cases, two or more functions and or the command window may need to share a variable. So maybe the command window needs to share this variable v. Well, let's see how to do that. We do it by creating a variable whose scope can extend outside the function. Such a variable is called a global variable. Let's suppose you wanted to make v global. Then somewhere in the function before v is used, we insert this declaration, and I'm going to put it right here before v is used. Global v. There. I'll put a semicolon. You don't have to have one. By the way, in MATLAB, you cannot combine this global declaration with an assignment. So, for example, you couldn't just do this, global v, and then put equals m colon like that. And in that case, you wouldn't need this statement at all. Do it like that. That would be handy. I mentioned that you can't do that because you can do it in some other languages. Okay, so let's go back. If I go right up here, you'll see this little reverse undo thing. Let's undo, undo, undo. There, we're back to where I wanted to be. Okay, now if you make the same declaration in the command window, or in another function, or in multiple functions, or wherever you want to access this global variable, it'll be accessible there too. We'll do it in the command window. There, you can see v shows up here. Now when we run myrand, and let's do that, we'll just run myrand and give it, I don't know, 5, 6. Makes no difference what we give it for this purpose. If we access v, or attempt to from the command window, there it is. This time we can get v. Now what is v? It looks like a big long vector, and it is. If I scroll up, that's what it is. Remember, when we made v equal to m colon, this two-dimensional array m had its columns stacked up into one long column vector. And that's what we see here. But the point right now is that v is accessible both in sum all elements and in the command window. Okay, now you know how to make global variables. But the next thing I'm going to tell you is very important. Don't use them. Global variables can cause errors that are very difficult to diagnose because one function can change the values inside another function like a ghost moving the furniture around, and you can't know which function did it. It's not that globals are inherently bad, they're not toxic, and sometimes they're the best approach. But until you have some real experience with programming, you're far better off leaving them alone. You should probably avoid using global variables until you've been programming for at least, let's see, I'm going to make it 2 years. For the rest of this course, we won't need them at all. We certainly didn't need one here. So I'm going to remove this one before I forget. There. All gone.
Let's look at some of the advantages of functions. First off, functions allow you to break down large, complex problems into smaller, more manageable subproblems. And a typical computer program consists of many such functions, each of which solves one subproblem. An analogy can be drawn from real life. Suppose you buy a table from IKEA. Well, its assembly guide might describe how to put together one leg in detail. Then, instead of repeating that description 3 times, it'll just say, now do this for the 3 remaining legs. Saying do this 3 times is similar to calling a function 3 times, and it's much more efficient than repeating the description or repeating the code. The particular functions that you decide to write has a great impact on your program. In general, you should try to group together closely related tasks into a common function, and tasks that are not related should go into separate functions. The process of breaking down a complex problem into smaller ones is called functional decomposition, and mastering the art of decomposition will help you become a good programmer. There are many advantages to functions. For example, there are whole sets of functions called libraries
that are available on the internet with so-called open source licensing, meaning you can modify them, you can use them in your own programs for any purpose, including selling them. Using functions that other people have written in your own programs is sometimes called code reuse, and code reuse helps you avoid reinventing the wheel. Also, a function typically solves not just a single instance of a problem, but a general set of related problems. It does this by accepting varying values for its input arguments. The built-in function sqrt, for example, computes the square root of any number, or any matrix of numbers. The built-in function plot can generate an infinite number of different plots depending on its input. Even our little myrand function has a considerable degree of generality. These advantages to functions are so great that most MATLAB programmers put all the code they write inside them. And we're going to get lots of practice in this course doing just that. There's a second kind of M file that we haven't covered yet. It's an M file that doesn't have a function in it. This kind of M file is called a script. A script is just a collection of MATLAB commands. If you type the name of the script's M file and hit enter, MATLAB simply executes these commands one by one as if you typed them into the command window yourself. It's important to note that a script is very different from a function. First, a script never returns a value or accepts input arguments. And second, the scope of the script is the scope of the command window. So commands in a script access variables that are already in the command window workspace, and they can put new variables into the workspace with assignments, just as you do when you're giving commands in the command window. Let's do a very simple example. I'm going to make a script called example script. MATLAB tells us that this thing doesn't exist. Do we want to create it? I'll say yes, and I'm going to put do not show this prompt again. Okay, we see a tab show up here with the name example script. We got a blank page. We can type it in. Before I do, note that I've cleared the workspace, so there are no variables over here. So I'm going to make a variable called x by setting x equal to 5. And there we see x is in the workspace. You'll see why I did that in a minute. And I'm going to put two more variables there with this script, y and z. I'm going to do that with two assignment statements. Y equals x plus 3. I think I'll leave that semicolon off, and z equals 2 times y. Not a very exciting script, but it'll do. Now back here in the command window, to run the script, I just type the name of the script, which is example script, and hit return. The first statement in the script accessed x over here in the workspace, so you know that it has access to x. And each command, the first one and the second one, put a new variable over here in the workspace, y and z. MATLAB printed y's value to the command window because I didn't put a semicolon up here at the end of the command. That happened just as it would have if I'd typed that command directly into the command window. So when would you use a script? Well, you'd use it when you want MATLAB to repeat a set of commands in the command window many times and you don't want to type them many times. You tell MATLAB what's supposed to happen, just like a script says what's supposed to happen in a play or a movie, by writing a script. Okay, let's make one more script called end lesson 3. I'll use the edit command just as I did when I wanted to make a function. And I'm going to put 3 commands in this one. We'll look at the function fprintf in the next lesson. It just prints out this concludes lesson 3. The command pause with that 5 as an input argument, pauses for 5 seconds before the next command is executed. We need it here because without it, you won't have time to see the output from fprintf before MATLAB quits. Okay, let's run it. Okay, end lesson 3. Return. Oh, okay. I better hurry. Goodbye. I'll see you in lesson 4. Hi, and welcome to lesson 4, Toolbox. This week we'll be talking about the tools that a programming environment like MATLAB gives us to help create useful programs. These tools include the many built-in functions that MATLAB supplies. We've learned about a few of these already, but now we're going to cover many more of them. We'll see how we can print on the screen in a nicely formatted manner and how we can create graphical output. And perhaps most importantly, we'll see how MATLAB can help us track down and eliminate the errors that inevitably creep into our programs. Before we look at new tools, let's revisit one we've used already, the square root function. Let's suppose I want to take the square root of 9. Well, we know what that is. 3, no surprise there. Let me show you something that perhaps is surprising. I'm giving square root a matrix. So I'm going to ask you to take the square root of a matrix. What does it do here? Well, the matrix I gave it was a 3 by 2 matrix, 1, 4, 9, 16, 25, 36. I specified it right here in the input argument. And what square root does is go to each one of these elements, take the square root, and put it at the corresponding position in an output matrix that's the same size as the input matrix. So we got square root of 1 is 1, square root of 4 is 2, 9 goes to 3, square root of 16 is 4, 25, square root of 5. So this is an example of something that's not supported by all programming languages. It's polymorphism. If the type of an input argument to a function can vary from one call of the function to another, it's called a polymorphic function. Polymorphic means having multiple forms, and polymorphism is a powerful feature because it allows one function to handle a huge variety of inputs, which can save us a huge amount of work because we avoid having to write a huge variety of functions. Furthermore, as we'll see, not only can the type of the input arguments vary, but the number of arguments can vary as well. And we can make the function's behavior change when the type or number of arguments changes. Many built-in functions in MATLAB employ the first form of polymorphism by returning an output that's shaped like its input. For example, as we've seen, if we call the square root function with a 3 by 4 matrix, it'll return a 3 by 4 matrix. If we call it with a 1 by 2 matrix, it'll return a 1 by 2 matrix, and so forth. This shape-shifting of the output to match the input is in fact the predominant form of polymorphism in MATLAB, and it's very convenient. But not every built-in function behaves that way. And we're going to look at one right now that doesn't. The function sum doesn't behave this way. Let's make a vector v. Let's put some elements in it. Doesn't make a difference what it is. And let's give this vector to sum. There, I guess that's right. 1, 2, 3, 4, yeah. It sums up the elements of the vector. Now let's give it a matrix. Let's make the matrix A equal to 1, 2 on the first row, 3, 4 on the second one. So there's A. Let's give it sum A. When you give a matrix to sum, it returns a row vector, and each element of it is the sum of one column of the matrix. So 1 plus 3 is 4, 2 plus 4 is 6. However, when you give it a vector, like we did up here, it's vector v, it returns a scalar that's equal to the sum of the elements of the vector. So sum is polymorphic, but the output that it returns doesn't have the same shape as its input. We've seen how to make a function return more than one argument. Well, some built-in MATLAB functions do that. The maximum function, for example. Here we gave max a 4-element row vector, and it returned the maximum number in that vector, the element that's equal to 8. Now let's ask max to give us 2 outputs and see what happens. I'll give it the same input. This time it gave us an 8 and a 4. The 8 is still the maximum number. The 4 is the index of the maximum number. So the 4th element here was where the maximum was, so it returns a 4. Note that returning 2 output arguments is not the same as returning 1 output argument that is a vector with 2 elements. Size does that. S is a vector. It has 2 elements, 3 and 2. This is a 3 by 2 matrix, so it returned that vector 3, 2. And when I say it's a vector, just to establish that, here's the first element. There's the second element. The function max wouldn't allow us to catch both outputs as a single vector, but size does. However, the function size makes it possible also to save the elements of its output in another way, like this. This time it put the number of rows in the first output argument, and it put the number of columns in the second output argument. So, size behaves differently depending on the number of output arguments we ask for. This is another example of polymorphism. Polymorphism based on the number of outputs requested by the caller of the function. Note that if you want to write a function that has these polymorphic properties, the ones that depend on the number of output arguments, you have to write it that way. It's not something MATLAB does for you. We'll see later how you do this. So far, we've always created matrices manually like this. There's a 2 by 4 matrix. But MATLAB has a few functions that let you create matrices of arbitrary size really quickly. Here's one. You can see what it gives you. Zeros, a matrix of all zeros, and this was a 5 by 6 matrix. What if you want ones? You can get those too. What if you want all 5s? Well, that's the way you get that. Oh, and let's look at this. Just given one argument. 4 by 4. This is another example of polymorphism. If you give it 2 arguments, the first one's the number of rows, the next one's the number of columns. If you give it 1 argument, you're giving the rows and the columns. If you want a vector, let's do ones. This gives you a row vector. If you want a column vector, we'll do it with zeros. And if you want a diagonal matrix, you can have that. Suppose you want a matrix with 7, 3, 9, 1 on the diagonal. 7, 9, 1. There you are. A diagonal matrix, of course, has elements that are non-zero only where the row index equals the column index. So here's 1, 1. This is 2, 2, 3, 3, 4, 4. We want to look at random numbers now. Random numbers are very important in many fields, such as signal processing and on and on. And MATLAB has some different functions to support this. We've seen rand in the last lesson, but let's revisit that one now. You remember rand? there. It outputs numbers between 0 and 1 that are uniformly distributed on that range, meaning that any number in the range 0 to 1 has the same probability of being returned by RAND at any given time. And as we've seen, it can return matrices. This is one we did a lot of in a function called myRAND. And like these other matrix producers, when you give RAND one input argument, it treats that as a number of rows and columns, and you get a square matrix. In our previous lesson, we showed how to get a range other than 0 to 1 by combining RAND with arithmetic operators. For example, here's how you get a 5 by 4 matrix of numbers between 1 and 11. But what if you want random integers in that range? Well, first note that the whole number part of these numbers ranges from 1 to 10. If we could just drop the fractional part, we'd have integers that go from 1 to 10. Well, MATLAB provides the function fix that'll do that. It returns the whole number part of a number. In other words, fix rounds the number towards 0. Let's just give fix the expression we just came up with. So I'm going to hit the up arrow. I'm going to put parentheses around this. There. There doesn't happen to be a 1 there that time, but these numbers range from 1 to 10. I'm going to repeat that command. And there you see some numbers a little bit different, and there is a 1 there. Maybe that's reassuring that it's 1 to 10. But MATLAB will do better than that. It provides a function that returns random integers. It's called randy. Rand I. And I'm going to give it 3 arguments. 10. You can see all these hints there. There's lots of different ways to call it. 5, 4. That 10 means that we want integers that go from 1 to 10. The 5 and the 4 say that we want a 5 by 4 matrix of them, and so there they are. And by now you probably correctly guessed that randy is polymorphic. If you give it just 2 arguments, the first one's still treated as the maximum possible integer, but the second argument gives the number of rows and columns of a square matrix. So randy 25 will return a 5 by 5 matrix of integers between 1 or ranging from 1 to 20. You can also call randy one other way. Well, more than one other way, but as you can see there, if you give a vector for this first argument of 2 elements, 5, say 10, that means you want numbers that range from 5 to 10. And now 2, 3 says that we want a 2 by 3 matrix of them. Many times we need random numbers that have a normal distribution instead of a uniform distribution. This is also known as the Gaussian distribution. Sometimes it's called the bell curve. Here's how you get that. You use the function rand n, the n's for normal. I give it a 5. Well, the inputs are the same. A 5 means a 5 by 5 matrix. The numbers range from minus infinity to infinity, clustered about 0 with a standard deviation of 1. And a lot of times we want a lot of these numbers. Suppose you want 1,000,000 of them. Better not forget that semicolon. There, it didn't take long. Generated a row vector of 1,000,000 numbers distributed normally with a mean of 0 and a standard deviation of 1. Now let's look at this distribution using the hist or histogram function. Figure pops up and we see a nice little plot. You can see this bell curve here. The first argument is the set of numbers, the list of numbers. We've got 1,000,000 numbers there. And the second argument is the number of bins. So there's 100 bins divided up in a reasonable way. MATLAB does that. And you can see the number of points, actually the number of random numbers that was generated by randn. In this little range right here around 0 is very large, and it drops off as we get out here and they get more rare and more rare.
We've seen a number of ways to get random numbers from MATLAB. Now I'm going to tell you a dirty little secret about these random numbers. They're not random. For example, the first time we call rand after we start MATLAB, it returns 0.8147. That exact same number. Every time. Go ahead, try it if you don't believe me. Not all that random, is it? And why is that, you may ask? Well, a computer is a deterministic machine. Everything it does is determined by an algorithm. There's no real randomness involved. So you don't get a truly random number. Instead, the random number generator uses some fancy math to generate a pseudo-random number sequence. It's pseudo because it seems to be something that it's not. But the sequence of numbers that it generates sure looks random because there's no discernible way to predict the next number from the ones that came before it. For almost any purpose, unpredictability is all we need, and that's what we get. Well, almost. When we start MATLAB, the algorithm is initialized the same way every time, so it generates the same sequence every time. Now that may seem like a bad thing, since it always gives us the same numbers. In fact, it's a good thing. It's a feature, not a bug, as the popular saying goes among us programmers. It's a feature because it helps us during the development of our programs. When we're developing a program, we often use the random number generator to give us many thousands of test cases. And just as often, we need to see what happens when we change the program but use the same input. Well, the only way to do that is to generate the same numbers repeatedly. So, it's very useful that MATLAB generates the same pseudo-random sequence each time it starts. Of course, restarting MATLAB every time you need to restart the random number generator hardly seems convenient. So MATLAB provides a separate function that will reinitialize the random number generator for you without restarting MATLAB. It's called RNG, which you might guess stands for random number generator. It takes an input argument, and it uses that to determine the sequence that RAND will produce when you call it. It also uses a neat trick that lets you initialize randomly. This trick allows you to get a different sequence every time you run your program, even if you restart MATLAB in the meantime. All this may sound complicated. It's really not. Let's switch to MATLAB and you'll see.
Okay, to demonstrate this pseudo-randomness idea, I've quit MATLAB, and I'm going to restart and ask it for 3 random numbers. There, MATLAB's awake, and I'm asking for the 3 random numbers. And there they are. They look pretty random, I guess. Let me copy those to my clipboard. Now let's do that again. Let's quit and restart. You know, they look pretty familiar. Let's take a look at that clipboard. There. Yeah, that's the same numbers. Looks like every time MATLAB wakes up from oblivion, it starts all over at the same point. It's sort of like Groundhog Day. That was a great movie, by the way. So anyway, here's how to have a new Groundhog Day anytime you want it without quitting and restarting MATLAB. First, let's get rid of these numbers we pasted on here. And then I'm going to call RNG and give it an input of 0. Giving it that 0 as input resets the random number stream to the beginning, right where MATLAB always starts it when it first opens up. So we get the same numbers. You can use any other non-negative integer to start at a different place in the pseudo sequence. 1, for example. There, that starts us at a new position. And by the way, RNG sets both rand n for the normal distribution and randy for the integers too. Let's look at those. I'm putting them all in brackets here so that they'll be on one line in one vector. And I gave randy one argument. When you do that, it gives back one pseudo-random number, I should say one pseudo-random integer, ranging from 1 to that argument. And you can start at that same point in the random sequence anytime you want to. We gave rand a 1 twice, so we started at that same position twice and got the same numbers both times. Or you can start at some other point. I went up arrow to get that command back, and I'm going over here to change this 1 to a 2. And of course, if I repeat that command, same random numbers again. If you want a more random sequence, an actual random sequence instead of this pseudo-random business, you can input a string, the string shuffle to RNG, like this. Let me go back, change my argument over here to the string SHUFFLE. Got to end that string with another single quote. Let's repeat that, see if we get the same thing. No, and let's repeat it again. We're getting different numbers in the sequence even though we're inputting the same argument to RNG every time. Well, how does that work? Well, it uses that trick I mentioned to start the pseudo-random sequence number stream at a random point. It does that by getting the current reading of the system clock to generate a truly random number. Since that clock has microsecond resolution, this is all but guaranteeing a random sequence that'll never be repeated. Lots of stuff into the command window in response to MATLAB's little double greater than prompt here. I'm going to clear all that away. Clear the workspace and clear the window there. Nice clean slate. What if you wanted to have your function get input in the same way that MATLAB gets it in the command window? In other words, your function would print a prompt in the command window and allow the user to type input into it. Well, you can make that happen by using the function named input. Let's illustrate it in a function that we'll write called one more. Let's see. There. It won't take any input arguments, but it will return one output argument. I call that A. And here's the code inside. The argument to input must be a string, so you have to type something inside single quotes. Let me give it just one more command inside this function, and that's it. So let's run it and see what happens. Well, the first thing that happens is give me a number, buddy. Prints out. Whatever you put in quotes here shows up first, and then you see this blinking bar, this blinking vertical bar at the right, which says to the user, look, are you going to type something or am I just going to wait here forever? And wait it will right there in that state, probably forever until your computer burns up, blinking away until the user types something and hits enter. Of course, you can stop it with a Control-C, but we're going to give it pi/2. I hit enter or return. MATLAB evaluates pi/2 inside the command window, gets 1.5708, and feeds that to the function input. Input then returns that value, so it shows up right here on the right side of the equal sign inside the function. That value, 1.5708, is then copied into X in this assignment. Then the last statement in the function adds 1 to 1.5708, gets 2.5708, and assigns that to A. Finally, one more returns with the value inside A that's 2.5708, which is one more than the user typed in, hence the very clever name, one more. The sequence of characters that begins with the G in gimme and ends with the space after the colon, here to here, is a prompt. It's a little fancier than two greater than signs, like down here, but it's still a prompt. Whatever prompt you want input to print for you is fine, but you have to give it a string or it'll cause an error. And what the user types down here where the blinking vertical cursor is has to be a MATLAB expression that's legal. It could be a number, a variable, a vector, a matrix, even a string, and it can involve arithmetic operators, function calls, and so on. It just has to be a legal expression. Once the user hits enter, MATLAB evaluates the expression and hands it to input. Then input returns it as an output argument. In this particular case, it's assigned to X. Note that MATLAB pays no attention at all to what's written in this prompt. Regardless of the type of object that the user types in, all those things I just mentioned, it'll be accepted. The fact that the prompt tells the user to put a number in means nothing to MATLAB. It's of no consequence. A program's work is of no use to anyone unless it communicates its results to the outside world. So far, we've taken advantage of the fact that a command that's not followed by a semicolon automatically has the value that it calculates printed to the command window. MATLAB provides a far more sophisticated way for printing with the fprintf function. Here's a very simple example which you saw at the end of Lesson 3. There. It prints its string to the command window. Well, except for the backslash and the n, which together have a special meaning in fprintf. We'll look at that in just a minute. It can also print to a file. We'll explain the requirements for printing to a file later. For now, we'll concentrate on printing to the command window. fprintf requires at least one argument. Its first argument is a string. But it's not just any string. It's called the format string because it specifies the format in which printing is to be done, such as the number of decimal places to be used for printing numbers, the horizontal spacing, the vertical spacing, etc. It includes the words that are to be printed along with the numbers. In this first example, the backslash and the n together, we call that a backslash n, specifies vertical spacing. It means go to a new line. The n is for new line. Let's see what happens if we omit it. I'm going to hit up arrow, space over here and get rid of the n and hit return. You see the difference? The prompt appeared immediately after the last character in the string, right after the 3. But when we had the new line specification, a new line was begun after the 3, so the prompt appeared on a new line all by itself. Let's put that new line specification back in. In fact, let's put a couple of them in there. Now you see the difference? Right here after the 3, we had a new line which brought us here, and then we had another new line which brought us here, and then came the prompt. Okay, that's how to print a string with fprintf and how to make it skip to a new line. But we need to look at this function more closely because we need to see how to print variable values with it. When you want to do that, which is most of the time, you include the names of the variables that you want to print as additional input arguments after the format string. We'll illustrate how it works with an example function called checkout. I've got it typed in already, saved in an M file. Here it is over here. I can load the M file simply by double-clicking on it in the current folder window. I'll do that. And here it shows up in the editor. I'll explain it in a minute, but first I want to just go ahead and run it. There. I gave it two arguments, 3 and 2.71, and it printed out 3 items at 2.71 each. Total equals $8.13. The numbers that I gave as arguments are passed in as input arguments and are copied into n and price, as usual. So inside the function, n has the value 3 and price has the value 2.71. And then total is calculated by multiplying them together here. And finally, fprintf is called. As in the typical case that I mentioned, there are additional input arguments to fprintf following the format string. So here's the format string, and here are the additional arguments. In this case, n, price, and total. And these 3 arguments contain the values that we want to be printed using the format specified in our format string here. When there are values to be printed, the format string will contain percent signs. You can see them here. And there's one for each argument to be printed. The first percent sign corresponds to the first argument to be printed. The second one corresponds to the second one, the third to the third, and so on. In this particular format string, there are 3 percent signs corresponding to the 3 arguments. The percent sign is called an escape character. You can think of it as causing fprintf to escape temporarily from printing each character in the format string and instead doing something special. In this case, the special thing it does is print 1 argument. After each percent sign is a format specifier. A format specifier is a sequence of characters that together tell MATLAB the precise format to use when printing the corresponding argument. The format specifier always ends with a letter, and there may be a number, often a decimal number, between the percent sign and that letter. For example, in this format string, the first format specifier ends with a D, and the other 2 each end with an F. And the second and third specifiers include numbers. The letter at the end, like the F here, is called a conversion character. It's called a conversion character because it tells MATLAB how the value of the argument is to be converted to printed output. The numbers here, the 5.2 in this case, provide a bit more detail as to how the printing is done, as we'll learn in a minute. This method of specifying the format of printed output and the function fprintf itself both come from the language C, which adapted them from earlier languages. And they've since been included in many other languages as well, including C++ and Java. So if you tackle these languages after you learn MATLAB, you'll have a head start on the printout. We're going to look now at what these specifiers did. But first I'm going to grab the border between the editor window and the command window and move it up a bit so we can see everything at once. There. Okay, let's look at the first specifier in our format string, %d, right here. The conversion character D means print using scientific notation, except for whole numbers, which will be printed without using either a decimal point or scientific notation. Here we see that n, this n here, which had the value 3, is printed as a simple 3, and here it is, 3, because 3 is a whole number. Following this %d is a space, then the word items, space at, space, then comes another % sign. So we see this space items, space, at, space. By the way, you can see all the possible escape characters and all the possible conversion characters by giving the command help fprintf or doc fprintf. But we're going to give you enough information to get you started. The next escape sequence is this %.2f here. The conversion character f means print using fixed point notation instead of scientific notation. So that's just normal decimal notation. It's good for smaller numbers. The 2 after the decimal point here specifies the precision. It means that exactly 2 digits must be included to the right of the decimal point, even if they're all zeros. If you replace that 2 by a 0, then the fractional part and the decimal will be omitted. So we see down here the value in price, which was 2.71, is printed, and there are 2 digits to the right of the decimal point. After the 1 comes a space and the word each, which were copied from the format string. In computer science terminology, the combination of the percent sign and the format specifier is a special case of an escape sequence. An escape sequence is any sequence of characters that starts with an escape character and has special meaning. Well, after the word each here, we see the by now familiar \n, which we've learned means start a new line. Well, the backslash is another escape character. We've had the percent now and the backslash. And the 2-character sequence, \n, is another escape sequence. So, after the each, we start on a new line, and the next thing printed is total space equal space $sign. Total space equals space $sign. Then up here in the format string, we hit the 3rd percent sign. The 5 in this decimal number here means print using at least 5 spaces. Since F is the format specifier, these 5 spaces can include a minus sign if the number is negative, some digits before the decimal place, the decimal point itself, and some digits after the decimal point. In this case, 2 of them. If more spaces are needed, then more will be used. Here we need only 4 spaces to print the value that's in total, which is 8.13, because we have the 8, the decimal point, and the required 2 digits to the right of the decimal point. In a case like this, when fewer spaces are needed than are specified, some blanks will be inserted before the number. In this case, just 1 blank is required to use up that 5th space. It may have occurred to you that we may occasionally need to print a percent sign, or a backslash, or a single quote. 2 of these are escape characters, and the last one ends the format string. So how in the world do we print them? Well, you just put 2 together with no intervening space. Here, I'll show you in the command window, starting with the percent sign. Here we can see that these 2 percent signs printed out as 1 percent sign, while this single one was treated as an escape character introducing the format specifier .3f, which specifies fixed point representation with 3 digits after the decimal point, as happened right here. To print a backslash, use 2 of them with no intervening space. Backslash, backslash. Like this. So here's a backslash, backslash, which printed a backslash, and we even added a new line after here, which is why we needed 3 backslashes. And do you remember we got 1 more? How about a single quote? There. 2 in a row does it again. Formatting output in fprintf can be frustrating at first because there are many pitfalls. The most common pitfall is that strange things can happen if the number of percent signs doesn't equal the number of arguments following the format string. If there aren't enough arguments, then printing will stop at the first unfulfilled percent sign and the string will be truncated right there. Let's look at an example first with 4 percent signs and 4 following arguments, as they should be. That's fine. Looks like the beginning of a recipe for a big chocolate cake. One with a pound of butter over here. Well, watch what happens if we forget the last argument, that is, this 4. So now we just have 184 over here. There are 4% signs. And this time only 3 values to print. So fprintf gets to the 4th percent sign right here and doesn't know what to do. It prints 1 pound of butter, 8 tablespoons of cocoa, 4 cups of flour, comma, and prints the space, and then there's nothing left. In this case, it follows the safest path. When in doubt, leave it out, and it stops printing right there. There's no \n, so no new line. So what happens is the prompt just prints right here at the end. And what if there are more arguments than percent signs? Well, that's even more confusing. Let's put one too many. There are 4% signs, so let's add a 5th argument and see what happens. Wait, I think I need to widen the command window first. That'll be wide enough. Let me jump down 1 space, and there's my command, and there. 9 pounds of butter. That's a lot of butter. Well, what happens in this case is that MATLAB recycles through the format string to print the extra argument. So after printing 4 cups of sugar, here at the end of all of this, it's at the end of the string, it finds this 9. It goes all the way back to the beginning of the format string and starts all over. It uses this first %d to print the 9. Prints that, 9, then the space, LB space, butter, comma, space. It gets to this %d, and it's out of argument, so it stops right there. Again, it doesn't make it to the \n again, so no new line, so the prompt shows up right here at the end. There's a reason for this recycling feature. It allows you to print a whole vector of numbers with one format specifier, like this. Here I've put the format specifier 4.1f after this %, then a new line, and we got a vector with 6 numbers in it. So what's going to happen is this string here is used to print 1. We get to the end, we're ready for another argument. Comes back and prints again, then prints again, then prints again, then prints again. This is a special feature of the fprintf function in MATLAB. Both these pitfalls, too few arguments and too many, will plague anyone who prints with fprintf. I've got the scars to prove it. And there are even more pitfalls when you start printing character strings or use more sophisticated format specifiers. On the plus side, though, when it's behaving itself, fprintf is capable of some pretty fancy output. Well, while we're on the subject of fancy output, let's look at plotting. MATLAB has an extremely powerful plotting facility, and its workhorse is the built-in function plot. You may remember we saw it in Lesson 1. Well, we're going to go over it again, with a bit more detail this time. The easiest way to use the plot function is simply to pass a vector to it. So let's get a vector. This is just a list of the squares, the numbers from 1 to 10. And plotting it is done like that. And there we go, there's our plot. As we saw in Lesson 1, it shows up as a separate window. and it's labeled figure 1. We docked it last time like this. It shows up right here. So now we've got the command window visible. But I'm going to undock it. Now that covers up the command window. But if I click in the command window, it uncovers it. But where did it go? Well, it's still there. It's just behind. I'm going to move this down a little bit, or actually squeeze it down, and leave a little room up here. And then I'm going to resize this figure window and put it up here so I can see this figure, and I can have other figures laid out here. I think I'll start this one over to the left. Okay, so where was I? This is a half of a parabola. To plot both sides of the parabola, we can do this. So there's a little longer vector. It's the squares of the numbers from -10 to 10. Now I want to plot this one in a separate figure. If I just plot now, it'll replace the figure that I've got, and I don't want to do that. I want to compare these. So you may remember the figure command. I can type figure and I'll get a figure 2, or I can actually tell it I want figure 2. Either way, there's a new figure. And I can plot into it. There. Let's make this one about the same size as the other one. Note you can just change the aspect ratio too. And let's tuck them over here right side by side. So now we can see the whole parabola there. And you'll notice that MATLAB picks a range. Pick 0 to 10 here to get all the points. Pick 0 to 25 here. Well, you might wonder, shouldn't this go from -10 to 10? But no, all we did was give it the A, which is these numbers here, and these indexes here, these indices, go from 1 to 21, and they just represent the indices of the elements in A. To properly plot a mathematical function like this, we need to pass two vectors of the same length, one with the x values and one with the y values. Let's do that. T is going to be my x values, B will be my y values. So T goes from -10 to 10, and B is just the squares of those numbers. So let's get a new figure window. And let's move it over here. Size it the same as the others. And this time we're going to plot with two arguments. There. The arguments are vectors, the t and the b, and they have to be the same length. And they give the horizontal and the vertical coordinates respectively. So now we see that the range, or actually the domain down here, goes from -10 to 10, as we wanted it to do, and the range here in the y-axis goes from 0 to 100. Again, MATLAB picked these for us. It's also easy to extend this idea to put more than one plot in a figure. So sometimes you want to compare two plots right in the same figure. You can do this with plot because it's polymorphic. It accepts a varying number of arguments, as we've already seen. So let's do an example of that. We're going to plot x1 versus y1 and x2 versus y2 on the same plot. So let's get these vectors ready. There, I had these commands already typed out ahead of time to save us some time. Here we've got x1, and I space this out so you can see it starts from 0. It goes in increments of 0.1, and it goes up to 2 pi. And then the other vector, y1, is equal to the sign of these numbers. The sign is polymorphic. If you give it something of the shape of a vector, it returns something exactly the same shape. And that's great because we want x1 and y1 to be inputs to plot, and they have to be the same length. Here's another plot, x2 and y2. x2 starts at pi over 2. It increments by 0.1, and it goes to 3 pi. And y2 is the cosine of those numbers. x2 and y2 have the same length, so they can be plotted versus each other. x1 and y1 have the same length, so they can be plotted versus each other. And both these pairs, even though they have different lengths from each other, can be plotted on the same plot. Let's do that. Note that the order is xy, that is horizontal vertical, and xy, horizontal vertical. And here goes our plot. Note that the plot shows up in figure 3 in place of what was there because we didn't give the command figure again. Notice that there are two different colors. MATLAB picks the colors for you. There's a default set of colors. You can specify the colors, and we'll show you how to do that in just a second. But I want to point out that your version of MATLAB might choose different colors. MATLAB just recently changed its default set of colors. In an older version, the first one would be blue, the second one would be green. In this version, the first one's, I would say, bluish, and the second one is reddish. So let's change the colors to be, let's make the first one bright red and the second one black. And let's make the second one a dotted line. We can do all of this with one command. Let's get a new figure. And I'm going to repeat this command that I just did, but I'm going to alter it a little bit. After the x1, y1, I'm going to insert a little short string, quote, r, quote, comma. That's going to tell plot to plot this as a red line. And then here, for the second one, I'm going to put quote, k, colon, quote. This K is for black. Why not B? Well, B is already taken up for blue. And this colon means plotted as a dotted line. So here we go. And let's make this a little smaller. And tuck it in over here. I guess I'm going to have to move all of these a little bit. Nice and neat. So you can see that this is in fact a red line, and the default is that it's a solid line. And this is black. And if you look closely, you can see these dots. You can get lots more line styles with the command help plot. Let's do that. I'll scroll up a little bit, and there they are. Over here on the left, you see the colors. In the middle, you see the marks that you can, the markers that you can plot. And over here, lines. We haven't plotted any markers yet. Let's do that. In fact, we can mix all three of these together. I'm going to plot an example with one from each column in figure 1. Let's see, to do that, hit return here. I'll pick figure 1. When I do that, you'll notice that figure 1 got highlighted. And now I'm going to plot. I'm going to plot T and B again. I'm going to use an M for the color magenta, a double dash for a dashed line, and an O, that can be uppercase or lowercase, to put markers that are little circles on there. And here we go. Isn't that pretty? It's magenta, it's got the dashed line, and it's got these circular markers on here. Well, we've seen up here how to plot two things on the same figure. There's another way to do that. You can call plot multiple times and use the function called hold. Let's see how to do that. Let's do it in figure 2. We first make figure 2 the active figure with the command figure 2. So there. You can also do that by clicking figure 2 with the mouse. And we notice that it's highlighted up here relative to the other figures. Now let's replace the current contents of figure 2 with a new plot. So we type plot using the same x1 and y1 that we defined earlier. And there it is in red, which is what we requested. Now we give the command hold on. Once that command is given, all subsequent plots to figure 2, which is the figure that was active when we gave the hold command, will be made on the same axes in that figure. The previous plot won't be replaced. So let's do that. We'll plot x2 and y2 this time. And let's, as we did before, use a black dotted line. There. And notice that the range of the axes were adjusted accordingly. Just like when we plotted everything in one fell swoop with one call to plot. When we're ready to replace the current plot in figure 2 with something else instead of adding to it, we give the command hold off. When the command hold off is issued, all subsequent calls to plot while figure 2 is active will replace the previous plot in that figure instead of adding to it. So watch figure 2 while I replot x1 and x2 with, green asterisks. That's a little garish. Anyway, as we showed you in lesson 1, there are additional plotting options, not reachable through the plot function itself, that you can get via separate functions. These options will enhance the visual quality of a plot that's already plotted. Let's apply some of them to the plot in figure 3. There, that's the active figure now. You may remember that grid turns on a graph paper like grid. Repeating the command turns it off and on. And like hold, it can be used with the terms off and on as well, but we'll use it without this time. Let's see, grid. And you see this grid shows up here. And now grid again. Turns it off. And one more time, because I want it on. There. Now it's on. And you may remember the title, X label, and Y label commands. Let's do those again. And there, things are nicely decorated, as you can see here. Another handy function is the legend command. It'll insert a legend right there in the figure with a note about each separate plot in the figure. Let's do that one. There, up here you see blue line here corresponding to this, or bluish, it's the same shade, and the word sign, and then the reddish line that corresponds to this one with cosine. And the order of these is the same. The order here is the same as the order in which we plotted them. So what you just need to do is remember that the first thing we plotted was a sine and the second was a cosine. And the legends will be straight. If you want this legend to appear somewhere else, in this case it was a nice blank spot up here. That's where it showed up. But if you want it here or somewhere else, even just outside here, next to the plot, you can do that. You need to just check the options in Help Legend. And finally, we'll remind you that you can control the range of the X and Y axes with a function named axis. Let's do that. Axis takes one argument, which is a vector of 4 numbers, with the left and right limits, right here of the plot, followed by the lower and upper limits, right here. Please note that despite the fact that it affects both the X and Y axes up here, its name is axis. I probably mistyped this command as AXES 100 times. There is an axes command, but it's far more sophisticated than the work that one normally needs to do. You probably won't want to use it. Anyway, watch figure 3 up here change when I hit return. Okay, 1, 2, 3. There. As always, you get more information about this function or any function with either the help command or the doc command. Okay, that's it for our second installment on plotting, except for closing the figures. You can do that with the function close, either one at a time like this, figures 4 and 1 are gone. You can't get them back, except by repeating the commands that did the plotting and the decorating. And you can close all the open figures at once with the close all command, like this. Now that I've got all this room, I think I'll stretch the desktop back to full size. And I think I'll clear everything. There, all done with plotting. The sad fact of life is that it's easy to make mistakes when writing. Humans are pretty good at filling in the blanks, so when we read a story, we can understand it even if it has typos or missing words, grammatical errors, and such. When you're writing instructions for a computer, you have to be very precise, and your grammar must be 100% correct. A happier fact of life is this: the easiest programming errors to make are syntax errors, and they're also the easiest ones to find and fix. It's easy to forget a comma or a square bracket, for example, but when you do, MATLAB will complain with one of those red error messages, and you can fix it. But semantic errors are more problematic. You'll remember that these happen when what you wrote is legal, but it doesn't do what you meant for it to do. Sometimes MATLAB can catch these semantic errors. For example, suppose you have a 10-element vector. You want the last element, but you ask for the value of the 11th one. MATLAB will stop you with an error message, and you can fix your program. What if you ask for the last element when you meant to ask for the first one? Well, your program may run just fine every time and give the wrong answer every time. In cases like that, the results will usually be consistently suspicious, and you're likely to realize that something's wrong. Finding the source of the problems may be difficult, but knowing that there is a problem is a big step toward solving it. Some semantic errors may cause problems only occasionally, though. That typically happens when only a certain combination of inputs triggers the error. This is the hardest case of all. First off, you may not notice the problem, and second, it's hard to find the cause. For that reason, it's very important to test your program with a wide variety of inputs. In fact, you should think hard about the possible problem cases for your program, and you should test all the ones you can think of. If one of these cases causes an error, then you need to find it and correct it. Many times, however, finding it can be surprisingly difficult. Fortunately, MATLAB can help you with a tool called the debugger. The name bug is synonymous with error in computer programming. It comes from the early days of computers when an actual insect caused a problem in one of the first computers. The name stuck, and now any tool that helps you remove errors is called a debugger. So let's see MATLAB's debugger. And if we want to use the debugger, we got to have some bugs, to debug. So let's practice making some errors. Remember what happens when we do that? Well, let's start with a few intentional syntax errors to refresh our memory. Wow, that's a lot of red text, but it should be familiar red text We made this same mistake in Lesson 1 when we first introduced the concept of syntax and syntax errors. And naturally, we saw the same exact error message. MATLAB is nothing if not predictable. It's telling us that we messed up the assignment. Of course, you know by now that it should have been x equals 1 and not the other way around. So how about this error? A little less red here. Undefined function RAMD. Again, MATLAB is not shy about telling us that we've fouled up. It can't find a function named RAMD because we didn't make a function named RAMD, and it knows darn well it didn't make one. So, of course, we got our hands slapped. Well, hey, we just misspelled RAND. Aren't you smart enough to figure that out, MATLAB? As a matter of fact, sometimes it is smart enough. For instance, suppose we just typed an extra D in the name. MATLAB yells at us in red, and then quickly calms down and politely asks us in black if we meant RAND. Well, yes, thank you. That's exactly what we meant. And all we have to do is hit return, and the function that it guessed we wants runs. Let's make an error that's a bit more serious. Okay, we've got Y. Let's look at the sixth element. What happened here? Well, we created a 5-element vector and then tried to access its sixth element. There's no such thing, so MATLAB let us know. It's important to realize that this was not a syntax error like the previous ones. Y of x is a perfectly legal MATLAB expression. But when MATLAB tried to execute it, it realized that in the given context, it was illegal from a semantic point of view. This is called a runtime error, because MATLAB can catch it only when it tries to execute it. We should be happy when we see this red stuff, even though I'm usually not, because it means that an error that we made was caught before it could do any serious damage to the output or, to people who depend on that output. MATLAB spotted a bug, and once we know where it is, we can eliminate it. Sometimes MATLAB is happy most of the time when we run our program, but on some input combinations, it runs into a runtime error. We may be thinking our program is perfect and everything is rosy, and then out of the blue, MATLAB hits us with an error message. That's always discouraging, but again, we can be thankful that it caught a problem. Unfortunately, though, as we've pointed out before, many bugs are such that MATLAB will never know that there's an error. It simply executes the statements we provided and gives us the wrong answer. The best we can hope for in that situation is that perhaps we can tell that the result is not what we expected. Then we need to figure out where we messed up. Both of these latter errors can be very hard to find, and if we don't find them, we're doomed to failure. And that's when the debugger can be our only hope of salvation. That may sound overblown. It's not. Let's consider this simple function. It roughly mimics the behavior of the built-in Randy function. In fact, it uses Randy, as you can see here. It's supposed to return an n by m matrix of random integers, right here in X, and print out the last number on the last row. It uses fprintf to do that. The last number on the last row, since it's an n by n matrix, that's element n by n. Yeah, that looks right. Well, let's try it. Well, that looks pretty good. It's 3 by 3. They look random. Last element on the last row is 3. The only thing I'm noticing here is that we only get integers 3 and smaller. Wonder why that is. Let's try it with a different input. Well, we're in trouble right there. Index exceeds matrix dimensions. Error in rand int line 3 fprintf. So, by the way, the first thing to notice is that these are live links. If I click on this line 3, it takes me to line 3. Well, what do you need that for? I mean, it's obvious these lines are numbered here. Well, the advantage of that is if you have a really long function, then it'll take you right to that point and you don't have to scroll around. When I'm looking at it, I know the error is here. I know I've got an n by m matrix. How can this not be legal? How am I exceeding? It'd be nice to see what the size of x is. It was 3 by 3, right? But there's no x here because the workspace doesn't have the local variables in it. It just has the variables in the command window. Well, I'm at a loss. It's time to use the debugger. The most important feature of any debugger is the ability to put breakpoints in your program. You use a breakpoint to mark a line in your code that you want the debugger to stop executing the code at. It's called a breakpoint because it breaks the flow of execution at a chosen point. To create a breakpoint, you simply click in the gray area between the line number and the given line on one of these dashes. Let's do that on line 3. The red circle indicates the location of the breakpoint. It's sort of like a red stop sign. We're going to stop right there. It'll stop before this line is executed. And we want that because that's where the error was. And you can have more than one breakpoint. You can have one on any line where there's a dash, on line 2, for instance. There. I think that might be a better place to stop, so let's get rid of the one on line 3. We don't need that one. To remove it, simply click on the red circle. It's gone. Okay, let's go back to the command window and call our function again. Call it the same way we did last time. The function begins to run, then it stops. And there's this little green arrow next to our breakpoint. What happened is that the debugger paused the execution of our function just as the code pointed out by the green arrow was about to be executed. Now we have several options. We could simply continue running the function by clicking the Continue button up here on the toolbar, or by hitting the F5 key on the keyboard. Instead, let's execute just the current statement by clicking the Step button right here, or you can do that by hitting the F10 button. So I'm going to click that and watch the arrow advance. There. And something happened over here. X showed up. Wait a minute, M, N, and X. These are local variables. We've never seen local variables in a workspace. Well, this is a great thing about the debugger. When you're stopped inside the function, the workspace that's shown over here is not the command window workspace, but the workspace of the function that's active. This is the workspace of rand_int. These are the local variables in rand_int. Let's see. Now that we're looking at this, X is not a 3 by 2 matrix at all. It's a 2 by 2 matrix. So wait a minute. We just gave it 3 and 2. Oh, and note the handy little yellow windows that the debugger pops up to show us the value of variables that we hover the mouse over. And we know that Randy makes a 3 by 2 matrix in that case. Doesn't it? Okay, maybe it's time to look at how Randy works. We can do that with a help function. But before we do that, notice this blue 2 down here in the command window. That number and x equals Randy of n, comma, m told us the line at which the function was stopped by the break and the code on that line. The blue color in the underline right here mean that this is a live link that will take us to that line when we click on it. And more importantly, notice that the prompt has a K before the 2 greater than signs. That K means that you can do things with the keyboard while the function is active. Yes, the function's active, but we're controlling it. It's like a person in a hypnotic trance who does what we tell it to do. Ordinarily, while a function is running, you can't communicate through the keyboard with it, or with MATLAB in general. But you wouldn't realize that because the function is over so fast. You will realize it, though, if you have a function that runs long enough to give you a chance to hit a few keys before it returns. When you do that, you'll see the characters that you type in the command window down here, but they'll be ignored, except for one magic combination. You remember what that is? That's the magic combination that will stop the function cold. It's Control-C. Everything else will be ignored. Anyway, this K always appears in the prompt when the function is stopped at a breakpoint. And when it's there, we can use the keyboard to make things happen. For example, we can look at the value of one of the variables in the function's workspace. Let's look at, say M. Well, we knew its value was 2, but it's fun to look at it. You know what's more fun? You can change it. Let's make it pi. Now M is equal to pi, and I want to emphasize that I'm talking about the M in rand_int. The input argument that was set to 2 when the function was called has been changed to pi. And look over here, there it is, pi. Remember, this is the workspace of the active function here. Of course, if we continue this function by hitting, say, the continue button or the step button, pi is the value that will be used right here inside fprintf when it's executed, and we'll get a new error saying that an index has to be a positive integer. That would be no help, but peeking at variables like this or changing them can sometimes help you figure out what the problem is. For example, if we'd have looked at x, we'd have seen that it's 2 by 2 instead of 3 by 2 as we expected it to be. We already saw that in the workspace window, but it's more obvious now. Okay, let's refocus here. We were going to get help on Randy. Let's do that. Let's scroll up to the beginning. There. Randy, pseudo-random integers from a uniform discrete distribution. R equals Randy, I max, comma, n, returns an n by n matrix. There's the problem right there. The arguments aren't the size of the matrix. Like what do we put? 3 by 2. That means the maximum value is a 3. That's what we saw. And the matrix is 2 by 2, which is what we saw. There it is, maximum value 3. Okay, there's our problem. We didn't know what Randy was doing. Okay, let's fix our little broken function. First, we need to quit the debugger. We can quit it either by typing db quit, that's for debugger quit, or by clicking the quit debugging button up here. It's the red thing. I'm going to click that button. And watch the green arrow when I click it. Okay, 4, 3, 2, 1, click. There. Green arrow disappears. And down in the command window, we've got our normal prompt back. You know, the one with no K. Now here's how we're going to fix our function. We're going to change x equals Randy of nm to x equals Randy of 10 nm. Note that this breakpoint turned gray when I did that. This is MATLAB's way of indicating that the breakpoints are inactive and you need to save your function before running it again. They'll all turn gray whenever you change the file, and they'll only turn back red when you save the file and it's got no syntax errors in it. Well, I don't think there's a syntax error here, so I'm going to click the little blue diskette over here to save the file right here, and you'll see the breakpoint turn red again. Here we go. There. Well, I can almost hear you complaining about the way we fix this function, because the change we made will mean that we've arbitrarily limited the range of pseudo-integers to go to 10. Good point. We can think about whether that's a serious problem, and if it is, how we might fix it. But in the meantime, let's just call that a feature of our function. Okay, ready to see whether it works now? Well, we'll leave that up to you. Try it. Try it with several different inputs. If it is working, then we can say, "Thank you, debugger." If it's not working, then you'll know how to find the bug and fix it. And then you can thank the debugger. As you might guess, MATLAB has extensive documentation on its debugger. You can get a good start on that by typing debugging into the little query box here. And then coming down here and choosing Debugging Diagnose Problems with MATLAB Programs. And you get lots of information right here, examples, and so on. Well, that's it for the debugger for now. But when we start writing more complicated programs in later lessons, more bugs will inevitably appear in our code, and you'll have more chances to practice with a debugger. And as you write more and more code, you'll get more and more practice, more than you might expect. And that brings us to today's message about life as a programmer. After you finish this course and begin to write more sophisticated programs on your own or with collaborators, whether it be for fun, for another course, or for your employer, you'll find that most of the time you spend on programming is debugging time. In fact, it's worse than that. Only a small fraction of programming time is spent typing what we think is correct code. The great majority of time is spent finding and removing the errors that we made while we were typing what we thought was correct code. And now for the most important part of the message. Programming is a very humbling experience. It shows us, as well as any exercise I've ever seen, just how imperfect we humans are. Wait, did I say humbling experience? Make that humiliating experience. And it can be very discouraging too. In fact, if you don't get discouraged, then either A, you aren't writing serious programs, or B, you aren't human. If you are human, and you can endure the humiliation of making 99 errors before you get one thing right, then you should make a good programmer. And you won't have many competitors, because most people will give up after a mere 10 errors. I'm convinced that this single factor is the reason that programmers are paid so much money. Everyone else gets discouraged and quits. But hang in there, because programming is also an exhilarating experience. When you finally get a big program working, and it works its way through inputs that it's never seen before, making decisions and doing calculations that would take 1,000 people 1,000 years to do, and when it carries out all those billions of calculations flawlessly and spits out the answers, you'll forget all the hours of humiliation that preceded it. And when you get there, it's a feeling that is amazingly wonderful. Well, you just have to experience it for yourself to know what I'm talking about. If you do, then this course was worthwhile. But frankly, most of the credit must go to, well, can you guess? Right. Thank you, debugger. And with that thank you, we'll end lesson 4. Lesson 5, Selection. This week we'll be talking about how to make your program run differently based on different conditions. So far, MATLAB has executed the statements that you gave it in the order that you gave them. In other words, it used sequential control. That's its default behavior. Sequential control is the most natural and the most common sequence in any program written in any programming language, and it's the primary example of a control construct. A control construct is just a method used by MATLAB to select the next statement to be executed after it's done with the current one. In this lesson, we'll introduce some constructs that tell MATLAB to select its next statement based on some condition. A construct that does this is called selection, or some people call it branching. The most common selection construct is the if statement. Let's introduce it with an example. The guessMyNumber function is a single if statement. It starts with the if keyword, followed by the condition x equals 2. This pair of equal signs is a new operator. It means equal to, or is equal to. The statement that follows the line with the if keyword will be executed if and only if this condition is true. In this case, if and only if x equals 2. The if statement is terminated by the end keyword. Let's see this function in action. And here it is in the editor. Let's try it with a few bad guesses. How about running it with 3? And how about 0? Nothing visible happens. Now it's how it's supposed to be, since our function doesn't do anything with a bad guess. It evaluates the x double equals 2 condition here, and if it's false, as it would be if x was 3 or 0, it skips this fprintf here inside the if statement, and then the function returns. Now let's try it with a correct number. We should see something different. Indeed we do. We see the congratulatory printout. The condition was true this time. X is 2. X double equals 2 evaluates to true. So we executed the fprintf statement inside the if statement, and the function ended again. The control flow of the if statement is best illustrated by a figure. The blue dot represents the control statement, in this case, the if statement. The blue lines with the arrows show the possible paths that MATLAB can follow. The branch that goes off to the left represents the case when the condition is true, that is, x equals 2. The box labeled block represents the set of statements inside the if statement that will be executed if this branch is taken. The right branch represents the case when the condition is false. In that case, we go straight to the next statement after the if statement, that is, after the end keyword that terminates the if statement. This figure highlights in red the flow of control when the condition is true. And as you can see, in this case, MATLAB executes the block of statements inside the if statement. This figure shows the case when the condition is false. This time the red line shows that we skip the block statements inside the if statement and jump past it to the statement after the if statement. What if we want to do something when the condition is false as well? In other words, what if we wanted to execute one set of statements when the condition is true and a different set when it's false? Let's improve our guessMyNumber function just a tiny bit by trying to cheer up the poor user who picks the wrong number. Both the function and the if statement start out the same way as before. But after the first fprintf statement, we see a new keyword, else. This else has two roles. First, it signifies the end of the block of code that needs to be executed when the condition is true. And second, it signifies the beginning of the block of code that needs to be executed when the condition is false. This new statement is called an if-else statement. As you can see, our new and improved guessMyNumber function prints out an encouraging message if the user's guess is wrong. The control flow of the if-else statement is illustrated by this figure. Here again, the blue dot represents the control statement, in this case the if statement, the if-else statement. And again, the blue lines with the arrows show the possible paths that MATLAB can follow through the statement. The branch that goes off to the left represents the case when the condition is true, that is, x equals 2. The box labeled block 1 represents the set of statements that will be executed when this branch is taken. These statements are the ones that come before the else keyword. The branch that goes straight down represents the case when the condition is false, that is, x is not equal to 2. The box labeled block 2 represents the set of statements that will be executed when this branch is taken. And these statements are the ones that come after the else keyword. This figure highlights in red the actual flow of control when the condition is true. As you can see in this case, MATLAB executes only the block of statements that come before the else keyword. And this figure shows the case when the condition is false. This time, the red line shows that we skip the statements inside block 1 and instead execute only block 2, which is the set of statements after the else keyword. Okay, let's try this function in MATLAB. Here's our new and improved version in the editor. Let's take a wild guess and guess 3. Like we did before. And, well, this time we get a little bit more information. Not right, but a good guess. MATLAB, of course, evaluated this exact same condition. 3 is equal to 2, and again came up with false. But instead of just quitting, this time it went to the statement, or the block of statements, in this case just one of them, immediately after the else keyword, and that brought us to the fprintf, which printed out this little bit more encouraging message. Now, what happens if we guess right? Well, let's do that. Let's go right straight to that, and we get the congratulatory message. The opposite happened this time. The condition evaluated to true, so the statement immediately after the condition executed. To recap, when an if-else statement is in our program, we're guaranteed that it will execute exactly one set of statements. Either the statements between the condition, here, and the else keyword, here, and that's carried out when the condition is true, or the statements between the else keyword and the end, which closes the if-else statement, when the condition is false. Okay, that's it for the if-else statement. But guess what? There's one more version of the if statement. And here it is in a third version of the guess my number function. It's the last one, and that's a promise. One change that has nothing to do with the new version is that the number 2 here seemed boring. So we changed it to 42, which I'm sure you'll agree is far more interesting. More importantly, we see a new keyword here, else if. This is an if, else statement. There has to be a condition after the else if. In this case, we have x less than 42, just as there had to be a condition after the if keyword, x double equals 42 in this case. You can probably guess how this thing works. Let's suppose x is equal to 42. Then we carry out this statement here and we're done. Let's suppose it's false. Then we skip that. We come to the else if and we check if it's less than 42. We carry this out. Let's suppose that's false. Then we come down and we do the else part. Let's call the function with 41. The first condition with x equals 42 was false, so MATLAB checked the second condition, the one after the else if keyword here. That turned out to be true, so we printed the too small message. If we run it with 43, you can see that we get the too big message. That's because x was neither equal to 42 nor less than 42. So both of these failed, and we went to the else condition. A few remarks about this version of the if statement. First, the else branch is optional, just as it was before. You can simply omit the else and close the if-else if statement with the end keyword. And if we leave that branch off, like this, I'm just going to hit delete now, we're left with an if-else if statement. Second, whether you have the else branch or not, you can have as many else if branches as you want. They come one after another, right in here. We'll see an example of this a little later. Okay, counting the if-else if statement that you're looking at right now, we've seen 4 versions of the if statement. An if, an if-else, an if-else if-else, and an if-else if. To understand how these various versions of the if statement are related, you can think of each of them as a fork in the road when you're driving. The most complicated one is the last one we saw before this one. I can get back to that by coming up here and hitting this undo button, and there we are. This is a fork in the road with 3 branches. 1, 2, 3. You're going to drive down one of these forks to get to the next statement in the program. If you drop the else if, again I'm going to hit the delete, then there are just 2 branches. If you add more else ifs, there will be more branches. And regardless of how many else ifs there are, even if there aren't any at all, if you get rid of the else, then when all the conditions are false, you'll just detour around the fork and drive directly to the statement that comes after the if statement. Okay, end of remarks and end of all these versions of Guess My Number. Promised that we were done with Guess My Number, but I didn't say we were done with if statements. I still need to show you an example with multiple else if branches. And I've got one here. It's called Day of the Week. And I can pop it up in the editor just by double clicking it. And here it is. It's a little longer, so I'll need to have some more space, and I can get that by just stretching the editor window down like this. Whoa, how long is this thing? Whoa, not much command window left, but at least we can see all of our function. Our new function will print the name of the day of the week when we call it and give it the number of the day of the week as an input argument, this number n. And it'll also identify it as either a weekday or a weekend day. We have a long if, else statement here because it has 6 else if branches. So counting its if and its else branches, it has a total of 8 branches. After this long if, else statement comes a separate if-else statement. As I mentioned, the function takes n, the number identifying the day of the week, as an input. The long if, else statement then checks n, comparing it one by one to the numbers 1, 2, 3, 4, 5, 6, and 7. When the first true condition is reached, let's say n is 3, we would print out the day of the week. In that case would be Tuesday. And then we set day type, a variable called day type here, equal to 1 if it's a weekday, or 2 if it's a weekend day. Here's a 2, here's a 2. The else branch here is just there to handle errors. If the input's not one of the integers 1 to 7, then none of these first 7 conditions can be true. So we take that else branch. And in that branch we print out an appropriate error message right here. And then we return from the function. We'll say more about this return keyword a little bit later. This second if statement, this if-else statement down here, is here to tell the user whether the day is a weekday or not. It checks the day type variable, and if it's equal to 1, it prints which is a weekday. Otherwise, it prints which is a weekend day. In either case, after the Y here of the word day, we included a \n. This is the escape sequence, you'll remember, that puts us to a new line. We wanted to get ready for the MATLAB prompt. Notice, though, that we omitted the new line in all the F statements above. And we did that so when the name of the day and the comma are printed out, this text following it, which is a weekday or which is a weekend day, will be on the same line. And notice one last detail about the printing. We included a space here before these whiches so that there will be a space between this comma after the weekday or weekend day name is printed and this phrase, which is a. Well, it's time to try this function out. Well, we note that this is an American function. The week starts on Sunday. And that looks good. Wednesday is what we would expect. We put in a 4. Let's see, Sunday, Monday, Tuesday, Wednesday. Yep, that's right. And we can see that Sunday's identified properly as a weekend day and Wednesday as a weekday. So far, so good. So we've tried a weekend day, we've tried a weekday. Now we need to make a mistake and see if we handle errors properly. Well, it handled the error just right. It's passed all the tests. I'd say this is a working function. Well, it handled the error just right, and it did that because of the return statement inside this else branch. Return is not only a keyword, it's an entire statement. And it does just what its name suggests. When MATLAB executes the return statement, it immediately quits the function and disregards all the other statements following it. The most typical use of the return is exactly what we're doing here. We encounter an error, and it's time to quit the function. Functions normally quit only when they reach the end of their statements. But you may want to have a function return earlier, either because of an error, just like this case that was detected before the end of the function is reached, or simply because the function's done with its work before the end is reached. In either case, the return is what you need. Let's just remove the return statement for a second and see what happens with this bad input. I'm going to hit delete here. So let's just run it again. Since that's the last thing we did, all I have to do is hit up arrow and return. And what did we get here? Let me stretch this up a little bit so we can see better. We got the error message. Number must be from 1 to 7. But then this is an ugly result here. This ugliness happens because day type is not assigned a value and the input is out of range. None of these else ifs or this if happens, and so none of these assignment statements take place. Day type equals. Since it doesn't have a value, MATLAB has forced to step in and take charge. This sort of behavior is termed an ungraceful exit, and it's an embarrassment for any self-respecting programmer. But with the return statement in there, and let's put it back, there. The function ends gracefully, and that's how all nice functions behave. So let's do it one more time. There. The return statement is a convenient way to handle this situation, and indeed it's a convenient way to handle any situation for which there's nothing more that a function can do or needs to do.
We've seen quite a few variants of the if statement. Let's summarize what we've learned. The simple if statement has a condition and a block of statements that's executed if the condition is true. If the condition is false, then the statements in the block will not be executed. The if-else statement lets you specify a block of statements for the case when the condition is false also. So there's a separate block of statements for each of two cases, that is true or false. Because of that else branch, exactly one block of statements will always be executed. The if-else if statement lets you specify multiple conditions that are checked one by one until the first true condition is found. Then the corresponding block of statements is executed and MATLAB skips to the end. If none of the conditions is true, then none of the statements in the blocks will be executed. The if-else statement is very similar to the if-else if statement. The only difference is that we add an else branch after the last else if branch. The else block at the end will be executed only if all the previous conditions are false. But because of that else branch, exactly one block of statements will always be executed. We've been doing comparisons in the conditions of if statements with expressions like x == 2.
The double equal is an example of a so-called relational operator. Relational means that the result depends on the relation between the operands. This table lists all 6 of MATLAB's relational operators. We've seen how to use these operators inside if statements. What may be surprising is that they can also be used outside if statements. And they produce values. Let's take a look at this other way to use relational operators. Let's see. 10 double equals 20. Answer equals 0. 3 double equals 35 minus 32. Answer equals 1. In the first example, we asked MATLAB to calculate the value of the expression 10 double equals 20, and it told us that the value is 0. In MATLAB, when the operator double equals finds that its first operand, like 10, is not equal to its second operand, like 20, it returns the value 0, which means false. In the second example, we found that the value of the expression 3 double equals 35 minus 32 is 1, because 35 minus 32 is 3, and so 3 double equals 3 is true. And when the double equals operator finds that its first operand is equal to its second operand, it returns the value 1, which means true. In fact, every relational operator returns 0 when its expression is false, and 1 when its expression is true. And when we say 0 and 1, we mean the numbers 0 and 1. Here's an example to drive home the fact that the result of a relational operation is a number. In this expression, 16 times 64, which evaluates to 1024, is greater than 1000. So the relational expression in parentheses evaluates to 1, which is true, of course. We then add 9 to 1 and get 10. So the value of 16 times 64 greater than 1000 is a 1, a normal 1, the kind of 1 that you can do arithmetic with, not some special 1 that has some special sort of truthiness attribute attached to it. The parentheses have an important effect here. If we omit them, we get a different answer. This time the addition operator is executed before the greater than operator. That happens because the precedence of plus is higher than the precedence of greater than, so this operation is carried out first. In fact, all the arithmetic operators have a higher precedence than all the relational operators. We'll talk more about this later in this lesson. So the result of the addition is 1009, but the value of the operand on the left of the greater than sign, which as before is 1024, is still greater than the value of the operand over here on the right, 1009. So the relational operator produces the value 1, which means true, as before. Since nothing's added this time, the result of the entire expression is 1. Let's take a look at this little function called if-test, which helps us test what MATLAB considers true and what it considers false. This function uses an if statement to decide whether x, the input argument here, is true or false. If it's true, it prints it's true. If it's false, it prints it's false. Let's try calling with a few different values. Well, 0 is false. We knew that. Let's try it with 10. 10 is true. It's non-zero. What about minus 1? It's non-zero, but it is negative. Now, it's non-zero, so it's true. And 1, well, we knew that was true too. What about this? That is a small number. Wonder if it's big enough to be true. It's awful close to 0. True. You can easily see the pattern. If it's 0, MATLAB takes it as false. For anything else, be it negative, integer, or not, big or small, MATLAB takes it as true. Okay, we're done with our if test function. And we don't need this stuff anymore. But we're not quite done with relational operations. There's one important feature that we need to look at. Relational operators work on arrays too. First, let's remember how array operations work. Let's do array multiplication on two vectors, like this. MATLAB applies the dot star operation to each corresponding pair of elements. First, 4 times 5 gives 20. Here we go, 4 times 5 gives 20. Then minus 1 times minus 9 gives 9. Minus 1 times minus 9 gives 9, and so forth. And the resulting matrix is the same size as the input matrices, which in this case were 5-element row vectors. Now let's replace the array multiplication operator with the relational operator, the greater than, like this. As with the dot star array operator, MATLAB applies the relational operation one by one to each corresponding pair of elements. First, 4 greater than 5 gives 0. So here's the 4. Greater than 5 gives 0, since 4 is not greater than 5, and 0 represents false. Then minus 1 greater than minus 9 gives 1, since minus 1 is greater than minus 9, and so forth. And again, the resulting matrix is the same size as the input matrices, 5-element row vector. As with the arithmetic array operators, the two operands of the relational operators must, in fact, have the same exact size, except for one special case. It's the same special case we saw with the arithmetic array operators. And that's when one of the operands is a scalar, like this. In that case, each element of the array in turn serves as one operand of the relational operator, while the single scalar serves as the other operand, and the result's an output array of the same size as the input array. So 4 less than or equal 4 is evaluated, which is true and gives 1. Then minus 1 is less than or equal 4 is evaluated. That's true, that gives 1. Then 7 is less than or equal 4, which is false, gives 0, and so on. And the result is an output array that's the same size as the input array. And finally, look at this tricky one. Can you see what we're doing here? We're counting the elements in the vector that are equal to 14. As you can see, there are 2 of them, here, and we got the right answer, 2. Can you see how this works? First, the argument to sum is evaluated. That's this thing in parentheses here. It's an expression involving a relational operator, double equals, that has as input a vector and a scalar. As we've just seen, the relational operator compares each element of the vector in turn to the scalar. Since the relational operator is a double equals, we'll get a 1 for each element that is equal to 14 and a 0 everywhere else. Since there are 2 of them equal to 14, we get 2 1s and 4 zeros as our output. Now you don't see that vector, but you know it's there. That vector of 2 1s and 4 zeros is then sent to sum as its input argument. Sum adds them up and gets 2. And the overall effect is to count the elements of the vector that are equal to 14. Cool, huh? This is a great example of MATLAB programming, a single line of code that does something that would take 5 or 6 lines in most programming languages. And if you're a MATLAB programmer, this version is clearer too. Let's recap the subject of logical values because it's a really important concept. If MATLAB is asked to consider a non-zero input as logical, it will interpret it as true. If MATLAB is asked to consider the input 0 as logical, it will interpret that as false. And when MATLAB outputs a logical false, it outputs the value 0. But when MATLAB outputs a logical true, it always outputs the value 1. Note that this means that you can give any value to MATLAB to be interpreted as logical. If you give it a value that's neither 0 nor 1, say 98.6 or minus 30, that's fine. MATLAB will treat it as true. But it will always return 1 for true and 0 for false. You may have thought about whether we can combine multiple logical values somehow. Yes, we can, using logical operators. The table here shows 3 logical operators. These are the operators that MATLAB has: and, or, and not. 2 ampersands mean and, 2 vertical bars mean or, and the single tilde means not. So how do they work? Not is a unary operator, meaning that it takes only a single operand. It simply flips the value given to it. If you give it a true, it'll return false. If you give it a false, it'll return true. And or are binary operators. They combine the value of 2 operands. The result of and is true if and only if both of its operands are true. Otherwise, it's false. Or works the opposite way. The result of or is false if and only if both of its operands are false. Otherwise, it's true. This table is called a truth table. It specifies how logical operators work in a bit more formal manner. The 4 rows show all possible combinations of input values. And there are 2 columns of outputs, one for and one for or, over there on the right. They show the result of the operator for each input combination. And here's a version showing the inputs from the standpoint of MATLAB, where 0 means false and non-zero means true. As you can see, there's a 1, which means true, in the and column, only when both inputs are non-zero. And there's a 0 for false in the or column, only when both inputs are 0. Now let's see some examples. Suppose we want a function that takes 3 inputs and returns one of the following 3 values. A 1 if its 3 inputs are in increasing order, a -1 if they're in decreasing order, and a 0 otherwise. Well, we've already written a function that does that called order3 over here. Let's have a look at it. It uses an if, else statement with the logical and operator, here and here. And here's how it works. The first condition in the if statement says x less than or equal to y, ampersand, ampersand, y less than or equal to z. This double ampersand is the logical and operator. As you may remember from the truth table, this and operator returns true only if both of its operands are true. This is the first operand, x less than or equal to y. This is the second operand, y less than or equal to z. So in this case, x has to be less than or equal to y, and at the same time, y needs to be less than or equal to z in order for this condition to be true. Notice how I use the word and to specify what's happening here in English. It's not an accident that this logical operator is called and. If you think about it, these 2 conditions together mean that x, y, and z are in increasing order. Well, if you think about it a little more, though, that's not precisely correct, because if x is equal to y, then those two numbers aren't increasing. And if y is equal to z, they're not increasing either. But at least we know that they're not decreasing. So to be more precise, we should say that x, y, and z are in non-decreasing order. And that's a thing, by the way, non-decreasing. It's the precise mathematical description. Anyway, if they're non-decreasing, the AND operator returns true. The variable a is set to 1. The if-else-if-else statement terminates, and so does the function. And since the function returns a, as you can see up here, then the function returns a 1. So that's what happens if x is less than or equal to y and y is less than or equal to z. But if either of these relationships is false, then the AND is false, and we take the else-if branch. Its condition is x greater than or equal to y and y greater than or equal to z. This condition is very similar to the first condition. The only difference is that the relations are reversed here. We still use the AND operator. In this case, in order to get true, x has to be greater than or equal to y, and y at the same time has to be greater than or equal to z. If both of these relationships are true, the AND operation will return true, and we know that the three numbers are in non-increasing order. In that case, a is set equal to -1. The if-else-if-else statement terminates, and so does the function, and since it returns a, the function returns a -1. Finally, if neither of the two conditions is true, this one or this one, we go to the else branch down here. This is the catch-all case. The numbers are out of order, and for that case, a is set equal to 0, and the function returns a 0. Okay, we've seen an example for the AND operator. Now let's see one for the OR operator, the not smallest function. The job of not smallest is to determine whether its first input argument is smaller than both of its other two input arguments. If it's not smaller than both of them, then it returns 1, meaning it's not the smallest, hence the name of the function. Otherwise, it returns 0. To do this, it uses an if-else statement whose condition uses the OR operator, which is symbolized by this double vertical bar here. As you may remember from the truth table, the OR operator returns false only if both its operands are false. To put that another way, it returns true if and only if one or both of its operands are true. In this example, the first operand, right here, is the relational operation x greater than or equal to y. And the second operand is the relational operation x greater than or equal to z. In English, this condition reads x greater than or equal to y or x greater than or equal to z. And that makes sense, because if x is greater than or equal to y or z, or both for that matter, then it's not the smallest. In that case, the OR operator returns true. This statement is executed. A is assigned the value 1, and the function returns that 1. Otherwise, we skip to the else branch. A is assigned the value 0, and the function returns 0. Well, let's try our functions. We'll do the last one first. Well, that makes sense. 3 is not smaller than 2 and 1. And that makes sense because -1 is smaller than 2 and 1. And finally, that looks good because 2 is not smaller than 2 and 1. Okay, let's pull up our order 3 function again. There it is. And we'll remember that it's supposed to give a 1 if they're in increasing order, or more specifically non-decreasing order, a -1 if they're decreasing, or more specifically non-increasing, and a 0 otherwise. Well, that looks good because they're in non-decreasing order. It's also good, non-decreasing. Whoops, picked the wrong function, but MATLAB guessed what I wanted, so we'll go with that. And that looks good. These are decreasing, or more precisely, non-increasing. Also non-increasing. And let's do one out of order. I hesitated after that parentheses to give MATLAB enough time to give me the hint that there are 3 arguments for this function. And the 3 arguments that I gave it were out of order, which means we should get a 0, and we did get a 0. So it appears that both our little functions are working. We've seen how to use the logical operators and or inside if statements. Well, they can be used outside of if statements too, in the same way as we saw earlier that relational operators can. Let's clear the screen and look at some examples of logical operators used in this way. We'll just type some expressions directly into the command window. No surprises here. When both of the operands of the AND operator are non-zero, which is equivalent to true, the operator gives true in the form of the number 1. But if either or both of the operands are 0, which is equivalent to false, then the operator gives false in the form of the number 0. Now let's give the same operands to the OR operator. Here again, we get what we would expect. When either or both of the operands of the OR operator are non-zero, which is equivalent to true, the operator gives true in the form of the number 1. But if both of the operands are 0, which is equivalent to false, then the operator gives false in the form of the number 0. Now let's build a more complicated expression and get the logical NOT operator involved too. Let's see why D is 0. Since both A and B are non-zero, they're both true. So A and B is true too. Then when the NOT operator is applied to that true, it's changed to false. The operation B and C is false too because C is false, as we can see here. So the OR operator here is given 2 operands that are false, false, and false. So it gives false in the form of the number 0. That value of 0 is then assigned to D. Let's make one tiny change. We'll replace the second AND operator here by OR. The result is different because B or C, unlike B and C, gives a true value. That true value becomes the operand of this first OR, which then gives true. All really as we would expect. In fact, logical operators tend to act, well, logically. They do what you'd expect them to do because we're so familiar with the concepts of AND and OR. But as with the relational operators, it's a bit unexpected to find that they can be mixed with arithmetic operators. What happens here is that the expression in parentheses is true because b is equal to 2 and 2 falls between 0 and 10. So the AND operator gives 1, and then b is multiplied by 1 to give b, which equals 2. Okay, as we said earlier, when we were mixing arithmetic with relational operators, this shouldn't be surprising because a 1 is, well, a 1. And 2 times 1 is 2. So why would you want to mix arithmetic and logic? Well, suppose you wanted to add up numbers that were between 0 and 10. You could initialize your total like this, and then every time you get a new value for b, you could add it like this. Five is greater than 0 and less than 10, so it gets added in. The same holds for 3. But 11 fails the test, so 0 is added. So as you can see, b is added only when it's inside the limits, just what we wanted to do. You could do the same thing with an if statement, but it's simpler to just do it in this one line. By the way, the parentheses are important because the precedents of AND and also of OR are lower than the arithmetic operators. And here we need AND to go before multiplication. In fact, the logical operators are at the bottom of the list. Everything else goes first, as we'll see when we revisit the precedence table in a few minutes. There's one last feature of logical operators that we need to consider: their use with arrays. We can see how it works with vectors, so we'll start off with those. We'll start with the NOT operator. Let's get a clean slate. There. Okay, here's a nice vector. Now let's apply the NOT operator to it. It changes true to false and vice versa. That's what's happened here. The non-zero numbers 1, pi, and minus 2 represent true, so they're changed to false in the form of a 0. And the 0 here is changed to a 1. Since NOT operates on individual elements of an array, it's an array operator. Now let's try the AND operator with arrays. Operands to the OR and AND operators must be convertible to logical scalar values. What does that mean? Well, it means that the operands of these operators have to be scalars. They can't be arrays. Well, it's time to reveal that MATLAB actually has two versions of the logical operators. The versions you've not seen yet are array operators. Here's what the array versions of AND and OR look like. First, let's get the original version, and then we'll alter it. Then we'll alter that one. And there we have it. As you can see, there's a single ampersand for AND and a single vertical bar for OR. You might have expected to see a dot show up in the array versions of these operators. After all, for the arithmetic operations multiply and divide, as you'll remember, each array version adds a dot to the operator. But for the array versions of AND and OR, there's only one ampersand for the AND operator instead of two, and only one vertical bar for the OR operator instead of two. These single symbol versions of the operators work just fine with arrays as long as their two operands have the same dimensions, which is the same rule as for all array operators. And they work with scalar array combinations too. Here we can see that in the first expression, 2 was ANDed with each one of the elements of the array. And in this second expression, 2 is ORed with each element of the array. And let's get a little bit fancier. Before I hit return, can you figure out the answer? Spoiler alert, I'm about to walk you through it. Okay, the first relational operator, 1.4 less than square root of 2, will give true, since 1.4 is a little bit less than square root of 2. Inside the vector over here, the first element, which is the expression pi greater than 3, will be true, since pi is indeed greater than 3. But the second element, minus 1 greater than 1, is obviously false. So the elements of the vector are true and false, which in the land of MATLAB is 1 and 0. Now the true value from this expression over here, 1.4 less than square root of 2, will be ANDed with the true and with the false elements of the vector to give true and false, which in MATLAB land are 1 and 0. Okay, time to hit return. And we get a vector with 1 and 0 as its elements. The order in which the operators less than and ampersand are applied has an important effect on the result. Let's check that by inserting extra parentheses around the less than operator and its operands to force the less than operation to go before the AND operation. This operation before this one. Well, that's the same result we got without the extra parentheses, because this order agrees with MATLAB's precedence rules, as we'll see in a minute. Now let's force the ampersand to go before the less than. Here we put parentheses around everything over here after the less than, right here, so that everything inside these parentheses is done first and then fed in as the right-hand operand of the less than operation. And this is what we get. The expression inside the parentheses that we added to the right produces the vector 0, 1 yet again, and the less than, which as we learned earlier is an array operator, is applied to each one of those elements. Since 1.4 is not less than 0 or 1, the result is a couple of falses. In other words, a couple of zeros.
Now that we've seen relational and logical operators, it's time to revisit operator precedence, which, you may remember, is the set of rules that governs the order in which operations are executed. This precedence table shows that order. Lower numbers mean earlier execution. For example, relational operators at 6 are executed before logical operators at 7, 8, 9, and 10. In addition, at 4 is executed before the colon operator at 5. Remember that surprising example a few lessons ago? Chances are you're not going to learn this table by heart, but you can get it anytime you want it by giving MATLAB the command help precedence. This is the table that shows up. It omits parentheses, but it's pretty easy to remember that they outrank everything else. By the way, when you're not sure about precedence, you should probably use parentheses to force the order that you want, because it'll improve the readability of your program. That in any branch of an if statement we can have a block of code that will be executed by MATLAB if the conditions are such and such. Guess what? That block of code can contain if statements.
When it does, the outer and inner if statements are called nested if statements. And putting one if statement inside another is called nesting for short. Let's revisit our ultimate question function. It uses an if, else statement, as you can see here. Here's a version that uses two nested if-else statements instead of one if-else statement. It's similar to the previous version, but now we have two separate if statements, one nested inside the other. Note how the indentation here makes the nesting organization clear. The second if statement, because it's indented further than the first one, seems nested inside the first one, as it in fact is. And note that each else keyword is aligned with its corresponding if keyword. MATLAB doesn't care about indenting, but it helps the human reader a lot. It makes your code more readable. The MATLAB editor will actually indent your code like this automatically as you type it, but you should always check its indenting to make sure that all statements that correspond to the same block of code line up properly with each other. Here's yet another version of the same function with a second way of nesting the two if statements. This is now not so similar to the original version with the single if, else, but it still produces exactly the same result. The layout of nested if statements is more flexible than a single if, else statement because it allows you to combine conditions in multiple ways. Back in Lesson 4, we introduced polymorphic functions. Remember that polymorphic functions are functions that behave differently based on the number of input arguments or output arguments that they're called with, or even the type of input or output arguments. Many built-in functions are polymorphic, such as the square root function, max, size, plot, and on and on. It's one of MATLAB's strongest features. Now, how do we make our functions polymorphic? Well, it's actually quite simple, really. The reason we waited until now to show you is that we really couldn't do it right without if statements. Now we'll combine if statements with a couple of built-in functions that we haven't mentioned yet. The first one's nargen, or nargen, which means number of arguments input. It gives the number of actual input arguments that the caller passed in. The other one's nargout, or nargout. It returns the number of actual output arguments that the caller requested. These two functions can be called from inside our functions to make our functions polymorphic. Here's the function declaration of a function called multtable with two output arguments and two input arguments. It returns an n by m multiplication table in the output argument called table. Optionally, it can also return the sum of all elements in the output argument in the variable summa. If it's called with only one input argument, it returns an n by n matrix. So let's see the code. First, we check to see whether the function was called with one or two arguments. If nargen is smaller than 2, then it was called with only a single argument. A single argument is always put in the first position, which in this case is the variable n. When m is omitted, we're supposed to return an n by n matrix. So we set m equal to n. This is a classic example of setting a default value for an input that's omitted. Now we're ready to compute the multiplication table. It's actually pretty simple. We create two row vectors, one going from 1 to n and the other from 1 to m. We transpose the first vector to be a column vector and use matrix multiplication to create the table. Now it's time to determine whether we need to compute the sum of the matrix as well. We need to do that only if the user requested a second output argument, so we check nargout. If it's 2, we call the sum function. Remember that sum computes the sums of the columns of a matrix and returns them in a vector? Well, that's not what we want. So here, we use the column argument to create a vector from all the elements of the table. That's done with a colon. And then we sum and give that to sum and it'll add them all up.
If NRGout is 1, then we avoid sum entirely. But there's no harm in computing summa, even if the caller doesn't request it. If we calculate it when the user doesn't request it, MATLAB will simply discard it when the function returns. So all we've done is save a few microseconds of calculation time here. But you will definitely want to use NRGout to avoid long calculations, perhaps many minutes, when the user doesn't ask for them. In any case, here's our first polymorphic function. Let's see it in action. Well, here's our multi table function in the editor all ready to go. Let's pitch it a few different inputs to see how well it does. There we gave it 3 by 4, and it gives us a 3 by 4 array, and that looks like a multiplication table. Let's ask it for a couple of outputs. There's the table, and there's the sum. And that's the correct sum. Okay, this time we just asked for one output, but we only gave it one input argument. And you'll remember that that defaults to 5 by 5 instead of just 5. So far, so good. It's hitting them out of the park. Let's see how it handles a curveball. Well, we managed to make it fail by giving it no argument at all. MATLAB tells us the line on which the failure occurred, and we can see what happened on that line. Right here. When MATLAB tried to look up the value of n, it found no value of n because we gave it no value. Well, that might seem like cheating, more like a spitball than a curveball. Let's be a little more fair. Let's give it some arguments. But, well, let's do this. We got the empty matrix back. Clearly we didn't plan on negative inputs, but can you see where the empty matrix came from? Well, the colon operator here, 1 to n on line 7, became 1 to minus 3 because we gave a minus 3 for n. And the 1 colon m became 1 colon minus 5. And as we saw way back in lesson 2, when the end is less than the beginning for the colon operator, and we don't include a negative increment with it, the result's an empty matrix. Here we got 2 of them. Now we see that the product of 2 empty matrices is also an empty matrix. So now we can understand why we got the empty matrix here. And we can also understand where we got this error. But both of these cases represent traps for the user. We should do something about them. So we got in trouble calling the multi-table function with no arguments. We got strange results when we called it with the wrong arguments. Well, how can we avoid these problems? First, let's note a limitation of the function declaration. A function declaration specifies the name and the number of input and output arguments. But in our head and in our code, we make additional assumptions about our function that aren't specified in the declaration. Then we write the code and the documentation for the function, which specifies the rest. What the function does, what types of values should be in the input arguments, and what those values represent. So rather than just assuming that the caller of the function will comply with the assumptions in our code, we need to write our code so that it checks its input. If a function checks all its assumptions about its inputs and outputs, and provides a meaningful error message when they're violated, it's termed a robust function. All built-in MATLAB functions are written in this way. In general, you should always check that the function is called correctly, that is, in accordance with your assumptions about the inputs and the outputs. This can make finding bugs later much easier.
But how do you do it? Well, we do it with the if statement. Let's make our mult table function robust. First, we check whether the function was called with at least one input. If n(arg_n) is smaller than 1, then no input argument was provided. In that case, we call the built-in error function. It prints out the message we give it in red and then terminates the function. That's how easy it is. And we get to print in red. And that's the only way to do that. Next, we check to see whether the function was called with m, just as we did in the earlier version of the function. But this time, we add an else if to check for the correct type of m. The type we want is a positive integer. The else if uses a combination of three conditions. If any one of them is true, m is not a positive integer. We use the OR operator to combine these conditions. The first condition uses the built-in isScalar function to check whether m is a scalar. It returns true if its argument is scalar and false otherwise. So we need to use the logical negation to turn that around by putting the tilde in front of isScalar, because not scalar is the error case. Then we check for the error m less than 1, and then we check for non-integer. Here's how we do that. We use the built-in fix function, which rounds its argument to an integer. If m is not an integer, then its rounded value won't be the same as m itself. If any of these conditions is true, then we have an error. So we use the error function, telling the user that m needs to be a positive integer. And then error automatically quits the function. Now we repeat the same check for n that we did for m. At last, we can compute the multiplication table. It's funny how the error checking was more painful than the actual computation. That's not that unusual, but it's worth the pain now to avoid pain later when assumptions are violated during actual function calls. Finally, we compute the sum if requested by the caller, just as we did before. And that's our new and improved, and most importantly, robust function. But we're not done. We got a robust function, but it's not a good program yet. There's more to good programming than good code. We need to include an explanation of our assumptions in human language, and not just in MATLAB code. Well, can we do that? You can probably guess the answer. Yes, we can. We can do it with the help of comments. A comment is extra text that's not part of the code, so MATLAB simply disregards it. You create a comment using the % sign. The MATLAB editor will then show that % sign and everything that follows it in green. Anything after the % sign, including the % sign, until the end of the line becomes a comment, and MATLAB ignores it. The purpose of a comment is to provide extra information for human users. You use comments to document your code. It's typically used to explain important or complicated parts of the program. For example, you should use comments at the beginning of your functions to explain what the function does and what its inputs are and what its outputs are. And guess what? And this is very cool. If we do it this way, that is, if we insert these comments after the function declaration, but before the function code, just as shown here for the mult table function, the built-in help function in MATLAB will work for our function just like it does with its built-in functions. It'll print out all the text we provided in these comments. So your function will behave just like a built-in function. Let's try it and see it for ourselves. Here's the improved version in the editor. You can see all the changes that we've made here. Let's ask for help with it, just as if it were a built-in function. But before we do that, we hardly have any room here for our command window. I think I'll get rid of the workspace over here by clicking this little arrow and clicking close. So that's gone. And maybe I can move the command window over here somewhere, like that. Let's make it a little bit bigger. I don't need as much space there. Let's get things. You can get things set up the way you like them and then go from there. So Let's try asking for help. Look at that. It looks just like we've written a built-in function. You see how you get bold type wherever you use all caps? That's just so cool. So it tells you what you need to do, and the user feels comfortable trying out this function. But now we've got to see what happens if we give it the wrong inputs. So let's try a few things here. No inputs. Now we're printing the red stuff out to the user. Must have at least one input argument. So far, so good. M needs to be a positive integer. Let's give it a fraction. It needs to be a positive integer. That's not an integer. It's positive, but it's not an integer. Let's give it a vector. Well, a vector is not a positive integer. Maybe we should add an error message that says, what part of positive integer do you not understand? But that would just be mean. We won't do that. And anyway, we'd need to count the number of times the user called it with a bad input. And how in the world would you do that? Anyway, it now has a help page, and it provides meaningful error messages for any inputs that violate the assumptions made about it in that help page. And does it still work correctly for valid input? Let's check that. Yeah, whew. Good. We didn't break the thing when we added all that error checking. You know, I think we can congratulate ourselves now. We've written a function that's robust and does what it says it'll do.
So far, we've used local variables a lot, and we briefly introduced global variables. Well, there's a third kind of variable, the persistent variable. A persistent variable is a local variable, so it's only visible inside the function in which it's defined. But its value persists across function calls. In other words, MATLAB doesn't discard the value of a persistent variable when the function returns the way it does with a regular local variable. It keeps that value until the next call. This can be useful in a few special cases. For example, when we need to know how many times a function's been called. The only other way to do that would be to use a global variable, but it bears repeating that we're discouraging you from using global variables until you've gained a lot more experience. And even then, many times all you need is a persistent variable. And they don't cause the mischief that those sneaky global variables do. So let's see how to use persistent variables.
Here's our first function that uses a persistent variable. Its job is simply to keep adding up the value of its single input argument every time it's called. And it returns the total of the arguments entered so far. It's like a bank account that you add money to. Let's try it. Okay, we started by adding 3, and the total in our bank account is 3. Let's add 5 more. And let's put in 10. And you can do negatives. And we took out $11. Oops, we're overdrawn. Anyway, the key to this function is the persistent variable summa here, which is declared using the persistent keyword right here, which shows up in blue since it is a keyword. When a function is saved in the editor, any persistent variables in it are initialized to the empty matrix. So we have yet another use for the if statement. We can use it to determine whether this is the first time the function has been called. If it is the first call, we set summa equal to the input argument n. Right here, we check if it's empty, we know it's the first call, then we set summa equal to n. It's an error to declare a variable persistent that already exists in the current workspace. That's why we couldn't use the output argument total to store the value inside accumulate. We need to introduce the new variable summa. It's clear that we could not accomplish what accumulate does with regular local variables since they're deleted every time a function returns. All persistent variables within a function can be reinitialized to the empty matrix in any of these three ways. By resaving the function in the editor, by clearing the function with clear, we come over here and we give the command clear accumulate like this, or by exiting and restarting MATLAB. Let's see if that did reset summa to the empty matrix. If it did, then accumulate should start over from 0. Yes, it did. So now you know how persistent variables work. But you know what a persistent variable would be just perfect for? Remember when we were saying that maybe we should add an error message to mult table that says, what part of positive integer do you not understand? You know, when the user keeps doing it wrong over and over. Well, we said we wouldn't do it because it would be mean. But now that we know how to count things with persistent variables, it's just too tempting. Let's try this version. It's called Snarky Mult Table. And it uses a persistent variable right here. It's called error count. We're going to let you study it on your own, but let's try it out. We'll give it correct input, and it looks like it works just fine. And now let's give it some incorrect input. We gave it 3 minus 2 before. Well, that's what the non-snarky version did when we gave it a negative number. Let's try the fractional number. That's also the non-snarky response. Let's try that vector. Okay, now we're in snarky land. What part of positive integer do you not understand? The user has made 3 mistakes in a row. It calmly handles the first 2 errors and then unloads on the user at the third one. You can do this sort of thing. It might even be kind of satisfying. But we know better, don't we? We should be nice. Go ahead and look at this function to see how it works. There's a couple of interesting things in here. Here you see we put an if statement all on one line by using a comma here. Here's an inline comment. Let's see, down here we check if we've actually had 3 errors. That means we give this nasty error message here. We set the count back to 0 to get started all over again. So the next error, the user gets the non-snarky response. So you can do this. You shouldn't, though. Well, we'll end Lesson 5 now, and we should probably take a little time to wrestle with our consciences before we write another function.
Hi, and welcome to Lesson 6, Loops. This week we'll be talking about a powerful programming concept, looping. The loop is a new control construct that makes it possible to repeat a block of code a number of times. So far, every statement and every function has been executed exactly once, or if some condition was false, not at all. While this is useful, it doesn't exploit the real power of a computer, which is the ability to execute millions or billions of instructions per second. With what we've learned so far, to get our computer to execute 1 billion statements, we'd have to type 1 billion statements. And we'd be typing for many centuries just to get a program to run for 1 second.
Fortunately, we can avoid all those centuries of work by using loops. In fact, we've already been using loops in MATLAB without even knowing it. To carry out the command n equals 1 colon 5, for example, MATLAB uses a loop internally to create the vector 1, 2, 3, 4, 5. And to carry out the command total equals sum of n, it uses a loop to add all those 5 numbers. These are implicit loops because we didn't use any explicit loop control constructs. Let's compute the sum of 1 through 5 without using the built-in sum function. We'll use a loop, but we need to design an algorithm that includes the loop. An algorithm is just the computer science term for a step-by-step procedure that solves a problem. And this figure shows a very simple algorithm that will solve our problem. It uses a variable called total to store the sum as we compute it, and it starts by initializing total to 0. The large light blue box represents the loop. It specifies that the statement add n to total be executed repeatedly as n takes on the values 1 to 5, one by one. So the add n to total statement will be executed 5 times. After the 5th time, the loop ends and the program continues to the next statement after the loop. That statement prints out the value of the variable total, which is the result we wanted. Note the curved line with the arrows on it. It shows that after add n to total is executed, control circles back and does it again, and it shows why this control construct is called a loop. That little circle looks like a loop. Let's look at the execution in detail. Warning, this part is really boring. We start by setting total to 0. This step is called initialization, and it happens outside the loop. Now we enter the loop. Since the loop must repeat n for n equal to each item in the list 1, 2, 3, 4, and 5, the first thing that happens when the loop is entered is that n is set to the first item, 1. Then n is added to the total. Since total is 0, n is 1, total equals 0 plus 1, which equals 1. That completes the first repetition of the loop. A repetition is called an iteration, and now it's time for the second iteration. This time n is set to the second value in the list, which happens to be 2. Again, n is added to total. Now total equals 1 and n equals 2, so total equals 1 plus 2, which equals 3. That completes the second iteration of the loop. Bored yet? Me too. Don't say I didn't warn you, but we need to go through this for at least one loop. Okay, for the third iteration, n is set to 3. Again, n is added to total. Total equals 3, n equals 3, so total equals 6. That completes the third iteration of the loop. For the fourth iteration, n is set to 4. And as in every iteration, n is added to the total. Now total equals 6, n equals 4, so total 6 plus 4 equals 10. And that's the end of the fourth iteration. For the fifth iteration, n is set to 5. Again, n is added to the total. Now total equals 10, n equals 5, so total becomes 15. That's the end of the fifth iteration, and we've hit the end of the list of values for n, so the loop ends. And finally, we get to the statement after the loop, which prints 15, and our algorithm is done. You may say this was a complicated way to add 5 integers, and you're right, sure. Typing 1 plus 2 plus 3 plus 4 plus 5 would have been simpler. But suppose we wanted to add the first 5,000 numbers. Using a loop, we can just change the 5 to 5,000, and it'll add them all up in an eye blink. Now we're ready to see how we can implement this algorithm in MATLAB. The most frequently used loop construct in MATLAB is called the for loop, and that's what we need. Let's see how we can use it to add 1 through 5. We start by initializing the variable total to 0, just like we did in our algorithm. Then comes our for loop. It starts with the keyword for, and to the right of that is what looks like an ordinary assignment statement, but it's not. Its left-hand side is a variable called the loop index. In this case, the loop index is n. On its right-hand side is a vector. But here's where the difference from an ordinary assignment statement comes in. The vector will not be assigned to n. Instead, the meaning of this special assignment statement is that the index, n, will take on the elements of the vector one by one. At each iteration of the loop, n will get the next element of the vector, stopping with the last one. And that's exactly what we want here. N will be equal to 1, then 2, then 3, then 4, then 5. At each iteration, n is added to the current value of total. So, just as for our algorithm, total keeps accumulating the sum, becoming equal to 1, then 3, then 6, then 10, and finally 15. Once the last element of the vector is assigned to the loop index and used in the block of code inside the loop ends. And then fprintf prints the value of total, which is 15. Okay, let's see this example inside MATLAB. Here's our summing algorithm inside a function called sumIntUp. But instead of adding the integers from 1 to 5, we add up from 1 to n, where n is the input argument. If we run it like this, we get 15, as we've just seen. The good thing with a function, though, is that it's easy to run our loop with different numbers. Let's try 10. Summing from 1 to 10 gives 55. What about 100? That gives 5,050, and so on. Let's run the function with 5 again. First, let's set a breakpoint right here on the second line. I just click the little dash here, and the red circle shows me that my breakpoint is set. Then we can use the debugger to step through. Okay, let's run it with 5 as the input. The green arrow here means that execution has been suspended right where we put the breakpoint, and that we're ready to execute line 2 here. At this point, we have not executed this line yet, so the variable total has not yet appeared in the workspace. But there's already a capital N there, and it's equal to 5. Remember, that's our input argument, and it gets its value from the function caller down here. And it comes into existence when it's assigned the input value, which in this case is 5, and that happens before line 2 is executed. Let's execute line 2 by clicking the Step button. To get that button to show up, click the Editor tab. That tab contains all the debugging tools. Here's the Step button right here. Before I click it, you may remember from our introduction to the debugger that you can also take one step by clicking the function key F7 on a MacBook or F10 if you're using Windows. Okay, as I click Step, watch in the workspace to see the variable total appear with the value we're assigning to it, which is 0. There. Now we're at the beginning of the for loop. Okay, I'm going to execute the first line of the for loop. Clicking Step executes that line. There. The workspace shows that we now have the variable lowercase n here, and it's been assigned the value 1, which is the first element of the vector 1:n here. This is a key concept for the for loop, so it's worth repeating. The loop index is assigned the first element of the vector produced by 1:n, not the entire vector, at least on the first iteration. On subsequent iterations, it will receive subsequent elements of the vector. Now we're ready to execute the body of the for loop here, with the loop index set to 1. The body comprises just line 4, and that line adds n to total. The workspace shows their values before we take the step, 0 and 1. Okay, I'll click Step Now, and we see that total has changed to 1. Clicking Step again here at the end statement results in MATLAB taking the next element of the original 1 to 5 vector and assigning it to little n. We'll see that happen right now. There. Note that we did not see the green arrow go back up to the 4 line at the top of the loop. That will never happen again through the entire iteration. That line is actually executed only once at the beginning of the loop. It calculates the vector of values, in this case 1, 2, 3, 4, 5, and it sets the loop index to its first value, which is 1 in this case. Then after the first iteration, the next index is actually set at the bottom of the loop. It's the same as if it were set at the top, but that's why you won't see control jump back to the 4 line. Anyway, now we're ready to execute the next addition. Total is equal to 1, and n is equal to 2. So after executing this line, total will be equal to 3. And 3 it is. As we continue clicking the button to step through the code, we can watch the workspace to see how n goes through all the values to 5, and how total reaches 15. Well, let's do that. Click. Now n is equal to 3. Click. Total is equal to 6. Click. N is equal to 4. Click. Total is equal to 10. Click. N is equal to 5. Click. Total is equal to 15. And we take one more step, and we're out of the loop. The next step will print the result to the command window. Let's do that. Click. And we see the result show up in the command window down here. Take another step. You see this arrow pointing down means we're about to leave the function. The function ends, the step button disappears, and we're done.
Let's look at this example one more time. The expression with the for keyword is called the control statement. This is where the index variable is defined and its subsequent values are specified. And it doesn't need a semicolon at the end. The block of code between the control statement and the end keyword closing the loop is the body of the loop. It's the body that gets executed repeatedly using successive values of the loop index. Here the body is a single statement, but in general there can be any number of statements in the body of a loop. Most of the time, the vector to the right of the equal sign in the control statement will be formed with a colon operator, as it is here, but it doesn't have to be. Here's another example. Instead of a colon operator, here we simply use another variable that already contains a vector. In this case, it's a vector of 5 random numbers. This is perfectly fine. The loop index will be assigned the elements of this vector one by one. The body of this loop is a single if-else statement. It prints out one of 2 messages, depending on whether or not the current value of the loop index, which is one of those 5 random numbers, is greater than 1/2. We ran this program, and this was the result. Note that depending on when and how the pseudorandom number generator was initialized, you may get a different random number set when you try it. And unlike Mythbusters, we do encourage you to try this at home. Consider this slight variation of the previous example. We eliminated the variable named list because you can call the rand function, or any other function for that matter, right in the control statement itself. In fact, any valid expression can go to the right side of that equal sign. The values assigned to the loop index don't have to be integers, they don't have to be regularly spaced,
or even assigned in increasing order. In fact, they don't even have to be scalars. The general rule is that the loop index will be assigned the columns of the array generated by the expression on the right of the equal sign. If that array is a vector, then those columns will be scalars. As for the body of the for loop, any control construct can be used, if statements, other loops, and so forth, or just lists of statements. Let's see the second example in the editor. And let's use the debugger again to watch it work. Place a breakpoint right here on line 2 and call the function. Well, we've stopped at line 2. Nothing's really happened yet. There's nothing in the workspace. So let's take a step. Well, we see n's equal to 5 over here. That happened right there on line 2. Now we've gotten a set of numbers into list by calling rand 1, 5, because n was equal to 5. And here's our list of numbers. There. 1, 2, 3, 4, 5 numbers. Let's enter the body of the for loop. X gets the first number. Body of the loop consists of a single if-else statement. Let's see what happens. Let's see ahead of time. X is greater than 0.5, right? So that means the if branch will be executed instead of the else branch. And we're in that branch, and the printf executes and says that it's large. Now we're down at the end statement. When we click on that, X will get the next value, 0.9058. So let's do that. And there we see X has the next value. That's also greater than 0.5, so this statement will execute again. And there we have it. The next step, we'll set X equal to the next element, 0.1270. X is not greater than 0.5, so we'll be in the else branch. And there we are. Now we're in the body of the else branch. We'll carry out this fprintf, which says that this number is small. And we'll keep going in that way. You can see X going progressively through the list. Now it's on the last one. That's also large. So it just so happened that in this position in the pseudo-random sequence, we had 4 large numbers and 1 small one. Another step gets us out of the for loop, and 1 more gets us out of the function. By the way, before we started, the pseudo-random number sequence was initialized to the state it has when MATLAB starts. So if you call RNG of 0 before you call RAND check, like this, then you'll get the same numbers. Otherwise, you'll get a different sequence. An interesting question arises when the loop index is assigned a value explicitly by a statement within the body of the loop. The question is this: what's the value of the index on the next iteration? The answer is that it's the next value in the list of values given in the control statement, up here. Assignments to the loop index inside the body of the loop are temporary. They last only during the iteration in which they take place. There's no effect on the original list of values given on the if line at the top of the loop, or on the next value to be assigned to the loop index for the next iteration. Let's see an example that illustrates this point. A modified sum int up function that we've named loop test. Inside the loop, we first display the current value of n, then we add 1 to n, and then we add n to total. Let's run it. And we give it the value 5. So what have we learned? The function printed the originally intended values for n as given by 1 to n here, the 1:5 expression. We changed the first value of n from 1 to 2, but at the next iteration we got the originally intended next value from here, which was 2. As we said, changing the value of the loop index is temporary. It applies only to the current iteration. There was an effect of adding 1 each time, though. You can see it in the total down here, which is 20. We added an extra 1 to n each time through the loop, so the total should be 5 more than the sum of the first 5 integers, which is 15, and we did get 20. This rule is ironclad. At the beginning of the nth iteration for every for loop, the loop's control statement will assign the loop index the nth term in its list of values, regardless of any value that may have been assigned to the loop index within the body of the loop during the previous iteration. Finally, a word of caution. Don't change it. Don't change the loop index inside the loop if at all possible. It'll just cause confusion when you read your code later or when someone else reads it. There's very rarely a need to do so, and even then you'll be better off using an additional variable than messing with the loop index. Let's talk a little bit about handling vectors with loops. Let's look at this example. Here, MATLAB handled the subtraction of the element 5 from the element 5 and got 0. It handled the subtraction of the element 4 minus 5, got minus 1. 8 minus 7 gave 1, 8 minus 8. It handled every one of these subtractions, element by element. Well, it did that with a loop. The loop's behind the scenes. We didn't write the loop, so we call it an implicit loop. MATLAB does that a lot of times. But we can do it too, out here, in front of the scenes. Let's do it. As soon as I hit return, the work is done, and the results are the same. The for loop does exactly the same thing that the array subtraction operation did. We visit every element using the for loop index, which indexes into U and indexes into V and indexes into W. We get the same result. We had to use the length function here to find out how far to carry the loop. In this case, there's really no reason at all to use an explicit loop instead of the implicit loop. Implicit looping runs faster in general, it's easier to program in general, and it attracts fewer bugs in general. You should use it wherever you can. But explicit looping is much more versatile than implicit looping. In addition to being able to do everything that array and matrix operations can do, for loops in general, can do many things that array and matrix operations can't do. Since we often need to do these additional things, MATLAB includes explicit loops as part of its language. As an example where we must use an explicit loop instead of an implicit one, consider the Fibonacci series. It's defined as a series where the first 2 elements are 1 and all successive elements are the sum of the previous 2 elements. We've got a function here that creates the first n elements of a Fibonacci series called Fibo. Let's see how it works. First of all, we do some error checking to make sure that the user has passed in a scalar, a number that's greater than or equal to 1, and a number that's an integer. In other words, a positive integer. We've done that before. Then down here we set the first element to 1 and the second element to 1. You'll remember the definition of Fibonacci series is the first 2 elements are equal to 1 and the successive elements are each equal to the sum of the two previous elements. Well, now we enter a for loop that goes from 3 to n. N is the input. Why 3? Well, we've already done 1 and 2, and as you can see on the left side of this assignment statement, we're doing F3 and then F4 and then F5 and so on. On the right side, let's say we're at 3. 3 minus 2 is 1. 3 minus 1 is 2. So this is element F1, this is element F2. So F1 plus F2 gives F3. Let's do one more. Double I, the index, becomes 4. So F of 4 is equal to F of 4 minus 2, that's 2. And F of 4 minus 1, that's 3. So F of 4 is equal to F of 2 plus F of 3. And so it goes. Here we had to use an explicit loop since there's no built-in operator or function that could have done what we needed, summing up the preceding elements of the vector to compute the current one. So the Fibonacci series serves as a simple example of why we need explicit looping. The body of a loop can contain any valid MATLAB statements. That means that a loop can contain another loop. In other words, we can nest for loops. That's in fact what we need to do if we want to perform an operation on every element of a matrix instead of a vector. Let's do this. There we've got some random numbers in A, all integers. And let's do this. Of course, you know what's happened here. We've used the array multiplication operation, so every element in A has been multiplied by the corresponding element in A. MATLAB did this with implicit looping. Just as with vectors, however, we can write equivalent code to do the same thing with loops. I've got an example right here in a file called mul.m. Let's see it. There. This is a script, by the way. You'll remember us talking about scripts at the end of Lesson 3. A script is a file that contains just a list of commands instead of a function. You can run it by giving its name as a command in the command window. You can also run it by clicking this Run button up here with the great big green arrow. Let's click the arrow. There it shows that mul is carried out in the command window as if we'd typed it in there ourselves. Well, let's see what value it gave to p. Good, same as the array operation did with its implicit looping. We didn't make an error in our script up here, that's good. Well, let's look at the commands in this script. First, we use the size function up here to find out the dimensions of A, and we put those dimensions in row and col. So row has the number of rows in A, col has the number of columns. Then we enter a for loop here, whose index, R, which suggests row, goes from 1 to row. So it scans through all the rows of A. Well, you can have, as we mentioned, any MATLAB command in the body of the for loop, and so we have a for loop in the body of this for loop. This inner for loop is said to be nested in the outer for loop. This for loop's index, C, which suggests columns, scans all the legitimate column indices in A. The actual calculation is done in the body of this inner loop, and that body consists of just this one statement. It's a multiplication. It multiplies element RC of A by element RC of A. When we exit this for loop, we've done all the columns for a given row. We repeat by changing the row index by 1, then carrying out this loop again for all the columns of that new row index. And we repeat again for a new value of R. And we carry out this inner loop for all these values of C for that given value of R, and so on. When we exit the outer loop, we're done with the script. Note that we've carried out the outer loop row times, and for each one of those, we've carried out the inner loop call times. So this body here, the single statement, was executed a number of times that's equal to row times call. And that's the same number of elements that there are in the matrix A. So that's all there is to it. Or I should say, there's a lot to it. I say that because this script is a lot more complicated than A dot star A. If we want to follow the order in which the elements are multiplied, we can insert a line right after the multiplication, like this, that prints things out. It'll print the row and the column in parentheses using the %D format with a space between them, and then it'll skip to a new line. Let's try it. And I'm going to need more room than this. I think I'll sacrifice my workspace. So I'll close that and then move the command window over here beside the editor window. There. So let's try it again. This time I'll type mul in the command window. There, you can clearly follow what happened. Remember, the first element is the row. So we did row 1, column 1, row 1, column 2, 1, 3, 1, 4. We're done with row 1. Now we move to row 2 and do columns 1, 2, 3, 4. Then we move to row 3 and do columns 1, 2, 3, 4. When we're doing these columns, we're staying inside this inner for loop. When we're done with the inner loop, we go to a new row in the outer loop and then repeat the inner loop. And we do that over and over and over. While we're at it, we could also insert another fprintf statement right here, like this. It'll print working on row, space, and then it'll print the row number R using the %D format, dot, 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 go to a new line, and then print all this stuff out. Let's try that. There. Working on row 1. Well, 1, 1, 1, 1, that's row 1. 2, 2, 2, 2, 3, 3, 3, 3, and so on. This makes it nice and clear. This is called row major order. It means that you visit every element of the first row, then every element of the second row, etc. You can't do this sort of thing to look inside an implicit loop that MATLAB provides, but as a matter of fact, for implicit looping, MATLAB uses column major order. Let's consider another example for nested for loops. I've got an example right over here in a file called asterisks. There it is. Let's run it and see what we get. Well, what we get is a pretty little half of a tree depicted in asterisks. In the first line, see that we get 1 asterisk, the next line 2, then 3, then 4, then so on, until we get to 7 asterisks on the last line. Well, over here in the code, there's nested for loops here. And in the inside loop, we see that it prints 1 asterisk each time through the loop. Its index goes from 1 to mm, and as mm gets bigger, it prints longer and longer lines of asterisks. You can see the outer loop changes mm from 1 to n, which happens to be set equal to 7, which is why we get 7 lines with 7 asterisks on the last line. And you'll notice that after each of the inner loops is finished, this fprintf takes us back to the beginning of the next line. The trick here was that we used the value of the outer loop index to control the behavior of the inner nested loop, which gave us these longer and longer rows of asterisks. This again is something that we could not do with implicit loops.
For loops work well when we know the maximum number of necessary iterations before entering the loop. In the control statement, the expression is evaluated, and then the loop index will receive the elements of the vector or the columns of the array one by one. The maximum number of times the for loop body will execute is fixed at this point. Why maximum? Because we can always quit early with a break statement. But what if we don't know the maximum number of times a loop needs to iterate? Consider this problem. How many positive integers do we need to add together to exceed 50? The only way to solve this with a for loop is to guess a large enough number for the number of iterations and then use a break statement to stop the loop when 50 is exceeded. You can do that. It's not that hard for this simple problem, but there's a better way, one with no guesswork at all, a while loop. Check this function out. We call it POSSUM, for positive integer summation. It takes the limit that we want to exceed as an input argument. It both prints and returns both the number of positive integers we need to add together to exceed the input value and the sum of those integers. We start by setting both n and total to 0. Then we use the new while keyword followed by a condition. The meaning is simple. If the condition is true, we execute the body of the while loop. The body is the set of statements between the while line and the end keyword. Once we execute the body, we go back and check the condition again. If the condition is false, the while loop is done, otherwise it continues. The body in this example increments n by 1 and then adds the result to total. Once total exceeds limit, the while condition will be false, the loop terminates, and we print the result. The function then terminates and returns its output argument. If we run the function with the input 50, here's the result. The first line of the printout came from the fprintf inside the function. Then MATLAB caught the first output argument in its ands variable and echoed the result. The second output argument was discarded. Well, we've seen the while loop in action, but let's take a closer look at its form. Just like the for loop, the while loop has a control statement and a body. However, the control statement of a while loop is a condition, like, for example, total less than or equal to limit. Its value is either true or false. If it's true, we execute the body, then we check the condition again. If it's false, we quit. You might have noticed that the general form of the while loop is very similar to that of the if statement. In fact, syntactically, the only difference is a different keyword, while instead of if. But semantically, they are very different. The if statement's a one-shot deal. If the condition's true, we execute the body and we're done. But the while loop keeps checking the condition and executing the body over and over and over until the condition becomes false. This is a very powerful and very flexible way of looping. Let's look at this example in MATLAB.
Here's the POSSUM function in the editor window right here. Let's run it. Okay, let's check its answers. Let's look at the last example first. We can do that by checking the sum of 1 through 318 and then the sum of 1 through 319, like this. Okay, 318 isn't large enough to get the sum above 51,000, but 319 is. And the sum to 319 is 51,040, which agrees with the answers up here. So the answers are correct. You can check the other examples too. You'll find they're all correct. This function works like a charm. But before we leave it, let's talk a little more about its form. We pointed out how similar a while loop is to an if statement. But notice how similar this particular while loop is to a for loop. Not only does it iterate, but like a for loop, on each iteration, our while loop increments n, right here, which is a kind of loop index. And it starts out at an initial value here and terminates when it reaches its last value. I say kind of because this so-called loop index here, n, is not an integral part of the while loop control statement up here, in the way that an index of a for loop is. The index of the for loop is an integral part of the for loop control statement. The syntax requires it. And the for loop semantics is based on it too, because the number of iterations is completely determined by the list of values for the for loop index given in the control statement. And then the index is assigned a new value from that list on every iteration. In fact, as we showed earlier in this lesson, you can change the for loop index to whatever you want in the body of the loop. But on the next iteration, it'll be changed right back to the next item on the list by the for loop control construct. The while loop, on the contrary, doesn't provide a list of values for an index, and it doesn't increment anything on any iteration. If we want to increment something, we've got to do it ourselves, explicitly, with a statement in the body of the loop, as we have here with this n equals n plus 1 statement. The index is not part of the while loop syntax at all, or the while loop semantics. And to drive that point home, I'm going to show you a perfectly good while loop with no loop index at all. It's in a function called approx square root, right here. As its name suggests, this function computes an estimate of the square root of its input argument x here. There's just one statement in the body of this while loop. It computes the value of the variable called y. I'm going to remove this semicolon. You wouldn't ordinarily want to do that, but I want to see y's value change each time we iterate through this loop. Let's also go over here and change the format to long, like that, so we can see more decimals when y is printed out. Okay, let's calculate the square root of 2. There. Well, as you can see, it took only 1, 2, 3 iterations, and then it gave us back the answer, and that answer, 1.41, seems like it might be pretty close to the correct answer. Let's compare it with the built-in function. Yeah, that's close. Differs by 2 millionths. If we test on a larger number, we'll see it takes a few more iterations. Let's try 200. Yeah, this time it took 1, 2, 3, 4, 5, 6 iterations instead of 3. Let's see how close it is this time. Not as close, but still pretty good. That's 3 thousandths. Well, let's look at the function itself over here a little more carefully. Let's look at the condition here. First thing that happens is the absolute value of the difference between y squared and x is calculated. Y, of course, is supposed to be the square root of x. That's what we're trying to make it equal to. And if you square the square root of x, it should be equal to x. So the difference here, ideally, would be equal to 0. If it's bigger than 0, then we might want to do a little more work. So what we do, in fact, is check to see if it's bigger than 1,000th of x. If it's bigger than that, then we carry out the body of the loop again. And we check this again, and we keep doing that until the difference between the square of y and x is absolute value no greater than 1,000th of x, and then the loop ends. We can talk about this combination of x and y that gives us a better estimate of y from the current value of y, but I'm really more interested in this condition. The key thing to notice here is there's no loop index. I mean, where is a counter that counts up the number of times we go through? Where is a list of values that it's set to? Where is an increment of n? There is no n. There is no loop index. It's absolutely unneeded. We don't care how many times we go through this loop. We just care that we go through it while this number is bigger than this number. We stop when that's no longer true and declare that we've got a good approximation to the square root of x, and we quit. And if we think we're quitting too soon to get an answer that's accurate enough, we can increase the accuracy by changing the 1,000th of x threshold to something smaller, say, let's make it 1/10,000,000th of x. So it took 6 iterations for 1,000th of x. Now we've increased the required accuracy by a factor of 10,000. Wonder how many more iterations it's going to take now. Better get comfortable. This could take a while. Wait, 1, 2, 3, 4, 5, 6, 7 iterations. Only one more iteration? Let's see how accurate this one is actually compared to the built-in function here. Three 10,000,000ths. We went from 3,000ths in 6 iterations to 3 10,000,000ths in 7 iterations. This thing is converging fast. By the way, if you're wondering why we aren't at 1/10,000,000th, since we have 1/10,000,000th here, remember that this while loop condition is checking the accuracy of the square of y, while down here we're checking the accuracy of y. Well, let's put that semicolon back in now that we've seen how this thing works. And let's see how accurate we are on something we know the exact answer to, like the square root of 1,000,000. Now that's pretty accurate. Look at that. Should be 1,000. 10 to the minus 11. Excellent. Let's see the built-in function try to beat that. 0. You know, MATLAB, nobody likes to show off. Okay, our little function may not be quite as good at calculating square roots as the built-in function, but it's a lot better than the built-in function at showing you how while loops work, which is, after all, its purpose. Let's get back to that by giving it another input. Let's try minus 200. Okay, well, it's not doing anything here. Where's our prompt? Well, here's a hint at what's going on. Look over here. You see this word busy? This means that MATLAB is actually still working on our function. It hasn't croaked. It hasn't stopped. It's still going. It's in this while loop, and it's going over and over, and it'll go forever because the condition in this while loop will never be false. This will always be greater than that. So we need to stop this thing. Do you remember what we said earlier that you should do in a case like this to stop MATLAB? You could click the little red button up here or over here, depending on your operating system, and stop MATLAB entirely and start all over again, but that's not necessary. Control-C will stop this loop. Let's do that. I'll pop up a keyboard viewer so you can see what I'm doing. And I'll press the Control key. On your keyboard, it might be CTRL on the key, or it might be Control. And here it's this little caret. So I'm going to press that. There, you can see I've pressed that. And while I hold that down, I'll press the C key. Okay, when we did that, everything stopped. We got this red message, and we've got our prompt again. The red message is, for once, not a slap on the wrist by MATLAB. This message says that the user stopped it while it was working. Maybe it's mad because we stopped it, but it tells us where it was when it stopped. On line 5 of the function approx sqrt, it's right here. That's the end statement of the loop, and that's where MATLAB typically stops when you use Control-C while it's looping. Let's remove the semicolon here and run it again so we can see things happening. And you can see values of y streaming out on the screen. It's working hard. But let's go ahead and stop it with Control-C. Okay, our function clearly doesn't work for this case. The algorithm works only for non-negative inputs. The square root of a negative number is a complex number, and we didn't do anything to produce a complex number in this short function. If you're familiar with complex numbers, you know they have a real part and an imaginary part. MATLAB handles complex numbers with ease, which is a good thing because they come up in some applications in engineering and physics. We're not going to deal with them except briefly in this course. First, let's see what the built-in square root function does with minus 200. Do you see the letter I at the end here? That means imaginary. The square root function is telling us that the square root of minus 200 has a real part that's equal to 0 and an imaginary part that's equal to, well, all this. We can produce complex numbers too. There are a couple of ways. Here's one. I just typed an I after the 3. And I got a complex number that has a real part equal to 15 and an imaginary part equal to 3. Here's another way to do it. This time I put 15 plus 3 times I. MATLAB sets the variable I equal to the square root of minus 1, and you can use it to make an imaginary number. If you set I equal to, say, 7 in the meantime, and then try this again, well, it uses the 7. If you want to get I back to meaning the square root of minus 1, clear it. Well, let's just look at it. Now you see I is equal to the square root of minus 1, which is the imaginary 1. That's how you can produce complex numbers, and it wouldn't be hard to fix our function so that it would return the correct complex answer for a negative input. But we didn't do that, and as a result, the condition in the while loop will never become false for a negative input. So MATLAB gets stuck in this loop. A loop that'll never end is called an infinite loop, and it's a feature only of while loops in MATLAB because that's the only place it can happen. A for loop can never become an infinite loop because the loop will always quit when the loop index reaches the end of its list of values. And there's no way to set up an infinite list of values accidentally or on purpose. But since while loops are susceptible to this problem, we have to be very careful how we set up the condition of a while loop and how the variables in the condition are changed in the body of the while loop so that eventually the condition will become false. While we're developing a program with one or more while loops, it's very common to make mistakes that cause one of those while loops to get stuck in an infinite loop. When MATLAB is seemingly not doing anything, always remember to check the bottom left corner for a busy message. If you see that, you know MATLAB is not dead. It's still working on your program. By the way, some very complex computations can run for a long time, even on today's fast computers. So whether you're using for loops or while loops, MATLAB may still take a very long time to finish your function. In that case, you'll see the busy sign, and you'll know it's working. But if it's taking too long, you can always use Control-C to stop the program, whether it's caught in an infinite loop or it's plowing through a calculation that you just don't want to wait for. Sometimes during the iteration of a for loop or a while loop, after some of the iterations are done, the rest of them should just be skipped. Let's look at an example of this situation and some code that takes care of it. The code is in the file named break examples over here. And it looks a little different from files that you've seen before. First of all, there's no function keyword in the file, so it's a script. But also this script, unlike the other scripts we've seen in this course, is divided into sections. Here, let me give it a little more room. I think I'll just clear the screen here. There. This is a section, this is a section, this is a section, so on. A section is a set of lines that begins with two successive percent signs. A section ends when another section begins, or at the end of the file, like this one. You'll remember that the percent sign signifies that it and the text that follows it on the same line are part of a comment, which is there only for humans to read. MATLAB colors a comment green. When there are 2% signs in a row, it means that a new section is beginning. MATLAB indicates that there's something special about that with a bold font. This font and this font is bold compared to that one. The significance of sections is that each section can be run by itself, as if it were the only thing in the script. You do that using special buttons on the editor. They're up here. We'll look at them in just a minute. But first, let's look at the first section of this script. Not this one, actually the second section, which has a while loop in it. It sets all the values in the vector named readings, this vector here, equal to 0 until it's reached the first value that exceeds 100. The condition here in the while loop makes this happen with two parts. The first part here, before the ampersand, allows the loop to continue only while the index is not greater than the length of readings. And the second part allows it to continue only while the readings are less than or equal to 100. You may remember that a major difference between a script and a function is that a script has no arguments, and it has no local variables. It uses the variables in the command window workspace. Since the script here reads the variable readings, we need to give readings a value. Let's give it a row vector of 20 random integers. And we'll reset the random number generator first, so we can regenerate the same set of pseudo-random numbers for the next two examples, and so that you can easily repeat this exercise with the same results. I've generated numbers, ranging from 1 to 105 here. I want to get at least some numbers above 100. And I see I've got some here. First one appears to be on 1, 2, 3, 4, 5, 6, 7, 8 at element 9. Now let's run example 1. I click anywhere inside this section, and when I click in that section, it's highlighted in yellow. Then I come up here to the ribbon, and I click the small green arrow with the tiny yellow page of text behind it here that says Run Section. Well, it didn't seem like anything happened, but let's take a look at readings. Aha! We can see that the 1, 2, 3, 4, 5, 6, 7 first 8 elements are now 0, and nothing has happened beyond there because over here the while loop got to element 9, realized it wasn't less than or equal to 100, so it skipped the rest of the iterations. It did the first 8 iterations, skipped all the rest of them, which is what we wanted it to do. Well, this works fine, but the condition of the while loop seems a bit cumbersome. All this here. Or at least let's call it cumbersome to give us an excuse to show you another way to do this. Example 2 provides another way. Let me highlight it. First of all, it uses a for loop instead of a while loop, as you can see here. Its control statement easily enforces the requirement that the index stay within the range of indices of the vector readings, but there is no possibility for the control statement of any for loop to check any condition whatever, the way there is with the control statement of a while loop up here. So it seems at this point that the loop will scan all the elements. The body of this for loop contains just one if-else statement. That statement checks the value of element II of readings here to see if it's greater than 0. If it is, it executes this break statement. Otherwise, it sets the element equal to 0. The word break here is highlighted in blue because it's a MATLAB keyword. And this same keyword is used in the same way in many other languages. It's not the same thing as a breakpoint. These things we've set when we click up here and make a red circle to tell the debugger to stop on a given line. Now this break statement is an executable statement that causes the loop to end immediately, and it works for both while loops and for loops. And it's a more powerful mechanism for ending a loop than a while condition, because in addition to skipping the subsequent iterations, it can skip the rest of the statements in the current iteration. Here, for example, there could be more statements after this if-else statement, and every one of them would be skipped if this break statement were executed. In short, the loop quits as soon as that break statement is executed, regardless of where it occurs in the loop body. Let's try this example. First, we give our vector readings the same pseudo-random number sequence as before. See if I can find that there. And now we click anywhere inside the next section of code, this one, example 2. Last time we did example 1. And we hit the Run Section button again. Well, let's see if it worked. We have to look at readings. And it looks like it worked again. All these values before 101, which were originally less than 100, are now set to 0, and the rest have been untouched. But let's go over one more time how it worked. We enter the for loop, and it appears that we're going to process each element of the vector because of the phrase I equals 1 colon length of readings. But that doesn't happen. As long as this if statement finds that the value of element II of readings is not greater than 100, then the else clause dutifully sets that element to 0. But when the if-else statement finds that the value is greater than 100, it enters the if clause and hits the break right here, which ends the loop immediately. By the way, the break statement can appear only inside a loop. In fact, MATLAB will stop the program and print an error message if it encounters a break anywhere that's not inside a loop. Okay, both these examples work, but we've got another example. It also uses the break statement, as you can see here, but it takes advantage of MATLAB's answer to an age-old question in programming languages. When the loop ends, what happens to the for loop index? Well, in most languages, and MATLAB is one of them, it's still there, and it keeps the last value it had while the loop was executing. And that's true whether the for loop ended normally or ended with a break, and whether it was set by the for loop control statement or by a statement inside the body, etc. Occasionally we can take advantage of the fact that the loop index keeps its last value. For example, suppose the problem is simply to find the first index with a value greater than 100 without setting smaller values equal to 0. Example 3 was designed to do just that. It starts out with the apparent intention of scanning through all the elements of readings with II equals 1 : length of readings. And its body is an if statement, though, and it uses a break statement to exit the loop at the first element that's greater than 100. After the loop comes this fprintf statement, which tells us the index of the first reading above 100. Looks pretty good. Let's try it. We'll generate the same values once again. You'll recognize them by now. And we click in the last section and then click the Run Section button to run the code. And over here we see it says first reading above 100 is at index 9, and that's correct. This seems to work well. But there's a bug lurking in this code. Can you see it? It'll give the wrong answer in many cases. Let's try one of those cases. We just need to give it values that are all less than or equal to 100. There. Now let's run it again. Seems to think that the last element is greater than 100, but it's not. Well, let me see if I can figure out the problem. Gosh, I'm kind of tired, though. Hey, I know what. I'll let you fix it. It'll be good exercise for you to exterminate this bug. And since you're going to take care of that, we're done with our little script and its sections. But I got to show you one feature of scripts with sections that is quite cool. Let's go up here to the ribbon and click on the tab labeled Publish here. There are lots of things you can do here, but I'm going to show you just one. Let's click this button labeled Publish. And what shows up is a web page version of your script with fancy typesetting and layouts and links and so on. Let's compare the two. Here we have the top label, might call it a title. It's been put in red, nice large type. The version of MATLAB you have may vary this a little bit. This is the latest version as I'm speaking here. And then there are these sections here. Each one of those is put inside this thing called contents. And if we click on these, we see their links. Like there's example 1. If we click there, we're on example 1. You can see the code. here's the comment I've got in example 2. Skipping is accomplished with a break statement. Let's go to example 3 down here. Shows that the for loop index looks very professional. And it even runs each one of these. There was no output with the first 2, but this one has output. First reading above 100 is at index 20. Well, that reminds me that bug is still there. You hadn't fixed it yet. Maybe we don't want to show this, but if we did, you can link it into other web pages, you can email it, you can show it to your friends. I think that's quite cool. And by the way, this web page is stored in a little folder inside the current folder that's generated by Publish. If you go in here, you can see break examples, which was the name of this M file, .html. Let's go back up to where we were before. Okay, now, what were we talking about? Oh, yes, you were going to get rid of that embarrassing bug, that we discovered when we ran this third example. And speaking of bugs, there's an extremely common bug that shows up when break statements are used in nested loops. It's a big problem for novice programmers. Not that, being a novice programmer is like a bad thing. Many of my favorite people over the years have been novice programmers. I used to be a novice programmer myself. But the fact remains that novice programmers have trouble with this problem. The problem is that the break statement breaks out of only the innermost loop, meaning that it will cause the loop it appears in to terminate, but the outer loop will continue. That is often not what the new programmer expects. We're going to look at an example that works with a two-dimensional array. So let's generate one. There's a nice array. We want to look at each element in row major order. That's first row, then second row, and so on. And set the elements equal to 0 until we find the first value that's greater than 90. We want to leave that element and all the other elements after it as they are. So in this case, we want to put all zeros on this first row because there's nothing greater than 90 there. Then we move to the second row, and we put 0 here and here. But when we get to the 97, we stop. We don't put a 0 there. And we leave everything else as it is, and we're done. This is a job for for loops, and since we want to be able to stop before we get to the end, but we can't know where we want to stop until we get there, it's also a job for the break statement. Here's our first try in this file called bad break. As you can see, there's a for loop here whose index II goes from 1 to the size of a, 1. Size of a, 1 means the first dimension of a, which is the number of rows. Then there's an inner loop whose index jj goes from 1 to the size of a, 2. The size of a, 2 returns the second dimension of a, which is the number of columns. So II is set equal to 1. We go in here and jj goes from 1 to 8 because there are 8 columns in A. And it checks the values of the elements jj against 90. And if they're less than or equal to 90, it sets them to 0, else it breaks. Well, that looks pretty good. Let's try it. We can run it by typing its name. We can also run it by clicking on Run up here. That works well for scripts, so let's do that. So bad break ran, and let's take a look at A. Something's wrong. We should have set the first row equal to zeros. We did that. Then we should have set these two equal to 0. We did that and stopped with the 97, and it looks like we're stopped, but then we seem to start up again on the third row. 2 more zeros. And wait a minute, this 63 here got set to 0 too. This is exactly the problem we were talking about. The break statement stopped the inner loop but not the outer loop. Well, this example is just complicated enough to warrant the debugger. First, I'm going to clear the command window because I want to print some things in there. And then I'm going to set A back to the value it had before. There. Okay, I'm going to set a breakpoint, but before I do, I'm going to remove the semicolon here after this 0 because I want A to print out. And I want it to print out each time through the inner loop, and that will make it do it. Now I'm ready to set a breakpoint. I'm going to put it right here at the beginning. Whoop, it's gray. That means that I have to save this. That means that the file that I'm breaking is not the same file that I'm looking at here. Okay, we're ready. Let's run it. I'm going to click Run. And we see that bad break is run. The K means we're in the break system, and so this little green arrow, which points to the next statement that's going to be executed. We haven't done anything yet. We're about to enter the outer loop, so I'm going to take one step. When I do this, you see that little hint there that shows you, depending on your operating system, a shortcut you can use for this. On the keyboard, I like to use the button, so I'm going to do that. So we go in here, and II is set equal to 1. If you hover over the II, you can see its value is 1. Now we're about to enter the inner loop. Let's do that. Now we see that II is still 1, JJ is 1. And we're checking the value of A, II, JJ, which is A11. It's 81. If it's less than or equal to 90, we'll set it equal to 0. And of course it is. So we're going to enter this if branch and set this equal to 0. So let's carry that out. And when we do, you'll see the whole array A printed out. That's what happens when you assign any value to an array and leave the semicolon off the assignment statement. Not just the element that you assign, but the whole array prints out. And that's kind of nice for us here. We can see what the array looks like, and we can see how it was changed from the last time. Just this 0 showed up here. Okay, we're ready to complete that iteration of the inner loop. And now here we are at the second iteration. The outer loop still has II equal to 1. The inner loop now has it at 2. And we're about to check the element 1, 2, which is also less than 90. And you can see it's set to 0. And we can continue in this way, going all the way through the first row. And every single thing on that row gets set to 0. Now we've finished that row, and that puts us at the end of the inner loop, and we're down here at the end statement of the outer loop. And you know the end statement will cause the II to take on its next value, which is 2. So let's go forward one step. Okay, we're now back at the top, and we're about to enter the inner loop again. This time II is equal to 2. We'll be a little more careful here. So now we've entered that loop. II is equal to 2. JJ is equal to 1. So we're going to be looking at this element right here, which is equal to 90. It is less than or equal to 90 because it's equal to 90. So we'll go into this branch again. There we did. And we'll carry it out by setting that element equal to 0. Let's do that. And it got set equal to 0, as you can see here. So we're at the end of that iteration. Let's take another step. II is still equal to 2. We're still on the second row. JJ is now equal to 2, so we're looking at this element. It's 28. It'll be less than 90. So we enter the if branch. We set it equal to 0. You saw it become 0 there. Now let's take one more step. We've entered the third iteration of this inner loop. I is equal to 2, JJ is equal to 3, so we're about to look at this element. This element is not less than or equal to 90, it's 97. So we'll go to the else branch. There we are. We're about to execute the break statement. And the break statement, we were expecting to exit the whole thing, but it's only going to exit the inner loop. So let's watch that happen. There, we jump down, we're out of the inner loop. We've jumped down to the next iteration of the outer loop. I is now equal to 3. So we're down here on the third row. Now we see the problem. We needed to break out of the outer loop at the same time we broke out of the inner loop. We needed to break out of this loop when we broke out of this loop with this break statement. Well, now we know what went wrong, so let's quit our debugging session. We can do that by clicking the great big red square here labeled Quit Debugging. There, debugging session is over, and one indication that it is there's no green arrow here, and another one is that we don't have the K in front of our prompt anymore. We've established that we need to break out of the outer loop as well as the inner loop when we find what we're looking for. So how do we do that? Well, we've got code here that does it in goodbreak.m. Let's take a look at that. Well, first we see a new variable here called found. We set it equal to false before we even enter the outer loop. Then inside the inner loop down here, where we have the break, we set found equal to true before we execute the break. And then in the outer loop, after we're done with the inner loop, we check found to see if it's true. There are two versions of the conditional for checking the value of found. The first version is found double equals true, like this. That certainly checks to see if found is equal to true. And the second version is the one we've got here. Either case works because in both cases the condition will be true if and only if found is equal to true. If found is true, then we break out of the loop. We've already broken out of the inner loop right after we set found equal to true, and so we break out of the outer loop and we're done. The variable found, which shows up in 3 places typically, is called a flag. A flag usually has only a few values, and most often just 2 values like this, true and false, the most common. And it serves as a signal that affects the behavior of the program. Here the behavior is to exit the outer loop or not. And the flag is the standard solution to the problem of exiting nested loops. There is another way, but it can only be used when A, the nested loop is inside a function, and B, it's appropriate to exit the function when you exit the nested loops. You just replace this break in the inner loop with a return, and you can forget this part and this part and this part. In other words, you can forget all the breaks and all the flags. Return leaves the function for good, regardless of how many nested loops there are. But if you have work to do in the function after the nested loops are done, then it's not appropriate to exit the function when you exit the nested loops. And it typically isn't appropriate. So you should remember how to use a flag. Well, let's get our nested loops back the way they were by doing a few of these undos. There. And with that, we're done with the break statement. But there is a related statement called the continue statement. It's similar to the break, but instead of using the break keyword, you use the continue keyword. And instead of quitting the loop, it skips what's left of the current iteration of the loop and moves to the next iteration. In a for loop, the loop index takes on its next value and the next iteration begins. In a while loop, it just goes to the beginning and checks the loop condition again. But probably the biggest difference between the continue statement and the break statement is that the continue statement is just not used very much and the break statement is used a lot. So we're not going to cover the continue statement in this course, but if you're interested in it, check it out in the textbook. We've seen the power and flexibility of loops. Now we're going to see another powerful feature, one that's unique to MATLAB. It's called logical indexing. Let's start with a problem and its traditional solution. Given a vector v of scalars, create a second vector w that contains only non-negative elements of v. Doesn't sound too complicated. In fact, though, there are a couple of subtle things in this problem that you might not get right the first time you try to solve it. Here's a solution. Let's go through it line by line. First, we initialize w to be the empty array. We've got to do this because that's the answer we need if there are no non-negative elements in v at all. If we don't initialize w, then for the no non-negative elements case, w will end up being undefined at the end of our program. In the second line, we introduce a new variable called jj and set it to 0. jj is necessary because we'll need to add elements to w one by one, and we'll use jj to specify the position in w at which to add them. It can't be the same index that we use for v, because they won't remain in sync as we copy some elements of v but not others. So we've got to have two different indices for the two vectors. And we got a simple for loop whose loop index ii can be used to index into v. We need to hit every element of v, so ii goes from 1 to the length of v. At each iteration of the loop, we need to check whether the current element of v is non-negative. In other words, whether it is greater than or equal to 0. We do that with an if statement. If vii is non-negative, we need to insert it into w. We do that by first incrementing jj by 1. Remember, it started at 0, and we need to do that every time there's a new element to add. Then we copy the number into w at the correct position. wjj equals vii. Again, notice how we use one index for w and another one for v. And that's it. The remaining two lines are just the end keywords closing the if statement and the for loop. Handling jj is a little tricky, but it's not terribly complicated, and this is the way you'd do it with a typical programming language. But MATLAB is not a typical programming language. MATLAB provides a much more elegant and intuitive solution, a solution that's more, well, MATLAB-like. Let's start with the solution that we've come up with so far. Well, with MATLAB, we don't need to mess with jj at all. Let's get rid of that. There, jj's gone. But now we're assigning vii to w. That's not what we want. What we really want to do is stick vii onto the end of w, like this. The hard work is done by the single expression on the right of the equal sign. It constructs a vector that has all the elements that are currently in w, followed by vii, left bracket, w, vii, right bracket. And we assign this new vector back to w. It's much clearer here that we are appending vii to the end of w than it was with the other version, not to mention it's shorter. MATLAB is just so nice to work with. And folks, it gets even better. The ultimate MATLAB solution to this problem, and many like it, is one single line of code. In fact, it's less than 10 characters. If I could have the drum roll, please. Really? Okay, we don't have the drum. Anyway, here it is. It's concise, it's elegant, and it solves the problem. If you don't believe me, just pause this video and try it out in MATLAB. I'll admit that this syntax looks a bit unusual. This is an example of logical indexing, and it definitely needs some explaining. But what it says is that the elements of W are set equal to the elements of V wherever those elements are greater than or equal to 0. In order to understand how it works, though, we first need to look at logical arrays. We've actually seen logical arrays already. We just didn't call them that. Last week, we saw that MATLAB considers everything that's non-zero as logically meaning true and 0 as logically meaning false. And when we ask MATLAB to give a logical true value, it returns 1. The greater than operation was applied to each corresponding pair of elements in the two vectors, like 4 and 5. 4 isn't greater than 5, so it gave 0 for false. -1 is greater than -9, so we get a 1 for true, and so on. In effect, it goes through each pair asserting that the left element of the pair is greater than the right element, and it returns 1 when the assertion is true and 0 when it's false. The result is a vector of logical values. These are not just ordinary numbers. The ones and zeros that are output by the greater than operator, or by any other relational operator, are special. They belong to a special type of value called the logical value. We'll see later that there are lots of types of values in MATLAB, but for now we'll just point out that we've seen ordinary numerical values like you get when you do arithmetic, we've seen characters, and now we've seen logical values like you get from the relational operators. And we just got a logical array in the form of a vector. Well, there are other ways to produce arrays of logical values too. Consider this command. So what happened here? The first element of this vector is true. 2 is greater than 1, so we return a 1 for true. Second element is false, so here comes a 0. These are logical values. And what about the third one? Well, we've got 3 greater than 2, that's true, and 4 greater than 5, that's false. So true ANDed with false gives false. But then we apply the not operator here, symbolized by this tilde, to the false, and that turns it into true. And, well, finally, we get a true here. Now, we knew that these results here were logical values because the relational operators give logical values. Well, now we'll tell you that the logical operators, in addition to the relational operators, return, well, of course, logical values also. So this is an array of logical values. It's a logical array. We can also create a logical array using a built-in function. Can you guess what its name is? Well, this ought to give you a clue. No, the name isn't Holmes. The name is logical. And it takes each one of these inputs in this vector, and it looks at every element in this vector, and every element that's non-zero is turned into true as a 1, and the zeros become logical zeros. All of these are of the type logical. A very nice feature of MATLAB is that it lets you index into an array using a logical array of the same size. Let's gin up a row vector with 3 elements, called A. Easy. Now we're going to index into A using a logical vector of the same size, namely C. So what does A left parenthesis C right parenthesis mean? Well, to MATLAB, it means that it should select those and only those elements of A where C has the logical value true. So it did that, and the result is a two-element vector consisting of the first and third elements of A. When an array of logical values, instead of ordinary numbers, is put in parentheses after the name of an array, this is always the way it works. The output is an array of values located at the positions where the logical values are true, and the output array is usually smaller than the input array, as it was here. It's called logical indexing. Here the first and third elements of the vector C were true, first and third here. The second was false. So in this case, MATLAB returned a two-element row vector consisting of the first and third elements of A. Well, let's put Holmes to work on another case. We've got a random set of integers in R, and as usual, I've initialized the pseudo-random number generator to make it easier for you to reproduce what I'm doing. I'll do that every time. Let's look at Holmes again. There. 2 1s, 2 0s, 2 1s. And now, let's do this. As you can see, the 1s picked up the 9 here, the 10 here, the 7, and the 1. And the 0s caused the 2 and the 10 to be omitted. So the output is 9, 10, 7, 1. This sort of indexing can be quite a mystery at first, but once you see what Holmes is actually doing here, it's not hard to understand at all. In fact, you might say it's elementary. And now we're ready to use logical indexing to do something useful. Suppose we've measured 10 voltages and saved them in a vector V. Furthermore, suppose we know that if our measurement process were perfect, there wouldn't be any negative numbers. So we want to remove these two negative values here, -2 and -3. Well, we could, of course, just remove them by hand from this little vector, but suppose that this is a really long vector, maybe thousands of elements. So we need code that will do it automatically. Well, we can do it this way. First, we make a logical vector like this. Let's look at this statement carefully. We know this is an assignment statement because of this equals here. On the left is the variable keepers. On the right is the expression we're going to evaluate and then assign the result to keepers. Well, that's v greater than or equal to 0. Well, the greater than or equal, like all the relational operators, is an array operator. So the 0 is compared to every element in turn of v. And we get that the first one and the second one are greater than or equal to 0, but the third one, as you can see, -2 here, is not. The fourth, fifth, sixth, seventh, we get to the eighth, that's the -3, it's not. And the other two are. So we've got all these ones and zeros representing the truth and falseness of the assertion that v is greater than or equal to 0, which means each element of v is asserted to be greater than or equal to 0. Now we can use keepers to do logical indexing on v, like this. We're going to set the result into w. These two zeros, in other words false, causes the corresponding elements in v, the -2 and the -3, to be omitted, and then this shorter vector is assigned to w. We did all this with just 2 commands. That's pretty good. But one command would be better. One line, one command, same result. It has to be the same result because we're doing exactly the same logical indexing. We just avoided the step of storing the logical array produced by the expression greater than or equal to 0 in keepers. And we used it directly in the logical indexing here. You should recognize this command, by the way, because it's the same command that I showed you on the slides that replaced 8 lines of for loop code. This version is a lot easier to program than the for loop version, and it runs faster, 10 to 20 times faster. We'll show you how to time code in just a little bit. In this speedy little command, we use the vector v in a relational expression here to construct a logical array that we use to index into the same vector v. But the logical array doesn't have to be derived from the array it indexes. For example, suppose that when the voltages in V were measured, there was a detector running that measured a confidence value for each measurement, and the values ranged, say, from 100 down to 0, like this. We can use this vector to discard values in the vector V for which we have low confidence. Let's say we want to keep only the values in V for which the measurement confidence was at least 10. We can do that with this command. So what happened here? Confidence was compared with 10. This is an array operation, so each element of confidence is checked to see if it's greater than or equal to 10. And if it is, we get true, otherwise we get false. So we get true, 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 false, false, and then a true. Well, that's used to index into V. Everywhere there's a true, we get something out of V. When there's a false, well, it's omitted. Let's see what V looks like. Here's V. So that's going to be true, 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 all the way till we get to these next to the last elements, these two here, and they are omitted. As you can see, between the 30 and the 45, those elements are gone. If we wanted to keep, say, the ones with confidence of 20 or more, like this, then fewer elements in V survive. So now you know how to use logical indexing to omit elements that are smaller than some threshold value. And of course you could omit them if they were larger than a threshold, or if they were equal to some bad value, etc. But there's another way to select elements to omit. Let's look at this example. There we have another 10-element row vector called V naught. Now look at this statement. Here we're using V and V naught in this relational operation here to compare each element of V with the corresponding value in V naught. We can think of V naught as a whole vector of threshold values, one for each element in V, and we'll get true only if V's element is greater than V naughts for each element. Since we're using the resulting logical vector to index into V here, we get rid of each element in V that's not greater than its particular threshold. So if we look all the way back up here at V, the first element of V, 56, is greater than the first element in this threshold vector, so it gets kept. The next element, 34, is not greater than the threshold 35, so it disappears. The minus 2, well, it's bigger than minus 8, so it shows up, and so on. Okay, we've killed off a lot of elements with logical indexing, but it's important to point out that the vector that we've been indexing into is not changed. The omission takes place when the expression on the right of the equal sign is evaluated. So up here, for example, V confidence greater than or equal to 10. That's evaluated. We come up with some trues and falses. That's applied to V, and the expression produces this vector. This vector is then assigned to V10, but V remains unchanged. Well, there is another way to use logical indexing that does affect the vector being indexed into. The effect is not to remove elements, though, but to change their values. You do that by using logical indexing on the left side of the assignment statement. So suppose, for example, that you wanted to replace all the negative values of V with zeros. First, let's remind ourselves what's in V. There. Now let's replace all the negative values with 0. That's these two, the -2 and the -3. We're going to replace those, and here's how we do it. Sure enough, the -2 is now 0, the -3 is a 0, everything else is untouched. So here, V minus 0 produces a logical array again, with true values only where the values of the elements are less than 0. And the meaning of this statement is that the value on the right side, the 0, is copied into those two elements, and only those two elements. Notice that no elements in V are lost. We still have a 10-element vector here, but some of their values are changed. 2 of them in this case. This might be a helpful summary of what's going on with these two different ways to use logical indexing. Logical indexing on the right, like over here, produces a subset of elements. Logical indexing on the left changes a subset of elements. In this case, they were changed to 0. But you can also change each one to a different value. Let's see how to do that. Start with the same V again. Now let's assign 100 to the first negative element and 200 to the second one, using logical indexing. When you have a vector of 2 or more values on the right, as in this example, the length of the vector has to equal the number of values that will be picked out on the left, which is 2. And so what happened? This element was negative, and this element was negative, so they were picked out for assignment. And the first value here was assigned to the first one, so the -2 became 100. And the second value was assigned to the second one, so the -3 became 200. And now let's do both left and right logical indexing in one command. First, let's get that original V back again. There it is. And let's suppose you need to add 100 to each negative element for some reason. I don't know why. Here's how you do that with logical indexing. So what's happening here? Well, first, the V indexed with V less than 0 here on the right side produces a 2-element vector containing only the values -2 and -3. Second, 100 is added to that vector to get the 2-element vector containing a 98 and a 97. Third, on the left side of the equal sign, the logical indexing picks out only the 2 elements of V that have negative values, which happen to be the same elements that we looked at over here on the right, the -2 and the -3. The -2 is at position 1, 2, 3. The -3 is position 10, 9, 8, 3, and 8, elements 3 and 8. And fourth, it assigns the first value that it got over here, which was 98, to element 3. The first one was less than 0. And the second element that it got over here, which was a 97, to the next element that was less than 0, which was element 8, the -3. And so now it's a 97. None of the other values were touched. And that's how you use logical arrays on the left and right in the same command. So far, we keep saying logical arrays, but we keep using only logical vectors. Matrices and higher dimensional arrays work fine with logical indexing, but there's a big surprise coming. Let's clear the screen and get ready for it. We'll start by making a 2x3 array. And now we'll use logical indexing to set a variable b equal to a, but keeping only the elements of a that are greater than 2. Before I hit return, I'll point out that this is just the normal right-side logical indexing that we've seen before. A greater than 2 will return true at every element that's greater than 2. So it'll return true here, 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 and it'll return false for elements 1 and 2 here on the first row. That logical array of trues and falses is then indexed into A, and it'll cause the 1 and the 2 to be omitted, and the 3, the 4, and the 5 and 6 will come on through. So let's hit return and see what happens. Surprise! What happened to our nice 2x3 array? And where'd this column vector come from? Well, remember way back at the beginning of Lesson 2, what we first said about arrays? No? Well, I guess I'm not surprised. That was a long time ago. Okay, I'll say it again. We said that an array is just a set of numbers arranged in a rectangular pattern, and that each row has to have the same number of elements as all the other rows. You know, like this. Well, if we were to simply omit 1 and 2 on row 1 and leave the rest of it the same, this row would just have this one element, 3. Row 2 would still have 3 elements, and 3 be hanging out way over here on the right. It looks something like this. I'm not sure what you'd call that. It's sure not an array. Well, what MATLAB does is give up on keeping the 2x3 shape that A has. It just makes a column vector by stacking up the columns of A, column 1 on top, then column 2, then column 3, before it does its logical indexing. Well, let's see what that vector looks like first by using the single colon as an index. Do you remember that? We showed how to do that in Lesson 3. So A looks like this, and the column version looks like this. There, we've used that single colon to index into A, and that gives us the column version of A. You can see that it starts with the first column, then the second column, and finally the third column. This is called column major order, and that's why we gave it that name. Now that it's converted A to a column vector in column major order, MATLAB applies the logical indexing to the column vector, like this. And there's the result, just the same as what we got directly up here. This is a strict rule. When you use logical indexing to an array on the right side of an assignment, then if the array is not a simple vector, it will always be converted to a column vector in column major order. And by strict, I mean, well, strict, no exceptions. Here, not one single element of A was omitted by the logical indexing on the right here. They're all here. So there's not one single reason to change its shape, yet its shape was changed to a column vector. Rules are rules. This is logical indexing. A is not a vector, so the result's a column vector in column major order. Case dismissed. And in MATLAB's court, there are no appeals. But wait. If you use logical indexing on the left side of an assignment, none of this column vector business happens. Logical indexing on the left of an equal sign just changes the values, you'll remember. It doesn't omit any elements. So the problem of keeping the array rectangular never even comes up. So there's never really any need to convert the array to a column vector, and the array just keeps its same dimensions. For example, here's how to set all negative elements of a 5 by 5 array to 0. I've used the random normal function here, which gives numbers distributed around 0, both positive and negative. Now let's get rid of those negative numbers. Replace them with zeros. The 8 negative values have been replaced by 0, and A is still a 5 by 5 array. And it can keep its same dimensions because no elements are omitted by indexing on the left. And you can replace these 8 values with 8 different values, like this, for example. What MATLAB does is take the 8 values on the right, the 101 through 108, and assign them to the 8 elements that were singled out by the logical indexing on the left. An important feature is revealed here. Logical indexing on the left assigns these values to the elements that were singled out in column major order. So it scans the first column up here, looking for a negative number. It finds one here on the third row, and it assigns the first value from the right, which was 101. So this becomes 101. It continues looking on that column for negative numbers, doesn't find any. Since it's doing column major order, it goes to the next column, finds one right up here at the top. It gives it the next value from the list on the right, which is 102. See that shows up. Then it finds another one immediately, gives that 103, finds nothing more on this column, goes to the next column, and so on, until it's replaced all 8 negative values with all 8 values from the right. And it's done right here. It doesn't make any difference what the shape is of the array of values on the right, so long as there are 8 of them. It could be a 2 by 4 array or an 8 by 1 column vector. It works the same. In fact, let's do the column vector version. I'm tired of looking at A, so I used a semicolon to suppress printing this time. The single quote up here transposed the row vector 101 to 108 to a column vector, but the result's exactly the same, as you can see by comparing here. But it makes a big difference if the number of elements on the right is different from the number of elements found by logical indexing on the left. That's just a non-starter. But if you get the numbers to match up, the assignment works, the numbers are assigned in column major order, and A retains its shape. So we've seen that MATLAB converts a non-vector to a column vector when logical indexing happens on the right of the equal sign, and it leaves the shape the same when logical indexing happens on the left. But wait. We saw a few minutes ago that you can have logical indexing on both sides in the same command. What happens then? You can't have it both ways. Looks like MATLAB has finally painted itself into a corner. Let's look at an example. Suppose our task now is to find the elements in A that are greater than 0.1 and replace each one of them with its square root. First, we'll get A back. Okay, here goes. So we've got logical indexing on the left, which means A retains its shape. And we got logical indexing on the right, which means A is changed into a column vector. Let's hit return and see if smoke comes out of this computer. Ha! Rules are rules, huh? Well, MATLAB, how do you explain this one? We've got logical indexing on the right, but the shape of A stayed the same. Well, as much as we might want to catch MATLAB in a contradiction, we haven't. It applies logical indexing on the right to omit all the elements of A that aren't greater than 0.1, which leaves 17 elements, and it puts those 17 elements into a column vector in column major order. We don't see it anywhere, but that's what's happened. It used that column vector as input to the square root function, which returned a column vector of 17 square roots. Then over here on the left, it used the same logical indexing that we used on the right and identified the same set of 17 elements as needing to get new values. And then finally, it assigned those 17 values in the same column major order that it generated them over here. It all works perfectly. MATLAB wins again. If you didn't know what's going on here, this command would be very cryptic. But a MATLAB programmer, like you, knows what's happening. And it's all self-consistent and logical. It is logical indexing, after all. If you were using C or Java, on the other hand, you'd have to write 2 nested for loops with an if statement in the body to get this thing accomplished. You can do that in MATLAB too, of course. Come to think of it, as an example, you should implement the same thing without logical indexing. Well, we're done with our introduction to logical arrays except for one quick example. It's an example of multiple arrays, all logically indexed in the same statement, just to show you that it works. There we've got an array A and B. They're both the same size. Here, each element in A that's larger than the corresponding element in B, so 89, for example, is larger than 34, is replaced by the difference between the two elements, so 89 minus 34 shows up here. 11 doesn't change because it's not greater than the corresponding element in B. It's still 11. If you spend a minute or two analyzing it, you'll see that the rule is applied that the same number of elements is produced on the right and consumed on the left. Well, with this example, we say goodbye to logical indexing. But don't forget it whenever you need to remove or change selected elements in arrays. Logical indexing is a powerful MATLAB feature that can save you from writing many loops. Use it wherever you can. Okay, I promised to tell you how to time a function. It's very easy with MATLAB. You time a function with the help of 2 other functions called tick and tock. Their names are supposed to sound like a clock ticking. You know, tick tock. Tell you what, go rent an old horror movie. They have lots of tick-tocking clocks in them. Anyway, tick and tock work more like a stopwatch than a clock. Tick starts the stopwatch, tock stops it. Well, let's time something. Let's time sum adding up the first 1,000 positive numbers. Well, I thought it would never get done. That took, what? A little over 1,000th of a second. Let's give it more work. There are 1,000,000 numbers. That took a whole 100th of a second. Okay, time to really put it to work. Let's give it 100 million numbers. 1 second. These computers are pretty fast. But let's run this much slower function instead. It's one that I've got over here called No Prealloc. We'll find out what that strange name means in a minute. And let's put this command window right underneath the editor down here. And I'll bring it up a little closer. And now that I've got things arranged to my liking, let's have a look at this function. What it does is use explicit looping and these nested for loops to compute a good old-fashioned multiplication table and put it in A. We're going to calculate 25 million of these numbers because we got n equals 5,000, so 5,000 times 5,000, that's 25 million. So we better get going. Well, okay, yeah, this is taking a long time, so sorry about that. It's kind of boring. Tell you what, maybe this is a good time for a joke. All right, did you hear about the guy they asked how he felt about death? He says, you know, I'm not really afraid of dying. I just want to die peacefully in my sleep like my grandfather, instead of screaming in terror like his passengers. Okay, as the laughter dies down, the function still seems to be working away. Here's one of these times where you start wondering, okay, 46.86 seconds. That's a pretty long time, but you know, we did a lot of work there. 25 million calculations. Yeah, we did a lot of work here, but on a modern computer, 25 million calculations should go a lot faster than that. Here's a faster version of the same function called prealloc with just a single extra line added right here. Here we've created a matrix A by calling the function zeros and made it a 5,000 by 5,000 matrix. How can this help? We're still going to do the same 25 million calculations, and then all those zeros will be written over. It seems like we're wasting time, and we're going to make an already long function take even longer. And I don't have another joke ready. But let's get comfortable and start it running. Wow, that's a little better. 0.596 seconds. That's how many times faster? Let's calculate that. 78 times faster. How can this be? Well, in the no prealloc version, MATLAB had no idea how large the matrix A is going to eventually become. So every time we added a new row, it had to find another place in the memory and copy the entire contents of the current array into the new location before it could add the next element. Finding a place in memory and reserving it for a variable is called memory allocation, and it had to do memory allocation over and over and over. While memory allocation is usually a minor part of the time required for a program to run, if we have to do it thousands of times, it can take a noticeable amount of extra time. That's bad news. But the good news is that most of the time this extra time is completely unnecessary. In this example, we knew before the loop started how large the matrix A needed to be. So in the second version, we initialized A to the right size before starting to compute its elements. That avoided all the time MATLAB spent on memory allocation and reallocation using the first version. Allocating memory before you need it is called pre-allocation. Kind of an obvious name, I guess. The way you do it is call a function. We use the function zeros, whose arguments tell it the dimensions of the array to allocate. It'll allocate the space and put zeros into every element. There's another function like it named ones. Let's just say I won't insult your intelligence by telling you what that function does. But at the risk of a tiny insult, I'll give you this advice. Pre-allocate every time you use a large array whose dimensions you know. And guess what? MATLAB gives you that same advice. It's easy to miss. Let's look back at this no pre-allocate function. The advice is right there. If you look very closely, you'll see a little red squiggle right here under this A. And if you hover the mouse over the A, you see a little hint pop up. First one says the value assigned to variable A might be unused. Okay. The second one says the variable A appears to change size on every loop iteration. Consider pre-allocating for speed. The textbook has a more detailed explanation about why this version without pre-allocation is so much slower than the other version. And it gives you a simple trick for speeding things up when you can't pre-allocate by simply changing the order in which you nest your loops. Well, that's about it for Lesson 6. But we'll leave you with this parting thought. Loops, whether they're for loops or while loops, whether they're explicit loops or implicit loops, are the programming constructs that let us exploit the amazing power of computer hardware. The power of that hardware is measured in billions or trillions of memory cells and billions or trillions of instructions per second. But without loops in the software directing the circuits in the hardware to iterate repeatedly through the paltry few commands that we humans can type into it, these big impressive numbers would mean nothing. The amazing things that computers do, like searching through 30 trillion web pages, answering spoken questions in multiple languages, pulling your car out of a skid on a slick road, landing a rocket on Mars, calling the one phone you want out of 7 billion, or even just playing this lesson for you, would just not be possible without loops. Well, to be more precise, they might be possible, but only if you had a few billion years to get them done. If you don't want to wait that long, iteration's the only way to go. It's simple. If you look into every world-changing effect that computers have had in the last half century, you'll find a loop down there somewhere inside driving it.
Hi, and welcome to Lesson 7, Data Types. MATLAB provides many ways of storing numbers and variables, operating on them, and printing them. We've seen lots of examples of numbers being stored, operated on, and printed. And these examples suggest that these numbers are equivalent to the real numbers of mathematics. But that's not the case. In mathematics, real numbers can be infinitely large, and they have infinitely fine resolution, meaning that the difference between two different numbers can be infinitely small. On the other hand, computers have a finite amount of memory, so there must be a limit on how large a number represented in the memory can be, and there is. Also, there's a limit on how small the absolute value of a non-zero number can be. And if you think about it, the finiteness of the memory means that a MATLAB variable can't store an irrational number. So, for example, the function pi returns not pi, but only an approximation of pi. And the square root function can return only an approximation of the square root of 2. The most important thing to learn here is that the number of values that can be represented by a variable in MATLAB is finite. And by the way, that's true for any computer language. This may seem like a pretty significant limitation, but for the vast majority of problems that we want to solve on the computer, the set of numbers that can be represented by a variable is more than adequate, by far. The subject of this lesson is data types, and data types can help handle this limitation. MATLAB supports many different data types, and they provide great flexibility in dealing with numerical and non-numerical data. A data type is sometimes called simply a type, and it's defined by a set of values and a set of operations that can be performed on those values. As we've seen, MATLAB allows a given function to be called with different data types. But there's a strict rule. All elements of a given array must be of the same type. It's the array's elementary data type.
In fact, the type of a MATLAB array is given by its number of dimensions, its size in each dimension, and its elementary data type. Well, let's play with data types in MATLAB. Let's start by clearing the workspace. And let's create a new variable. Of course, you do that by assigning a value to it. So we got this variable x. Let's find out what its data type is. We do that with a function called class. And it tells us that x is of type double. That's the default data type for all numerical data in MATLAB. And that's not just for variables. It's for values too. For example, if we just give it a value without assigning it to a variable, MATLAB will still treat it as a double. By the way, why is the function called class instead of type, since we're checking the types? Well, MATLAB reserves the name type for a command that prints out the contents of a file, as in type the file. Let's get a little tricky here. Of course, you know that the square root of -1 is an imaginary number, so you might expect the class to say something about that, but no, it just calls it a double. MATLAB supports complex numbers, but it doesn't distinguish among real, imaginary, and complex numbers when it's classifying them into types. Let's make some more variables. Now let's look at a new function that gives us even more information about them. It's called whos. First of all, whos prints out a list of the existing variables in the current workspace. Simple. As you can see, x, y, and z all have double over here in the class column, as you'd expect. Over here, the size column shows the array dimensions. X is a 1 by 1, since all scalars are treated as 1 by 1 arrays in MATLAB. Y is 1 by 8, as any well-behaved 8-element row vector should be. And Z is a 3 by 4 matrix. You may find the data type for ANDs surprising here, char. Well, how did that happen? What's the value of ANDs anyway? Let's see. Double. Well, is ANDs a double? No. Remember, this is the value of ANDs we're seeing here. And that value is a string whose characters are double. And how did the value of ANDs get to be a string? Well, it happened back here at this command class square root of -1. That was the last command we issued in which we didn't assign the output to a variable. The class command returned the data type of the output of the square root, and that happened to be a double, and returned that information as a string. Since we didn't assign the string produced by the command class to a variable, MATLAB assigned it to ANDs. Of course, when we enter a string, as for example when we type the format string of an fprintf statement, we have to put it in quotes to let MATLAB know that it's not the name of a variable. But when MATLAB prints a string, it doesn't put it in quotes. As we'll see in a minute, a string is just a row vector of values whose type is char. By the way, I pronounce char, char, but char is also an equally acceptable pronunciation since it's short for character. And speaking of putting strings in quotes, let's look at the type of a string that we enter. There you go, a char again, as expected. So how many types have we seen so far? We got the double and the char here, but we talked at great length about one other type. That's right, the logicals. You know, the kind of value that can only be true or false. So we've seen the doubles, the chars, and logicals. Now let's learn more about these types and introduce some new data types too. As we've seen, the default data type in MATLAB is the double. That type uses floating point representation. And what's that? Well, you can think of floating point representation as being like the scientific notation that we talked about before. For example, to represent the number 12.34, we can use the fact that 12.34 is equal to 1,234 times 10 raised to the minus 2 power. So we can store two integers, 1,234 and minus 2, to represent the non-integer 12.34. In floating point representation, the 1,234 part is called the mantissa, and the minus 2 part is called the exponent. MATLAB uses this floating point representation for all doubles, and it uses 8 bytes of memory for each one of them. Since there are 8 bits in each byte, we say that the double is a 64-bit number. The single is the only other floating point type supported by MATLAB. The difference between a single and a double is the length. A single has only 32 bits. By the way, that's where the name double comes from. It occupies double the space of the single. That extra space allows for more digits, and so you'll sometimes hear it called double precision. But what if we know that we need only integers? For example, sensor values that are read into computers are typically integers. And in image processing, the color values of pixels are always integers. Well, MATLAB supports a number of different integer data types. In fact, there are 8 of them. There are 4 signed and 4 unsigned types. What does that mean, you ask? Well, if you don't need negative numbers, you should use unsigned data types because they represent only non-negative integers, 0 and higher. But if you do need negative numbers, or both negative and non-negative numbers, then you need one of the signed types. The other important attribute of integer data types is length. There are 8, 16, 32, and 64-bit variants of integer types, both signed and unsigned. And they differ in the range of numbers they can represent, with more bits giving a wider range. This table shows all of MATLAB's numerical types and the ranges that they span. For example, int 8, which is an 8-bit integer, can cover the range between minus 128 and plus 127. Well, why not plus 128, you ask? Well, the number of different values that 8 bits can form is 2 to the 8th power, which equals 256. So it can only hold 256 values, and we need to account for 0 too. The unsigned version, on the other hand, spans the integers from 0 all the way to 255. The table also shows the ranges of the other integer data types. As you can see, a 64-bit integer can store truly astronomical numbers, so it's very rare that any programmer needs integers that are larger than int64 provides. At the bottom of the table, you can see the range for the floating point data types too, and the double range is unimaginably large. But the singles and doubles can each hold values outside their ranges too. There are 2 of these out-of-range values. The first is INF, or INF, for infinity. INF most commonly comes up when we accidentally divide a non-zero number by 0. But it signifies the result of any expression that gives a number greater than the largest value that can fit in a double. And you can guess what minus inf means. The second out-of-range value that a single and a double can have is NaN, or nan, for not a number. Nan signifies the result of an expression that gives an invalid value. For example, 0 divided by 0. So that's a look at the ranges for these types. Now let's look at some functions that deal with them. Here are a couple of useful built-in functions for checking data types. We've seen the class function before. It returns the name of its argument type. The is_a function is new. It returns true or false, depending on whether the first argument has the data type whose name is given in the second argument. The int_max and int_min functions give the maximums and the minimums of the integer types. And real_max and real_min do the same thing for the floating point types. We'll try them out in a minute. In addition to the functions for checking types, there's a set of functions that do conversions among them. The need to convert a value from one data type to another comes up from time to time, and there are built-in functions whose names are the same as the desired types to be produced by the conversion. We'll see these functions in action in just a bit. Of course, what we do most often with values in MATLAB is arithmetic, and there are rules for arithmetic that depend on types. First, all arithmetic operations have no problem accepting two operands of the same type, and the result is always a value of that type. But MATLAB also allows some mixing of data types in arithmetic expressions. It's called mixed mode arithmetic, and there are many rules and restrictions on what's allowed and on the type of the result. These rules can be a bit complicated and somewhat cumbersome, so we'll skip them here. But if you need to work with mixed mode arithmetic in your programs, the textbook explains the rules in detail. And finally, some good news. Relational operators work with any mixture of numerical data types just fine. And not surprisingly, the result always has the same type, logical. Now let's play with numerical types in MATLAB some more. First, let's just create a few numerical variables with types other than doubles. The way to do that is to use the built-in functions with the name of the given data types that we need. For example, we just converted the double 98.76 into a single and put it in X. And we just converted the double minus 16 into an int 8 and put that in N. And we put a uint 16 into M. Let's see what we've got here. There's our three variables. There's their three types. Their sizes are all 1 by 1 because they're all scalars. That works smoothly. Well, what if we try to assign a number that doesn't fit in the given type? Let's look at some examples of that. What's happening here, as you can probably see, is that the conversion function is producing the number that's closest to the input value that can be represented in the given data type. Here we're dealing with the uint 8 data type, and it can hold the integers from 0 to 255. So 500 doesn't fit. It's bigger than 255, but 255 is the biggest number, so it's as close to 500 as you can get. 256 is just a hair too big, so we get 255 again. Here's minus 1. Well, an unsigned int can't hold a negative number, so we get 0. So what's happening here exactly is we start with this minus 1, which is a double. Since any number you just type into MATLAB is a double by default, it's passed as input to uint 8. uint 8 then converts that minus 1 to the nearest 8-bit integer possible, which happens to be 0. The function then returned that value as a uint 8 type. So we've got a uint 8 0 coming out of uint 8. Then MATLAB assigned that value to k. So k now has the uint 8 data type, and its value is 0. So let's look at k. It's 0. Let's look at its type. uint 8. This changing of an out-of-range value to the value at the closest end of the range is sometimes called clipping, because the operation clips off the excess of the value so it'll just fit into that range. Here 500 was clipped to 255 and minus 1 was clipped to 0. MATLAB's assumption here is that you know what you're doing. You explicitly asked it to convert a big number to a type that it can't hold, or a negative number to a type that can only hold positive numbers. So rather than throwing an ugly red error message at you and stopping your program in its tracks, it silently clips the big number down to size or the negative number up to a 0. So in this case, now k is equal to 0, and its type is uint8. But you have to be careful here. Look what happens if we decide to increase k to some other value that fits inside the range of its type, uint8, say 2. Okay, it's now 2, and let's just check its type. Well, its type is now double. The moment we assigned 2 to k, its data type changed. The number 2 is a double by default. So when we assigned it to k, k ceased to exist as a uint8 and became a double. It's really quite logical. If we now assigned it a string, say, you wouldn't expect k to remain a double, would you? And you'd be right. K didn't remain a double, it became a char. This illustrates a rule in MATLAB. When a variable is assigned a value of a new type, the variable takes on the new type. Many other languages work differently. A variable is declared to be of a given type, and it keeps that type. And if you were to assign a value of type char to k after it's been declared to be a double, then either an error would occur or an invisible conversion would take place right there on the spot during the assignment statement from double to char, with the same sort of clipping happening. One approach is different from the other. Not better, just different. They each have their pros and cons, but once you know what the rules are, it's all quite logical. Boring, but logical. And to keep with this theme, the boring theme, I'll show you how you can check the ranges of the types you want to use so you'll know when clipping is going to happen. There are 4 built-in functions that we can use to do that, and here's some examples of them in action. Let me clear the screen first. Bet you wish you could type that fast. We saw these same values in that table a little earlier, of course. It's pretty straightforward stuff, but it can be important when you're working with very large arrays of numbers whose range is small because of the application, such as image processing, for example, and you don't have room to store 64-bit doubles, so maybe you want to use 8-bit or 16-bit or 32-bit integers. Then this stuff won't be boring anymore. Wait, who am I kidding? This stuff will always be boring. But at least it'll be useful. Text is another important kind of data that computer programs need to manipulate. And in computer programming, we call any segment of text a string. We've used strings before. For example, the format string of the built-in function fprintf is, as its name implies, a string. And we've just used the int_max function, where the argument was the name of the data type that we were interested in, and that's a string. So what is a string in MATLAB really? Well, it's a vector of characters. In other words, it's a vector whose elementary type is char. We saw this when we used the class function earlier in this lesson, so it shouldn't come as a surprise. What will be surprising, though, is that char is a numerical data type. A char is actually a number, and behind the scenes there's an encoding-decoding scheme that specifies what number represents what character. The oldest such character encoding scheme is called ASCII, pronounced ASCII. ASCII stands for American Standard Code for Information Interchange, and it was developed in the 1960s. An ASCII character code is 7 bits long, so it can encode a set of 128 characters. As you can see in the table, the ASCII set includes the Latin alphabet, the digits 0 to 9, punctuation marks, and some special characters. For example, 36 is the $, while 97 is the lowercase a. Of the special characters, we care about the new line character, abbreviated NL, and having the code 10, and the space marked SP and encoded as 32. 128 characters seemed like plenty in America in the 1960s, but nowadays, well, we need more. Just think of all the characters in all the world's languages, and most importantly, all the emojis that we just can't live without. So over the years, many other schemes with far more characters have been developed. The good news is that little old ASCII is a subset of pretty much all of them. Let's dig a little deeper into this subset. Here's a function that prints out all the visible characters in the ASCII table. It uses a for loop with a loop index that starts at 33 and ends at 126. 33 is the encoded value of the first visible character in the ASCII table, which happens to be the exclamation mark, and 126 is the value of the last visible character, which is the tilde. Inside the loop, one character is printed at a time using fprintf with the %s format string. You may remember that %s expresses a string, so the second argument of fprintf is the value of the loop index converted to a character by the char conversion function. After the loop, we print a new line as usual, and that's all there is to it. Okay, let's see how this thing works. I got it right over here in its M file. And there it is in the editor. I'll just run it. And it works as advertised. Here at the beginning is the exclamation point that we get from ASCII code 33. And over here at the end is the tilde, whose code is 126, with all the other printable characters arrayed here in between. As it turns out, we can make it even simpler. As I said, the %s in the format string of the fprintf function tells the function to expect a string argument. More exactly, what it tells the function is that whatever argument it gets should be converted into a char. So we don't need to use the conversion function char here. We can simply use II. And the %s will treat it as if it were a char. Let's try that. Same result. And if we want to look like a wizard, we can even change the last line like this. Which says to fprintf, print the number 10 as if it were a string. 10 happens to be the code for the new line character. So if we tell fprintf to expect a string and then give it the number 10, it will convert it to a char with the value 10, which is just the new line character. And we get the same result again. This time we're magically getting characters out of nothing but numbers up here. And what does character mean exactly? Well, these so-called characters that we're looking at here, the ones that are being printed to the screen, are actually just arrangements of tiny black, white, and gray pixels that look to our eyes like familiar symbols whose meanings we know. Let me turn on my magnifier here and show you what's really there. There. See those little gray pixels and white pixels and black pixels and so on? Look like a 1. They look like a 2, a 3, a 4, and so on. Well, here's a D, an E, etc. So we give MATLAB a number, tell it to treat it as a character, and it produces a pixel pattern that symbolizes something to us. Okay, we peeked behind the curtain and found that there's no wizardry in strings at all, just ordinary numbers, a conversion table, and some pixels. The rest of it's all in our heads. Let's play some more with strings. This was plan B if the title Computer Programming with MATLAB didn't work out. Now I'm going to treat this string just like a vector, just to prove there really is one. There, you can check its length. Like up here, you can index into it. Here's number 1 index. You can use the colon operator to give it multiple indices and use the and so on, just like you can with any vector. Those are advantages, but there are disadvantages too. Because they're vectors, comparing two strings is not as easy as comparing two scalars. So let's see. You cannot just compare two arrays with the double equals operator if they don't happen to have exactly the same size. It violates the rules of array operations. And even when our two strings are the same length, the result of the comparison is probably not what we want. Let's illustrate that with the word MATLAB, which we'll pluck out of this title again. You ever ask yourself what MATLAB spelled backwards is? It's Baltum. As in, that stupid bug showed up out of the blue. It was just totally Baltum. Anyway, MATLAB and Baltum are the same length, so we can use them as operands for the double equals operator. So let's try it out. We get a vector of logicals, which is what you get for any element-wise comparison of vectors with a relational operator. Instead of the answer we want, like, these strings are not the same, we get one answer for each pair of chars in these two strings. And since, as it happens, only the A's match up, the second and the fifth elements are the only true values in the resulting vector. The rest of them are false. In a minute, I'll show you a helpful function for comparing strings that'll give us the answer we want. But for now, I'm going to show you how to have some fun converting chars to doubles. Okay. We started with a string. We converted it to a double, and now code is just a vector of doubles. Let's tweak the values in code just a little bit and then change the code back to a char. So we're adding 3 to every element of code. Then we convert it from a double to a char, and we put the result in secret. Let's see what it looks like. Will you look at that? We've encrypted our message. We can send this to our friend now. Even if it's intercepted by the teacher, he won't have any idea what it says. But our friend is a MATLAB programmer too, so she can decode the message easily. Here's how she'll do it. All she has to do is know the secret tweak, which was to add 3, and she just undoes that by subtracting 3. Told you it was going to be fun. We found another advantage of the fact that a string is a vector. We can send secret messages. And on the subject of a string being a vector in MATLAB is just a one-dimensional array, so we've in fact got an array of chars here. So can we have a two-dimensional array of chars? Yes, of course. Bill is an array. Well, it's a one-dimensional array, so it's a vector, and it's the first row. Mary is the vector of the second row. John's the third row, and so there's our array. It's a two-dimensional array of char. Let's try another one. So that works great too. So far we've had a 3 by 4 array, and now we've got this 2 by 8 array. Let's do an array operation on this array. We'll do a transpose. We're on a roll here. Let's get a little more ambitious. Oh no! What just happened? What kind of an animal is a vertcat anyway? Well, vertcat is a built-in function, not a feline. MATLAB uses vertcat internally for vertically concatenating the two vectors we provided into a matrix, but it didn't work here. Can you guess why? I cannot hear your answer for some reason, but I'll give you the benefit of the doubt. Yes, that's right. We were trying to create a matrix in which the two rows, this one and this one, had different lengths. You'll see this error message quite often because there are lots of times when you'll accidentally try to give the rows of an array different lengths. To help you remember what vertcat means, it might be worth pointing out that vertcat is a contraction of vertically catenate, because catenate and concatenate mean the same thing, just like inflammable and flammable. In this case, MATLAB complained because the first line of the text had 28 characters, tiger, tiger, burning bright, while the second, in the forests of the night, had only 27. Oops, that's a big no-no in MATLAB. So you have to be very careful. In fact, typically you shouldn't try to store strings in matrices because they're rarely of the same length. We'll show you how to store strings the right way and how to compare strings the right way too. These tasks and others that deal with strings require a little finesse, but fortunately MATLAB provides specialized functions and additional data types that'll make it easier.
MATLAB provides a set of very useful built-in functions to help us deal with strings. We'll recommend a few of the most useful ones, which can help us with 5 common tasks involving strings. First, searching for a substring inside a string is made easy with the function named findStr, which means find string. Second comes conversion of a number to or from a string. Now that we've learned about strings, we know that a double with the value 123 is not the same as a string of characters 1, 2, 3. They look the same, but they're fundamentally different. One's a floating point number, and the other's a vector of 3 chars. However, you can convert back and forth between them using num to str for number to string and str to num for string to number. Third, when we need to compare two strings, we've seen that the double equals operator doesn't really do what we want. Well, the strcmp function does, and its name, in fact, means string compare. Fourth, it's often necessary to change between upper and lowercase letters. For that, we can use the function named lower to convert a string to all lowercase, and upper to do the opposite. Fifth and finally, sometimes we need to print with fancy formatting into a string instead of into the command window or into a file. For that, we have the sprintf function, which means string print formatted, and it's often pronounced sprintf. It's a snap to learn because the only difference from fprintf is that sprintf puts its result into its output argument. Okay, let's try these functions out.
Let's try searching first. So what does the 4 mean? It's the index of the first letter of the first occurrence of the substring in the string. Okay, now let me try that in English. We're looking for LAB, and we found it. The first time we found it, in this case the only time we encountered it, is at position 4 in the string. 1, 2, 3, 4. Character 4. That's where the first character of the string LAB occurs in the string MATLAB for Smarties. It's the first place the second argument occurred in the first argument. But remember, these strings are case sensitive. Let's try this. This time we get the empty matrix. MATLAB in the title up here is in all caps. So there is no lowercase LAB in this string. So there's no index to return this time. That's why we get the empty array. And I'm sure you've heard it said that there's no I in team. Well, let's check. Well, that proves it. I is definitely not in there. Sorry. No, I am. No. Anyway, so far we've either not found the substring we were looking for or we've found it once. Let's do one more example in which we see what it looks like when we find something more than once. The substring R, right here, shows up in two places in MOOC title. Let's see, MOOC title was MATLAB for Smarties. And there's an R right here at the end of the word for. That's character 10. And there's an R in Smarties, which is the 15th character. So find string returns the vector 10, 15. Okay, that's it for searching strings. Now it's time to compare strings again. Remember the trouble we had before when we tried to do that with a double equals operator? Well, now we're better equipped to tackle this problem because we know about the string compare function, strcmp. Okay, let's review what happened here. First of all, we reminded ourselves what was in MOOC title, MATLAB for Smarties. Then we defined this variable lang by setting it equal to the string MATLAB. Then we compared MATLAB for Smarties with MATLAB. Well, MATLAB for Smarties is not the same as MATLAB. MATLAB's a substring of it, but they're not the same, so we get a 0, or false, meaning they're not the same. Next thing we did was just take the first 6 characters in MATLAB for Smarties right here, compared that with lang. Now they're the same, so we get true, or a 1. Couldn't be any easier. It returns true or false depending on whether the strings and the two arguments are the same or not. Case sensitivity applies here too, but if we don't care about that, we can use strcmpi, which stands for string compare ignoring case. Let's try that. Well, we get true. Clearly, MATLAB is not the same string as the first 6 characters of MATLAB for Smarties because this is in all caps. But this little I here in strcmpi means ignoring case. Ignoring case, they are the same, so we get a 1. This ignoring case has nothing to do with anything other than characters that are letters. Doesn't affect punctuation, doesn't affect digits. By the way, if you ever need to convert a string to lowercase or to uppercase, check out the built-in functions lower and upper. Let me emphasize again how different strings containing digits are from numbers. The only difference here is I put quotes around the 3.1416 down here, but that makes this a string. These two variables have values that are completely different. This is a number, this is a string. We know that because we just typed them in. But MATLAB doesn't put quotes around the string here, so it is easy to confuse these two sometimes. There is one subtle hint. Numbers are indented, strings are not. Let's see how different they are. First, they have different dimensions. 1 by 1, it's a scalar. 1 by 6, it's a row vector of 6 characters. And speaking of characters, they have different types. And look what happens if you try to use them in arithmetic. No surprise there. 4.1416 is 3.1416 plus 1. But look at this. What is this? Well, what's happened here is that we've done mixed mode arithmetic. We've added one value, that's a char, to another value, here the 1, that's a double. A bit earlier in this lesson, we mentioned that the rules for mixed mode arithmetic, mixed mode meaning mixed types of operands, are complicated enough that we're leaving it to you to look them up in the textbook. But I'll explain what happened here. The rule for mixing chars and doubles is that before the addition, the char is converted to a double. So it's as if we did this. We get the same result. If we look at the term on the left converted to a double, it all makes sense. The 51 became a 52 and we added 1 to it, the 46 to a 47, and so on. It's just array addition with a vector and a scalar. It makes sense, but it's not something we'd want to do, unless we're encoding secret messages again. What we might want to do is convert the string 3.1416, way up here, to the number 3.1416, and then add 1. You'll sometimes find, for example, that your program must read a string of digits that a user typed in or that's in a file, and then it has to convert it to a number and do arithmetic on it. Well, by now you're probably tired of me. Well, I could probably just stop right there. You are probably tired of me. I'm tired of me, for goodness sakes. But what I was going to say was, tired of me posing a problem just so I can have an excuse to introduce just the perfect built-in function to solve it. Okay, but be that as it may, there is just a perfect built-in function that'll solve this problem. It's called str, the digit 2, num, which means string to number. Let me write it out here. And I'll give it pi digits and convert it. Notice that it's indented over here. That's a little hint that this is actually not a string, but a number. And let's prove it's a number by adding 1 to it. There, 4.1416. And you probably won't be surprised to learn that you can go in the other direction, number to string. And notice that this isn't indented. Let's try to add 1 to it. And there we go. It's deja vu all over again. Okay, there's just one more string function that I want to show you. Remember earlier when we were saying that there was this function sprintf, and it's a snap to learn because of how similar it is to fprintf and so on? No? Well, that's okay. All you need is one example and you've got it. It's easy, don't worry. Let's see. Okay, we've got a variable r12, and we want to use fprintf first to print something to the command window involving r. Here goes. Okay, that's straightforward. We've got this format string here with the format specifiers, escape symbols, and so on. And the first argument, r, is printed point to f, 2 decimal places. Then pi r square, printed the same way. And we put a little exclamation point there, and that's it. Now, I'm going to repeat this command by using the up arrow key on my keyboard. But I'm going to come over here and change one character. I'm going to change this F to an S and see what happens. Okay, here we go. Nothing. This is sprintf. Everything is the same. Everything you've learned about fprintf is the same. But where'd the output go? Well, instead of printing to the screen, sprintf puts the text into an output argument. We didn't see anything because we put this semicolon here. Let's give it an output argument that it can stick things into. I'm going to hit the up arrow key again and come over here, and I'm going to give it an output argument str for string. There. Still don't see anything because we still have the semicolon, but now we know that there's something in str, or at least we hope so. Let's have a look at it. There we go. The area of a circle with radius 12 is 452.39. Same exclamation point, everything's the same. Even that line feed showed up here. That's why there's a space. So you can see that sprintf constructs a string using a format string, using arguments after the format string, just in exactly the same way that fprintf does. Except it puts the result into an output argument. And what's the type of the output argument? It's a string. It's elements of type char. Well, that's it for sprintf, and that is all I have to say about strings.
We've learned that all elements of an array must be of the same type. Such arrays are said to be homogeneous. But what if we want to group together heterogeneous data somehow, that is, data of multiple types? Well, MATLAB, like many other languages, provides ways to do that. The easiest way is to use a struct. A struct is different from an array in three ways. 1. Structs have fields, not elements. 2. We access the fields of a struct by names, not indices. And 3, fields within the same struct can have different types. What's especially cool is that the field of a struct can be another struct, and that ability of a struct to have another struct inside it makes structs very versatile. The syntax for creating or accessing the field of a struct relies on the period, or dot. If we type r.ssn equals 1, 2, 3, 4, 5, 6, 7, 8, MATLAB will create a new variable named r, make it a struct, create a field called ssn for that struct, and assign it the value 12,345,678. So the syntax is simply to put a dot between the variable name and the name of the field. Easy. Now, if we check the data type of the variable r with the class function, we get struct as expected. But if we check the data type of the SSN field, we get double, which is also what we should expect since we assigned a number to that field. Okay, so we've created a brand new struct. Now we can add a new field to that struct simply by typing r.name equals, quote, Homer Simpson, end quote. MATLAB will modify our struct by adding a new field called name, and it will assign the string Homer Simpson as the value of that field. Now here comes the cool part I mentioned. Typing r.address.street equals single quote 742 Evergreen Terrace single quote creates another field for r called address. And because of the dot after address, this new field is itself a struct with its own field, which is called street. And then it assigns the string 742 Evergreen Terrace to the field street of the field address of the variable r.
As you can see, MATLAB doesn't print the inside of this new struct in the command window directly. Instead, it just signals that the field address of the struct R is another struct. As I said, allowing a field to be a struct makes structs really versatile. But there's more versatility here than that, because structs can hold arrays, and arrays can hold structs. In other words, a field of a struct can be an array, and it goes the other way too. An element of an array can be a struct. But in that direction, we encounter the homogeneity rule. All array elements must be of the same type. So if they're structs, they must all have the same fields. We'll see some examples shortly, but first, you'll not be surprised when I tell you that MATLAB has some useful built-in functions that deal with structs. For example, isField will tell you whether a struct has a certain field. You just give it the struct and the name of the field you're looking for, and it'll return true or false. And setField can add new fields to a struct in a dynamic manner, meaning that you don't have to know the name of the field when you're writing your program. The user can specify it while your program is running, for example. Another handy function is called RMField, which means remove field. It can produce a struct that's a duplicate of another struct, except that a specified field is missing. You give it the struct and the name of the field you want to remove, and it returns a copy with that field removed. Finally, if you want to create a struct with a set of names in one shot, you can simply call the function nameStruct and give it the field names you want as arguments. Okay, we've learned about structs, and now we're ready to see them working in MATLAB. Information about a bank account is pretty heterogeneous. An account has an owner, which is probably going to be a string, an account number, which will be a number, and a balance, which will be a number, etc. Let's create a struct that represents a bank account. The value that we've assigned to the variable account here is a struct. Class will tell us that. And its first two fields are doubles. Its third field is a struct, as we can see right here, called owner. And owner has a couple of fields, which we can look at by typing the variable name, dot, and the name of the field, owner, to see what's inside it. And it has two fields. When we see these two fields with this colon here, we know that we're looking at a struct. And they happen to be both of the same type. As we can see, these quotes are included by MATLAB when it gives the value of a struct field that happens to be a char. If we want to turn a count into an array of structs, it's easy enough to do. We just give it another element. And we did that by assigning something to one of its fields. As you can see, MATLAB prints out only the field names once we have a struct array. Also, the new struct, well, the second element of the array, magically has all the same fields that the first element already had, not just the account number we created. This has to happen to keep the types of both elements the same. Remember that homogeneous rule? If some elements had one set of fields and others had another set, well, homogeneity would be out the window. So what values are in these fields that showed up automatically? Well, let's just have a look. Well, they're initialized to the empty array. Let's assign values to more fields of our new struct. If we want to see the entire struct, we can do this. But if we want to see the value of a field of a substruct, we have to type in the entire hierarchical name. the array name, the index in parentheses, the dot, the field name, another dot, and the field name of the substruct. Well, let me just do one. And I'll do the other one. While the structs must have the same field names, the values stored in those fields don't have to match. They can have different types and or different sizes. For example, the length of the strings in owner.names are different for elements 1 and 2. Let's prove that. One's 9, one's 11. And substructs don't even have to have the same set of fields. There we've added a substruct to owner, given it the value 23 for element 1. So what about element 2? Does a new field called age show up under its owner with maybe a empty matrix or something in it? No. Reference to non-existent field age. It doesn't even have that field. The homogeneity rule for arrays is only skin deep. It extends only to the first level of the fields. Every element of the array account has to have the fields number, balance, and owner, but different things can be inside them. Okay, that's a look at how fields of structs are accessed and the homogeneity rule for an array of structs. Now let's try some of the functions that work with structs, some that we've mentioned before. First, let's clear this cluttered screen and look at the owner field of each element of a count. Putting that 1:2 in there makes it show each one of these elements. And we see there's quite a few things in 1 and not much in 2. Well, let's look at isField. So what we see here is that isField takes this argument, which is account 2, the second one, dot owner. It looks at the field of account 2 called owner and checks to see if there's a field in there called age. Well, there's not, so it returns false or 0. Then we do the same thing with element 1. Well, if we go inside owner for element 1, we find there is a field called age. And so we get true. As we said, isField returns true or false, depending on whether the given structure has a field with the given name. And then there's RMField, which you may remember removes a field from a struct. Let's remove age from account1.owner. There, age field is gone along with its value, which was 23. You give the thing you want to remove the field from, then you give the name of the field that you want to remove. Now let's just check to make sure that it's gone. Wait, why is age still there? We just removed it. Well, we've made one of those rookie errors. The function RMField doesn't change its argument. This was its argument, account1.owner. That's not the way MATLAB works. It returns a changed version of its argument. That's what we saw here. So when we checked out the argument that we gave it, it's unchanged. It's still the same. If we want to change it, we have to assign something to it. That's easy to do. We do it like this. First of all, I'll click my up arrow and get that command back. Then over here, I type account1.owner, and the result from RMField will be assigned back to it. So let's hit return and see what happens. Now let's check. Age is gone. Okay, we got one last function that works on structs to look at, and its name is struct. You remember when we started all these struct examples, we needed to have some structs to work with, and you do that by giving a variable some fields. We started out by giving a count, the field named number, and then we gave it balance and so forth. We kind of did it piecemeal, one field at a time. But you don't have to do it that way. You can do it all in one fell swoop with a built-in function whose name is struct. Like this. Man, I got my typing in high gear here. I am smoking it. Okay? Whoa. Remember, we're professionals here. We don't recommend you try typing like this at home. But anyway, the inputs to the struct function come in pairs, organized as field and value. So here was the field called area. Here's the value called CS, and you can see it showed up here. Here's a field called number, and 103, which is a double, is the value for that field. Title, there you go. This method of setting values for fields by processing a list of field value pairs is not unique to MATLAB. It first appeared in a language called Lisp, which means list processing, shortly after Fortran was invented in the late 50s. Lisp and derivatives of it are still used today for writing programs that have artificial intelligence. We're still using this method of giving values to fields. Good ideas never die. And with that bit of programming language history, we conclude our coverage of structs. How would you store a page of text? As we've seen, two-dimensional arrays are not a good way to do it because each row, that is each line, would have to be the same length. Storing it in a single string is not appealing either because you can't easily access individual lines. We could store each line in a separate string, but then how can we group these lines together? Wouldn't it be great if we could create a vector of special objects that would link somehow to each one of these strings? Well, it turns out that we can. But what are these special objects? Well, they're called pointers. To understand what pointers are, we have to take a step back. Each variable, be it a scalar, a vector, an array, a struct, or anything else, is stored in the memory of the computer, and each memory location has a unique address. You can think of a computer memory as a very, very long vector of memory cells. And the address of a cell is the index. That is a positive integer starting with 1. Consecutive addresses indicate neighboring memory cells, and a pointer is simply a variable that stores a cell's address. To make it just a tad bit more confusing, though, MATLAB calls a pointer a cell. And MATLAB doesn't allow you to treat a cell as if it were a number. There are strict rules on what you can and cannot do with cells. But those rules are for your own good because it would be very easy to shoot yourself in the foot with pointers repeatedly and painfully if you could, say, do arithmetic on them or whatever you wanted to do with them. Nevertheless, the cell is a very powerful and very useful data type because cell arrays, like structs, let you group heterogeneous data together, which is what we wanted to do with strings from a page of text. But unlike structs, cell arrays can be indexed with numbers, and partly because of that, while they're a bit trickier, they're used more frequently than structs. Since cells is a new concept, it shouldn't be surprising that there are new syntax rules. To access the object that a cell points to, you need to use braces, also called curly braces or curly brackets. To actually use cells, let's solve our original problem by using them to create a variable that stores multiple lines of text. Okay, I've got a script over here named cells of text. It'll give us what we want. This script is divided into two sections. It's the first section. It says the ultimate legend of Big John. And let's see what it does. First line sets the first element of page to the string. You can find him on the field almost any day. These braces here tell you that this is going to be a cell. So this value will now be pointed at by the first element of page. Second one set to the string, tall, dark hair and eyes of steel gray. The third one, they say, pulled a frisbee about half a mile. You'll see this pair of single quotes here, and you'll remember that two single quotes together inside a string translate into one single quote. In the fourth and the fifth line, you see another one of those pairs, and when he'd stick it in the corner, you could almost catch a smile on Big John. Must be quite a guy. Anyway, let's run the first section. Of course, you remember how to do that. You just click Run Section. You don't see anything happen because every single one of these assignment statements has a semicolon at the end of it. But something must have happened. I think Page should have gotten a value. Let's check that out with the function whose. Sure enough, it's a 1 by 5 array, in other words, a vector, a row vector, of type cell. We can access individual elements of Page by using braces. There's the first element. You could find him on the field almost any day. Let's look at the fifth one. What's in 5? Well, it's pointing at the string on Big John. And to double check whose, let's get the type of page with the class function. So this, of course, means that each element of page is of type cell. But as we said, each element of page points at something else that can be of varying size and or type. In this case, the sizes of the elements are different. Let's look at a couple of them. Let's look at the first one. Notice I've put the braces here. That means we're going to access the thing that the first element of page is pointing at. And its type is char. Of course, we knew that. It's a string. Let's look at the size of it. Well, it's a 47 element row vector. Fourth element also points to a char, and the size of that char is 1 by 65. It's a 65 element row vector. So we managed to put lines of text of different lengths into one homogeneous array of cells, which is what we set out to do. The second section up here, this one, shows you how you might use this cell array to print out the lines using fprintf. It goes to a new line here. Then it loops through the 5 indices of page here and prints each element here using the %s format and putting a new line after each one. And then it ends with an extra new line. Let's run it. I click anywhere in it, turns it yellow. And I come up here and I click Run Section. And here's what we see. You can find him on the field almost any day, tall, dark hair, eyes all the way down to Big John, with the space above and below.
As you might have guessed, cells are not just for strings. Let's create a cell array that refers to truly heterogeneous data. First, we call the cell function to create a blank 2 by 3 cell array, where blank means that each element contains the address of the empty array. Each element is said to point to the empty array, as indicated by the arrows. In this next assignment statement, the use of braces instead of parentheses for indexing the array element indicates that the address of the object on the right is assigned to that element instead of the object itself. In this case, the function pi produced that object, a scalar, which was then stored by MATLAB at a newly allocated memory location. The address of that location is then assigned to the element 2,1 of the cell array P.
Thus, element 2,1 now points at pi. It's important to take a minute here to emphasize that even though P now refers to heterogeneous data, namely an empty array and a scalar, which are of two different types, the array P itself is still homogeneous. The MATLAB cell array model allows individual elements to point at different types, but the elements themselves are all of the same type, and that type is cell. The next command is P left brace 1, 1 right brace equals int 8 of minus 17. Again, following the cell model, as with the previous assignment statement, the braces on the left mean that the address of the object on the right is copied into the element 1, 1, not the object itself. And as before, the address refers to a newly allocated location in memory. In this case, MATLAB has stored minus 17 at that location, encoded as an int 8. And we can do more than empty arrays, a double, and an 8-bit integer. Here, MATLAB allocates a new location in memory to hold the string awesome, and then makes the element of P on row 2, column 2, point to it. We show the pointer directed at the first character of awesome because the address used for a vector or array or anything that occupies multiple cells in memory is that of its first element. Next, we create a 3x2 array of doubles and assign its address to the element 2, 3 of P. Again, we show the pointer aimed at the first element, element 1, 1. But in fact, it makes no difference what element it points at because MATLAB doesn't allow you either to look at the numeric address or to change it. As we mentioned earlier, MATLAB maintains strict control over its pointers. In this statement, braces are used differently. When they're not on the left side of an assignment statement, braces indicate that the object pointed at by the element is to be retrieved instead of its address. Thus, in this case, P brace 2, 3 brace retrieves the 3x2 array pointed at by element 2, 3 of P. That array is then input to sum, and sum does what it does with any array it receives. It adds up each of the array's columns and returns the sums in a vector. From this point forward, the process is the same as for the other assignment statements above. MATLAB allocates a new memory location to store the vector from sum. Then the address of that location is copied into the element 1, 3 of P. Notice that we use braces twice in this last assignment statement. On the right, we use them to retrieve a value, and on the left, we use them to store a pointer. All of these uses of braces are necessary. If we were to try using parentheses, MATLAB would complain, in red letters. The lone cell that still points to the empty array is changed next. We create an inf of type double by dividing 1 by 0. MATLAB stores the result in memory, and then braces are used to point element 1, 2 at it. With that, we have a nice little cell array that refers to two types of scalars, one string, a double vector, and a double array. And it might show more clearly how it can be possible in MATLAB to construct an array that refers to a set of data of multiple types, despite the fact that MATLAB, like almost all other languages, supports only arrays whose elements all have the same type. And what is the type of P's elements? Well, we can call the class function to answer that question, and the answer is cell, as expected. But if we use braces to retrieve the object pointed at by one of P's elements, in this case element 1, 2, then the class function tells us the type of that retrieved object. In this case, the object is the scalar inf, which happens to be of type double. But if we use normal parentheses when indexing that same element of the cell array, then we're referring to the cell itself and not the data that it points to. So the class function returns cell. That's the difference between using parentheses and braces when it comes to cells. Well, here's a tricky one. We use both braces and parentheses, but it's all good. First, P brace 2, 3 brace retrieves the object that the cell at index 2, 3 of the cell array points to, and that object happens to be an array of doubles. Then the parentheses with the indices 3 and 2 inside them are used to index into that array. And this array indexing works as it normally would. It retrieves the second element on the third row, which is 12, as shown in the figure. Nice. Now let's see some more examples. The most important concept to remember is the distinction between a cell and the object it points to. MATLAB uses various notations to indicate that the elements of a cell array are not actually arrays, but are instead pointers to arrays. For example, it encloses all numeric arrays in square brackets, and it encloses a string in single quotes. That notation is supposed to say to the user, these are pointers to respective objects, not the objects themselves. For example, let's create a cell array of 2 cells. The first element of C points to a scalar, 3.1416, which is just a 1-by-1 array. And to remind us that the first element is a pointer instead of a 1-by-1 array, it puts that 1-by-1 array inside brackets. The second element points to a string, and to remind us that the second element of C is a pointer to this string and not the string itself, it puts the string in quotes. Now, instead of assigning a value, let's just look at the values in these cells. Once again, we use these braces here, sometimes called curly braces, to look at the object that the given cell points to instead of to set the object that it points to that we did up here. And so we get the object that it points to. Here it's the number, here it's a string. If we use regular parentheses, on the other hand, we get something different. You notice the difference? Here we got the brackets saying, yes, we're looking at a pointer here. Here we got the quotes saying, this is a pointer to a string. But up here with the braces, we got the sort of thing we ordinarily get when we look at a number, just the number, with no brackets. And we get the same sort of response when we look at a string. It's not indented and there's no quotes around it. But when you use regular parentheses with a cell element, you're asking to look at the cell's pointer. And as above, MATLAB indicates this with brackets for numbers here and quotes for strings. So when you see no quotes, you're looking at a string. And when you see quotes, you're not. Feels like we're in Bizarro world here. But anyway, that's how MATLAB shows you that the object that you've requested is a cell pointer. It's subtle, but now you know what it means and how it works. Another subtle detail about cells is that MATLAB doesn't allow 2 cells to point to the same object. Let's look at a simple example here. It consists of 2 elements, each pointing to a 1-by-2 array of type double. C1 itself, of course, is a cell. Now consider the following statement. It looks like a simple assignment operation, so we might assume that the pointers in C2 are now the same as the pointers in C1. That would mean that they both point to the same objects. In fact, that's how it appears if we look at these objects. What happens if we change one of these objects? Let's change the object at which C111 is pointing. The first element of C1 is now pointing at some nice fresh strawberries. We know it's a pointer because there's quotes around it. If C211 contains the same pointer as C111, then when we ask MATLAB to show us what it's pointing at, we should find those same strawberries. Let's try it. Instead, we find the object pointed at by C211 is the same as it was before. The strawberries are missing, and I know they were there before. I can prove it beyond a shadow of a doubt with geometric logic. But wait, let me check C1 again. Now the strawberries are there. So am I losing my mind? Well, I may be, but there's a logical explanation for what's behind these strawberries. The culprit here is MATLAB's cell pointer model. That model doesn't allow C2 to point to the same objects as C1. In fact, no two cell pointers can point at the same object. Instead, in MATLAB's version of cell pointer assignments, what happens when MATLAB carries out the assignment C2 equals C1 up here is that it first copies all the objects pointed at by C1, then makes C2 point to the copies. So we put the strawberries in the original, but the copy pointed at by C2 was left as it was. And because no two cell pointers can point at the same object, it's impossible to change an object pointed at by one cell by manipulating it via another cell. This is a strict limitation that you need to keep in mind when working with cells. For example, if you pass a cell as an argument to a function, any changes the function makes to the objects that the cell points at will not change the objects that the original cell points to. MATLAB will simply copy the cell into the input argument, and that input argument will point to copies of the objects that the original cell points to. The function can only change the new objects. Unless the objects, or the cell pointing to them, is returned from the function as an output argument, these changes will be lost. And the original cell that was passed in as an input object, it won't be changed with or without an output argument until something's assigned to it, nor will the objects it points to. This ironclad rule against two cell pointers pointing at the same object is not enforced by most languages, including C, C++, and Java, and as a result, their pointers are far more flexible than MATLAB's cell pointers. There are multiple pros and cons and advantages and pitfalls associated with both types of pointers, and hours of vigorous debate have been expended on them by people who care about such things. But if you hear someone say that MATLAB is a weak language because of this rule, don't believe them. It just means they don't know that MATLAB supports two types of pointers, and its second type works like the pointers of C, C++, and Java, with all the rights and privileges and pitfalls thereunto appertaining. They're part of the less well-known object-oriented structures in MATLAB. They're rarely used because they're rarely needed for numerical applications. But they're there. If you want to learn how to use them, they're taught in Chapter 3 of the textbook.
Here's some built-in functions that are useful for working with cells. To understand them, you really need to try them out on your own, and I encourage you to do that. And in conclusion, let me just say that cells and cell arrays are essential in many real-world problems that you may run across in the future. You'd be wise to invest the time you need to learn the concept well. And a wise investment now will pay dividends in the future. And with that programming and financial advice, we'll conclude Lesson 7. Okay, for the rest of this lesson, we're done with cells, and we're done with 2015, which is the year that I recorded the part of this lesson that you've watched so far. And we're done with that old 2015 microphone. Now, I guess I need to explain all this. I've traveled forward in time again, and I'm now speaking to you from July of 2018 with a brandy new microphone that makes me sound even better, if you can imagine that. If you watched the videos in the first lesson, which were added in March 2018, then you've already heard this more mature mic as recorded by this less mature mic. Get it? I'm a mic, and my microphone is also a mic. And see, I'm older and it's younger. Man, I just crack myself up sometimes.
My goodness. Anyway, in that segment, we showed you the MATLAB desktops for both MATLAB Online and Install MATLAB. MATLAB Online hadn't even been invented yet back in 2015, so I had to jump forward in time in order to be able to use it. And now I've gone back to the future again, so I can tell you about some new data types introduced by MATLAB relatively recently. No matter when you're watching me, this course has already covered all the data types that have been part of MATLAB since back in the 90s. You know, the double and single floating point numbers, all the integer types like int8, unsigned, int16, etc., and the char and the logical and the struct and the cell, which we just now finished with. By just now, I mean in the segment you just watched, which was recorded 3 years ago. But in the next segments, we're going to look at some new data types. If you're using an older installed version of MATLAB, you may not have these types. But if you're using MATLAB Online, then of course you'll definitely have them, because MATLAB Online is always right up to date. And speaking of being up to date, I'm using the very latest version of MATLAB, which today is, as you can see up here, 2018A. And which is exactly the same version that I was using when I introduced the desktops in the first lesson. The A in the name means that it's the first version released in 2018. MathWorks has for many years released 2 versions of MATLAB per year. The first one shows up in March and is labeled with an A. The second one shows up 6 months later in September and is labeled with, you guessed it, a B. The changes are usually not big, so you can stick with one version for a year or 2 or even 3, and you'll still be fine. We'll add one new video segment for each new data type that we think you should learn about. And you can look at the title of each video to see the name of the type and the version of MATLAB in which it was introduced. The segment that we're in now, for example, is entitled The String Type, introduced in 2017A. You may wonder how the string type, which we are introducing now, relates to strings, which is the title of an earlier segment in this lesson. We'll talk about that relationship in great detail in a few minutes, but a quick overview is that both of these types are used to hold words, phrases, sentences, etc. But as we point out in the earlier segment, the type of the strings in that earlier segment was char, not string. There were some problems with using char to hold strings, and MATLAB introduced a new type with the name string to solve them. We just finished using the old string right there near the end of our segment on cells when we formed the word strawberries. Let's get some more strawberries. In this command, we've assigned the string strawberries to the variable named fruit. Let's determine the type and dimensions of fruit by using the class function and then the size function. So the function class tells us that the type of this variable is not string at all. The type is char, which you can see right here. The name string is just an informal way of saying a vector of chars, each of which is printed on the screen as a character. S, T, R, A, W, B, etc. The size function reminds us that this so-called string is a row vector, just like any set of characters that we enclose in single quotes. And this particular one has 12 elements. Hey look, I know you remember all this char stuff and are probably edging closer and closer toward an epic case of total boredom. But before you drift off to sleep, I just can't help but also point out that when the function class returned the type of fruit right here, it did it with an output argument whose type is also char. We know that because the word char is surrounded by single quotes. Okay, hello! Sorry about that, but you should probably wake back up now because here comes the new string type. To get it, we can simply use double quotes instead of single quotes, like this. So there you go. You are looking at a new string. You can tell it's the new string because it's surrounded by double quotes instead of single quotes, the way the old string was. And there's something remarkable about these double quotes. Other languages like C, C++, and Java have used double quotes to denote a string for decades. But double quotes had to wait 40 years to be given a place in MATLAB. Congratulations, DQ. You're in the game and you're looking good. Note that our new string type gets the same purplish pink color that we got when we typed in a char. So there we are. We now have our first new string. Or to put it another way, we have our first string. I'm not always going to say new string for two reasons. Number one, you can figure it out from the context whether I'm talking about a string that is a char vector or a new string. And number two, I'm tired of saying new string. If we need to distinguish, I'll call the old version a char vector or a char string or just a char. Otherwise, string means new string. To prove that new fruit is in fact a string instead of a char, let's check it with the class function. Sure enough, it's a string. But the class function still gives its answer in the form of a char vector, no matter what type of input it gets. We'll talk about differences between chars and strings in a minute or two, but first let's talk about a similarity. Probably the most important similarity is that almost any built-in function that's designed to process a char vector will process a string in the same way. The prime example is good old fprintf. As you can see from these two commands, it's happy with a format argument that is either a char vector or a string. And then there are all the built-in functions that were designed originally to manipulate char vectors. They're also happy with the string. Let's put one of those happy little functions right here in the command window. Remember the function that we used earlier in this lesson to search for a substring inside another string? It returns all the starting positions of the substring everywhere it finds it. And the name is string find, abbreviated for the function name as strfind. We'll first make an old char string, and then we'll call string find to find something in it. Let's see. Inane refrain equals the rain in Spain stays mainly in the plain. So we've got the string to search in, and we're going to search for, the string in, like this. There, string find happily searched through the string in the first argument, looking for the substring in, which was the second argument. It found it in 6 places and gave us the index for each one of them. Now maybe we want to have another happy little string find function call. And let's do something different with this one. Let's give it a string for the first argument instead of a char vector and use the same second argument. Riddle equals bushy-headed trainer in an art form mainly planar. There. As you can see, our happy little string find function is just as happy with a string as it was with a char. And I could have used a string for the second argument too. By the way, if you need to look for more complex string patterns, like, for example, every substring that starts with a lowercase a followed by one or more lowercase letters followed by one lowercase r, then you should look up regular expressions and the built-in function that searches for them named regexp, which stands for regular expression. It'll take you a while to get used to it, and by a while I mean days. But here's how to tell it to find that substring example. And take my word for it, it found it 3 places. I could show you lots of examples of such string functions that were originally designed for char vectors but also work for strings. But for now, I'll just show you that the function upper works fine with both types and let it go at that. And of course, the function lower works just as well. So, all the built-in functions have now been tweaked by the MathWorks programmers so that they do their things with either a char or a string. In other words, as we've learned, that means that they're all polymorphic functions. Since char and string are different types, these functions have to do different things internally with them. But that's the beauty of the concept of the polymorphic function. You just give it the argument and the function looks at the type and figures out what to do. That's the best way to write any function that might be appropriate for use with more than one type, if you have the time. But let's suppose that you've already written a whole bunch of functions that require an old-fashioned char vector instead of a string, and you don't want to, or you don't have time to, change all of them to handle strings too. Well, never fear, the converter is here. Before we find out what that means, let's suppose you've written a function that reverses a row of chars, just like this one over here, called myStr function, which is supposed to mean my string function. Here's what the function looks like. It's just a one-liner. It takes the input and then it just plays it backwards for you. And let's suppose you want to reverse strawberries. Let's first see what happens when we input strawberries as a row of chars. That's what we assign to the variable fruit, so let's use that as an input. I think I'll clear this cluttered command window first. And let's move this command window underneath the editor so we've got a little bit more space. There we go. Clean slate. All right, now let's try out our function on the char vector strawberries. Well, that looks kind of disgusting for some reason, but the function is obviously working because the variable fruit contained the word strawberries, and C. Arab warts is strawberries spelled backwards. Now let's give it the variable new fruit, which contains the word strawberries as a string instead of a char vector. Huh. Didn't do anything. I'll let you figure out why, but I'll give you one hint if you need it. Think about how many elements there are in the input variable new fruit. There's only one. A string, no matter how many characters it contains, is just a single element. So how do we get this function to reverse a string? Well, we can convert the string to a char like this using the function char. Then we can use this char vector as the input, which gives us a char vector as output, and we can convert that output to a string. We need a little more room. Okay, that worked, but it requires 2 new variables and 3 command lines. Well, we can do all this with no new variables and only 1 line, like this. So here we've converted new fruit to a char, and here, after the function has returned its value, we've returned the output of the function to a string. Is that slick or what? We didn't monkey around inside the function itself. Instead, we just switched to char on the way in and switched to string on the way out. I think you've got the picture, but I want to do one more example of converting a char to a string. This example reminds us that in order to insert a single quote into a row of chars, you have to include two single quotes back to back. And it reminds me of one of the greatest Broadway musicals of all time, West Side Story. Just thinking of this poignant song gives me goosebumps. I could sing this song for you, and you'd probably get goosebumps too. Well, the kind you get when your skin crawls, but that would be the end of my video career for Vanderbilt, so I'm not going to do that. What I want to point out from this example is that the same sort of doubling requirement shows up for strings. In order to insert a double quote into a string, you have to include two double quotes back to back, as in this example. Some people make your skin crawl for a living. Andy Serkis is amazing, but as you can see, I had to put a pair of double quotes around my precious to end up with just single double quotes. By the way, you might have noticed that there's a double comma too, but unlike double quotes, the commas come through doubled in the string itself. That just shows that this double to single business doesn't happen with any other punctuation marks, or any other characters for that matter. Don't I have quite the knack for making simple things sound complicated? Maybe that means I'm a really bad teacher. Or maybe I'm cleverly making it sound like you're learning really hard stuff so you can impress your friends. Of course, it's not really hard at all, but the single versus double quotes business is the most obvious difference between the two types. This is a syntactical difference between them, and syntax is usually much easier to understand than semantics, as the semantics of the one-line string reversing example above shows. There are other semantic differences that we need to look at, of course. One nice difference is that the string type does not suffer from a particularly irritating limitation of the char type, which we ran into in Lesson 7. The limitation occurred when we tried to put more than one row of characters in a two-dimensional array of chars. Before we try that again with the char version of strings, which will fail as miserably now as it did then, let's see how easy it is to do it with the new string type. Here, 3x1 string array means that there are 3 rows, 1, 2, 3, with one string on each row. Regardless of the number of characters in a string, it's just one element. And since there is just one element on each row, this is a column vector. Okay, now I'm going to try to make a stack with the char version by using single quotes instead of double. Oops, here's that red stuff. Dimensions of arrays being concatenated are not consistent. We saw this same error earlier in this lesson. The error was worded slightly different in the 2014B MATLAB that I was using then, but the problem was exactly the same. That problem is that in this second command, this one, we are trying to make an array whose rows do not all have the same width, whereas in the first command, the ace on the first row is just one single element. In the second command, ace comprises the 3 elements A, C, E. And in the first command, king and queen on the second and third rows are also each just one element, whereas in the second command, king on the second row has 4 elements, and queen on the third row has 5. MATLAB never allows different numbers of elements on different rows of the same array, as we first pointed out in Lesson 2. Arrays are rectangles, meaning that all their rows have exactly the same width, and I can guarantee you that until that sad day when MATLAB finally ceases to exist, which by the way is over 200 years from now, it will continue to enforce that rule. What? How do I know it's over 200 years? You've forgotten I got a time machine? I know many things, my friends. And this rule, stretching forth over the centuries as it does, has nothing to do with chars or strings in particular. It's a basic rule of arrays, and all the widely used computer languages enforce this same rule. As we saw back there in Lesson 2, you'll get the same error if you try to sneak around and put different sized rows into an array of doubles instead of chars. Let's see, I don't know, let's just do this. There, the first row has 3 elements, the second row has 4, and the third row has 5. Now let's hit enter. No go. Different type, same rule, same error. If you really need a stack of different length strings of type char, you can use this handy little trick. When you give a column of strings as an input to the function char, it not only changes the type to char, but also adds just exactly the right number of blank characters to the right of each short row to make all the rows the same width as the longest row. As you can see by the space between ace and its closing quote mark, and by the space between king and its closing quote mark. So it returns a rectangular, two-dimensional array of type char. All strictly legal. Okay, we put strings on top of one another, but what happens if we put them side by side? Let's clear the command window and do that. And we'll do it with strings first. No surprise there, we put in 3 strings in a row and got out a row of 3 strings, which is, as MATLAB says right here, a 1 by 3 string array. Now let's try the same thing with the char version. So what happened here? Why did all the letters get shoved together into a single string of chars? Well, this same thing happens anytime you put multiple row vectors on the same row. You end up with a single row vector containing the elements of the multiple row vectors, one immediately after the other. It works the same way with numbers, of course. Here's an example of that. When you combine multiple strings together to produce one string, you are concatenating them, which we've talked about before. And after strings are concatenated, you can't tell where one ends and the next one begins. But sometimes concatenating strings is exactly what you need to do. So how can you concatenate strings? Well, you just add them. By add, I mean use the plus sign, which we've used so far only to sum up numbers. Here's how it works with strings. Hey, I wonder what happens if we use a minus sign. Let's try that. Wow, how about that? MATLAB figured out that these strings are numbers, and then, just kidding, I faked this one. Here's what really happened. And you'd get an error like this with any other arithmetic operator too. The plus sign is the only arithmetic operator you can use with strings. Enough with concatenation. Let's clear all that away. And get back to conversions. We've converted between strings and chars, but what about converting between strings and other types? Well, for openers, you can convert any number to a string. First, let's look at 4 examples with numbers of the type double, which is the default number type in MATLAB. And here's a 5th example in which we convert from one of the integer types to a string. This works for all the other number types too. Okay, these examples came at you pretty fast. Let's examine them a little. The 2nd and 4th examples, here and here, show that only 4 digits after the decimal place are given in the string. This is MATLAB's short precision, which is the default in the command window. The 3rd example shows that the string function also uses the default number format of the command window, which is fixed point, instead of floating point, which was the form of the input for this example, as you can see here. The 4th example might seem special because the input was pi, but remember that the input argument pi is a function that returns a double, and like any input argument to any function, it's evaluated before it is passed to the function string. When it was evaluated, it returned a double. So string did what it did for the first 3 examples. It just changed a double into a string. And the string function can even convert from a logical. Look at this. And here's a really nifty example. Oh my, looks like I made a little bit of an error here. But MATLAB is helping me out. Yes, MATLAB, I did mean that. Thank you for adding that parenthesis for me. What a great system these MATLAB programmers have given us. But anyway, why did we get this vector of 4 strings? Well, you may remember that the greater than sign operates element by element, and it returns a row vector of logicals. String was given that row vector as an input, and it converted each element to the appropriate string to produce a row vector of corresponding elements. So, to summarize conversion from logical to string, a true input produces the string true, and a false input produces the string false. Not exactly earth-shaking, but this operator can be quite helpful when you need to produce output in string format, say for printing or for exporting to Excel or any other application that takes strings. You can't go the other way, though. As we learned when we tried to do subtraction on numbers written as strings, MATLAB will never try to determine the meaning of words in strings. But you may be surprised to learn that it will determine the meaning of a numeric string. Here's some examples. By the way, only double is capable of this trick of reading numbers in strings. You can't do this with other number types like int, uint, etc. There are some important differences from what happened when we converted in the other direction. Let's pop that one up again from the command history for comparison. Let's see. The only difference that you can see here is in the 4th example. When we converted from the string pi to a double up here, we get NaN. But when we converted from the number pi to a string, we got 3.1416. So why did we get NaN instead of 3.1416? Well, NaN means not a number. And this is the function double's way of enforcing MATLAB's rule that it will never try to determine the meaning of a word in strings. When you give it a non-numeric string, it returns NaN. every time. There's another difference that you can't see. You may remember that for converting from a double to a string, the format short is used. So here. Well, when we're converting from a string to a double, the format is whatever format that is set in the command window at that time. It's currently set to short. But watch what happens if I change the format to long and repeat this command up here. Let me make this window a little bit bigger so you can see what's going on. So what you want to compare is this command and this identical command. And look at this output. For this number, we got 1.1235 because at that point the format in the command window was short. Now we get all these extra decimal places. I'm going to take it back to short because that's the way I like it. Before we continue, we should check to see what happens when we give double the old char type of string instead of the new string. Here's a head-to-head comparison. String first, char second. We've already seen the first one, which works perfectly. What happened in the second command? Yeah, we talked about this earlier, but in case you've forgotten, let me go over it again. The argument to double in the second command is actually a vector that contains two numbers that are codes for the two characters that we call 1 and 7. So with the char argument, double gets a two-element vector of numbers, and it converts each of these numbers individually from char to double. That's quite a different thing from what double does with the new type of string. In that case, the string is treated as a single element, and that single element is translated into the single number 17, right here. We showed you a way earlier in this lesson to convert the entire char vector into a number with the function string to num, which is abbreviated str to num. It converts the char vector properly into a scalar double. But I want to show you a new function for doing that called string to double. It's abbreviated str. I'll just type it. There. String to double has the advantage that it also works with a string input. You can't do that with string to num. This function gives you a way to write code that includes a string to double conversion when you don't know whether you're going to get a char type or a string, like this. There. If rand_n returns a random number greater than 0, then unknown will be a char vector. Otherwise, unknown will be a string. And we don't know which one it is. But we don't care because string to double works with either one of them just fine. So that's great, but I have trouble remembering the names of all these functions. Is it string to num or string to double or string to number, or I can't remember all that. So if you're like me, you just do this. There. String converts unknown to a string if it happens to be a char, and then we're handing double a string and everything's fine. Of course, we're making MATLAB run two functions instead of just one, so we might be making it a little hard on MATLAB, but that's a lot easier on us, and that's as it should be. We are, after all, the masters, and MATLAB is our obedient slave. Sometimes, though, MATLAB is not so obedient, like when I ask it to convert a string to an integer type, which, as I already warned you, doesn't work. Conversion to int8 from string is not possible. To that I say poppycock, balderdash, and pish posh. If you're watching this sometime in the future with a MATLAB release that's later than 2018A, and you might not get this error because this conversion is definitely possible, and all the red print in the world won't convince me otherwise because I can prove it. My proof goes like this. MATLAB can convert from a string to a double, and MATLAB can also convert from a double to an int8. So invoking the principle of transitivity, we know that it can convert from a string to an int8. In fact, we can do it indirectly in one line like this. End of proof. QED. Case closed. And more importantly, I managed to work in the word transitivity, which also shows how smart I am. So that's it for conversions involving strings. No, wait, there's one more thing. Look at this conversion. Here we've given the string function a cell vector containing a double, a logical, and a char vector, and it converts each one of them and returns them in a vector of strings. This example shows that the string function will reach inside a cell array and convert different types into strings. This feature lets you avoid having to use looping when you're given lots of heterogeneous data in a cell array, and you need to translate it into strings. So that's it for conversions involving strings, and this time I mean it. So what's next? Well, so far we've treated our new strings as indivisible elements, but they of course comprise a sequence of individual characters. So what if we need to access those individual characters? We learned earlier in this lesson that with the old char strings, we could use normal vector indexing. First, let me clear this command window. Remember this example? That was Plan B for the title of our textbook. So here we've asked for elements 1 through 6 of this string, and that gave us MATLAB. When we first did this, it seemed a little surprising that it even worked, because MATLAB for smarties doesn't look at all like any vector we were used to. Well, now you may be comfortable thinking of a string as a vector, but don't get too comfy with this idea because it doesn't work with the new string. It doesn't work because a new string is just one monolithic element, and you can't index into an element to isolate individual characters any more than you can index into a double to get an individual digit. I mean, like this, for example. This isn't going to give us the 7. There's only one element. We asked for element 2, so index exceeds array bounds makes sense, just as it did when we had a string with just one element. But you can do it another way with strings. Here's an example showing you how using a new function called extract between. As you can see, I've given this function 3 arguments. The string that I want to access, the starting position of the characters that I want, and the ending position. Note that the B in the name of this function has to be uppercase. And also note that the word between is not quite right, because in addition to the characters between 3 and 8, which is this first D and this D, it includes those 2 characters too, so it's not really between. I have trouble remembering the name of this function, the capital B, and the meaning of between. Oh my goodness, this is all way too complicated for old Mikey boy here. Fortunately, there's a workaround. Just convert to a char, and use normal indexing, and convert right back to a string again. Sure, it takes 2 steps, but you don't have to remember the name of a new function or how it works. Yeah, I'm sure some people at the MathWorks think I'm wrong to teach this method, but I love it. And if loving it is wrong, I don't want to be right. Here's another example. This stuff is tasty. And now to access some characters inside it. Oops, I guess I should have left the semicolon off. But when you do it, you can leave it off and see the answer to the riddle I gave you 30 minutes ago. Wait, you are doing everything I'm doing, right? Don't be that guy standing over at the side in the yoga class. Okay, I like converting to a char vector and indexing better than using extract between, but the function extract between does other things too, such as extract the part of a string that comes between two substrings inside it, as in this example. This works pretty well, and this time the word between in the name of the function is correct. So I'll be the first to admit that extract between does have its place, and so do its sister functions, extract before and extract after. Yeah, there are 3 extract functions. There are a couple of insert functions too, and by now I'm sure you are guessing that there are lots more built-in functions for working with strings and or char vectors. Yep, you're right, 58 of them. 58 functions that MathWorks considers to be the basic functions for working with this data type. And we better get busy because we need to go over every single one of them in detail. So get comfortable because, just kidding, that is not happening in my class. Instead, I'll show you where you can find a list of these functions with links to explanations for every one of them. You can figure them out yourself. I know this because you've made it to lesson 7. I can see also that you happen to be, let me check here. Yeah, you're in the top 5% of the students taking this course. So for you, this should be a walk in the park. Okay, time to clear the command window again. And then I'm going to type doc. And up pops this help window with a document page open that's called MATLAB documentation. To find those links to all 58 string and char functions, here's what you can do. Click on MATLAB, which opens a document page called MATLAB. Click on Language Fundamentals, and just to show you that I can, I'll click on this link on the left over here. These are just links, without all the explanatory text. Both sets of links, the ones on the left and the ones on the right, take you to the same places. And there we go. That closes the MATLAB page and opens up the Language Fundamentals page. Click Data Types, and now we're looking at the Data Types page. Finally, click Characters and Strings. Okay, here it is at last, the list we were looking for. The list of built-in functions for working with characters and strings. Wait, you know what? Before I get into the functions for characters and strings, I want to show you that there are other lists of built-in functions that you might want to consult from time to time. For example, let's go back to the previous page by clicking this left arrow up here at the upper left. And that takes us back to the list we were looking at before. And then let's click, let's click numeric types. And here's a list of functions that work with numeric types. You can scroll down and see all of them. These are functions that are deemed to be basic numeric functions in MATLAB, so the list leaves out square root, for example, and cosine, and hundreds of other built-in functions that also work with numeric types, but aren't considered to be basic. Okay, let's go back to characters and strings by clicking the left arrow and then clicking characters and strings, and here we are again. The functions in this particular list are hidden from view right now. All you can see are subcategories. That's nice and organized, but if you want to see a list of all the character and string functions at once, just click this teeny tiny expand all over here at the right side, and there they all are. And we can scroll down, and here's extract between, which we've just introduced. I'll click on that, and up pops the help page for that function. Now you can see all the ways that you can use extract between. And this is exactly the same help page that you'd get if you typed doc extract between in the command window. So, sorry, what? Why'd I do it that long way? What do you mean by long? A long way. Oh, I see. Got it. Why did I go through all those other doc pages when I could have gotten here in one command? Now see, just asking me that question proves that you're in the top 5%. The greatest contributions to human thought are questions, not answers. Answers are literally in second place. And here's the answer to your excellent question. It's the only way to find what you can do when you can't remember the name of the function that does it, or have never even heard of the function. What we've just shown you about navigating these documentation tabs will get you to any basic function in MATLAB for any data type. Okay, let's tidy up, because we are done with our introduction to the new string type. And we need to get ready for another new type.